Hi everyone, welcome to PrepFusion. So we are going to start our new chapter now that will be semiconductor junctions. Sir, what is the meaning of junction that we need to understand, and mainly in this particular chapter we will study about PN junction only. Sir, what do you mean by PN junction? So everything we will see, but we will build up our concept from where we left. We left at the semiconductors. We saw uniformly doped semiconductor, we saw non-uniformly doped semiconductor. Okay, so we will start from there only. Now some people would be thinking that sir, I already know the concept of uniformly doped n-type semiconductor. I already know everything, but still you should not be skipping this part. Here in this particular part, whatever that we are revisiting, in that particular part as well, I will be telling some new things. Okay, so those new things you need to learn. So don't skip it. You can watch it in a quicker manner, but don't skip this particular part, because from here only the concept of PN junction would be made up. Okay, so we have studied this uniformly doped n-type semiconductor. What was the Venn diagram for this one? This was at equilibrium. What do you mean by uniformly doped? The doping has been done uniform. From x equals to 0 to x equals to L, the doping is uniform, right? So what kind of energy band diagram you were getting? Sir, very simple. I was having EC, valence band, and in between I was having intrinsic Fermi level. And sir, since it is n-type semiconductor, so our Fermi level would be nearer to conduction band. So conduction band, valence band, intrinsic Fermi level, and EFN, right? And sir, when I applied an external bias, what really happened? Sir, here positive voltage came into action, here negative voltage came into action. Whatever the electrons that were at x equals to 0, electrons at x equals to 0, so their energy went down, and here negative into negative, their energy went up. So this kind of diagram we were getting. So sir, this we have already studied, and sir, I already know that EC, EV and EFI, EC, EV and EFI would always have the same phase. Whatever the look EC would be having, the same look EC, EV and EFI would have. Along with that, sir, there is some current flowing as well. So there is some current flowing as well. So that's why there would be a slope in EFM as well. Here there was no slope in EC, no slope in EFN, no slope in EFI and no slope in EV. Why is that so? Because sir, there was no current and no electric field. What did I tell you? Electric field would be 1 by Q dEC by dx. Here you can see that there is a slope. And what is the direction of electric field? Sir, the direction of electric field is this one. This is the direction of electric field. So in the direction of electric field, the slope of EC would be positive. So in the direction of electric field, the slope of EC is positive. So this is also I told you, right? So this was your E external. All good. Along with that, I told you the current would be proportional to the slope of Fermi level. Note this Fermi level. This intrinsic Fermi level is of no use. In this chapter, I will be rarely making this intrinsic Fermi level. Okay. This is of no use, but our main Fermi level is this one, which is coming because of n-type semiconductor. So here in this n-type semiconductor, the slope of Fermi level would be representing the current. So if there is some current, that means there would be some slope as well. And in the direction of current, the slope of EFN would be positive. So this we have already studied. Then we studied about non-uniformly doped n-type semiconductor. So in non-uniformly doped n-type semiconductor, what was the scenario? Sir, this is the scenario. Again, it is open circuit only. Sir, one particular part is highly doped and one particular part is moderately doped or lightly doped. So this part is highly doped, this part is lightly doped. So the part which is highly doped, that can be represented as N plus, and the part which is lightly doped, that I am representing with N. Is that clear to you? N plus means highly doped, N means lightly doped. So what will happen? Sir, because of the concentration gradient, here there are more electrons, here there are lesser electrons. What electrons would do? Electrons will try to move from left to right. Right? These electrons will try to move from left to right because there is a concentration gradient. Our tendency or the tendency of electrons would always be that we will always move from higher concentration to lower concentration. Same goes for holes as well, from higher concentration to lower concentration. Right? So since they are moving, then what will happen? Sir, here positive would be maintained, and sir, here a lot of negative charges would be there. And because of that, sir, there will be one electric field build up. That electric field we called as E built in. Or you can say, sir, there is some potential build up here. That potential we were calling as V built in. Right? Now this electric field, what this electric field would do? Sir, this electric field would make sure that if a lot of electrons are moving here, then this particular electric field would put this kind of force on the electrons. So electrons would be drifting in this particular direction and they would be diffusing in this particular direction. So this was your, initially electrons were diffusing in this direction, so this was your electron diffuse. I am moving a bit faster because this we have already understood. And electrons are drifting in this direction, so this is your electron drift. Since electrons are drifting in this direction, because of the drift, the current direction would have been this. So this is your I drift. And since they are diffusing in this direction, so this would have been your I diffusion. And at the equilibrium, I drift would be equals to I diffusion, and the total current would have been 0. And it is pretty obvious as well, because this is the semiconductor which is having no external bias. If there is no external bias, that means it is under equilibrium. And under equilibrium, there has to be 0 current. So current is 0, but there has been an electric field that has been built up, that is E built in. So what kind of energy band diagram we were making? So this kind of energy band diagram we were making. There would be a slope in EC. Why is that so? Because this particular part is positively charged and this particular part is negatively charged, and because of the positive charge on the electrons, their energy is going down, and because of the negative charge on the electrons, their energy is going up. So this side energy is going up, this side energy is going down, right? Or how you can think, sir, this is the direction of built-in electric field. So in the direction of built-in electric field, the slope of EC has to be positive. In the direction of built-in electric field, the slope of EC has to be positive. So in this manner as well, you can understand. Now one thing you know that, sir, current is 0. Sir, since current is 0, so there will be no slope in EFM, right? There will be no slope in EFM. And what about EV, sir? EV would look similar to EC only. EV would always look similar to EC only, and same goes for EFI as well, but I don't need to make EFI, okay? I am not making EFI here. But there is something wrong in this diagram. What is wrong, that we will see later on, okay? There is something wrong in this diagram. Can anyone think of it? What is wrong? What did I tell you? That your electric field would be this relation. Electric field is equals to 1 by dEC by dx, right? So can I directly write down that electric field? Here electric field I am denoting by capital E, but it should be denoted by small e. Like not small e, this kind of E. So I know one thing, that electric field is proportional to dEcx. Your EC is a function of x, no? Like here EC value is low, here EC value is high. So it is a function of x divided by dx, right? Now, if I am saying that the slope of EC is uniform, like if you are making this kind of EC waveform, energy versus x you are drawing, and this you are saying that this is my EC. That means you are saying that ECx is linear. It could be, sir, some 3x plus 5. So this could be the expression of ECx. And if you differentiate it, what do you get? 3. That means you are saying that, sir, this built-in electric field, it will be a uniform value. But when we solve the numerical, I got to know that this built-in electric field was not a certain numerical value. It was coming out to be a function of x as well. Are you understanding this point? Here, if I am making this diagram, right? If I am making this diagram, what I am saying? Sir, dEc by dx is uniform. It will be a constant value. Or I should say it will be a uniform value. If it is a uniform value, that means my built-in electric field should also be uniform. But when I solve the numerical problems, I got to know that built-in electric field was actually a function of x, and it is pretty obvious as well. No, why it is obvious? You consider this particular structure, okay? You consider this particular structure. If I go to this electron and I ask him, do you see concentration gradient? What I am doing? I am going to this electron and I am asking him, do you see concentration gradient? What he will say? Sir, here I see one electron. Sir, downward I see one electron. Sir, here also I see one electron. So basically, sir, I am not seeing much of concentration gradient, although this electron knows that if he looks ahead, then there are no electrons here. Although this electron knows that, sir, there is concentration gradient, but near me, there is very less concentration gradient. But if I go to this particular electron, what this electron would say? That, sir, if I look ahead, no electrons. If I look this side, no electrons. Sir, there are very lesser electrons. If I look downward, then there is an electron. But sir, I am surely seeing some concentration gradient. Basically, this particular electron would see more concentration gradient than this particular electron. That means which electron would be more tending to diffuse? Which electron will diffuse more fastly? this electron will diffuse more fastly or this electron will diffuse more fastly. Who has more tendency to diffuse? This particular electron will have the more tendency to diffuse, no? Are you able to understand this point? Because this particular electron is seeing more concentration gradient. So what will happen? This was your scenario. Now this particular scenario, this donor atom, what it would do, this would leave its electron very fastly. I should not say very fastly, basically this particular electron would have more tendency to diffuse. That means this would become a positive ion, and surely here there will be some negative ion because of the holes. So here the electric field would be built up. So more tendency of electric field to be built up is there in this particular region. Although here also some electric field could be built up. Here also in the whole scenario some electric field will be built up. But the important part is that electric field will not be uniform. Surely at the junction, this is known as junction only, because after this the scenario is changing, no? Before this uniform doping, after this uniform doping. But here at the junction, at the midpoint, the scenario is changing. From n plus 2 we are moving to n. From n plus 2 we are moving to n. N plus 2 n. So where the scenario is changing, at the junction you will get maximum electric field. Do you agree to this point or not? Without mathematics we are able to understand this particular point. Just by the pure intuition, that this particular electron will have more tendency to move than this particular electrons. That means this will make stronger electric field here. So here if I am making this particular diagram, what does that mean? I am saying that, sir, electric field is constant. This particular diagram I am making with respect to x, right? This particular part was x equals to 0. I hope you haven't forgot. Like this particular part I used to call x equals to 0, and this particular part I used to call x equals to L. So I was saying that from x equals to 0 to x equals to L, I am having a uniform electric field, which statement was absolutely wrong. So there is some problem in this diagram. That problem I have told, right? So how we are going to eradicate this problem, how we are going to move from here to the actual diagram, that I am going to tell now. But before that we can see one more case. Right, all this is fine, this also I can remove. So in short you can write down that this is having some problem, but this problem will be eradicated later on. Okay, now in this particular diagram what was the scenario? First, this particular semiconductor that was in equilibrium. In equilibrium what was the scenario? That some built-in electric field has been set up here, right? This built-in electric field has been set up here. Now what you are doing, you are applying an external bias. Because of this external bias, what will happen? There will be another field that will be set up. There will be another field that will be set up across the semiconductor. That field will be EB, right? So this particular field will be EB. Now this EB is actually supporting EBI. What was the role of this EBI? What was the role of this EBI? This EBI that was set up, what was the role of this EBI? That if some electron will try to diffuse from here to here, then what this EBI would do? This was trying to go from here to here. This EBI will put the opposite force. This electron was trying to diffuse from here to here. EBI will say move back. Electron will say I want to diffuse because of the concentration gradient, but EBI will say move back. Now what is the scenario? You have made EBI more stronger. Another external bias you applied, that EBI has become more stronger. So now what this EBI would do? It has been become more stronger. So the electron that tried to diffuse from here to here, now he will not be able to diffuse more. Why is that? So previously only he was not able to diffuse, now as well. Now that tendency of diffusing has become even weaker. But because of this higher electric field, what will happen? Because of this higher electric field, what will happen? That this particular electron which was here, now the drift would increase. Are you able to understand this point? Do you remember this particular scenario? We made the diagrams and then I told you that diffusion would depend on Q dn dnx by dx. Now diffusion almost remains the same, but because of the higher electric field, what will happen? The drift would increase. So here what will happen? The drift would increase, right? Although this is not important, but directly I will make the diagram. Here what I would do, sir, EB plus EBI, that means electric field has become stronger. So this slope would become even more stronger. This particular slope would become even more stronger, right? Here I was having this much of slope. Here I would have even more slope. But again, this diagram is not completely correct. Why is that so? It is partially correct only because here you are saying that sir, slope is uniform. If slope is uniform, that means electric field should be at all the points electric field should be uniform, but it is not the scenario. Electric field is not uniform. Here at the junction you would get a more electric field, but at these points the electric field would be lesser, right? So EC. Now there would be a current as well. What will be the direction of current? Sir, electron tried to diffuse from here to here, and electron tried to drift from here to here. This was the drift, this was the drift, and this was the diffusion. Now sir, because of this applied electric field, the drift has been much more stronger. The diffusion is, you can say as it is, but drift has been much more stronger. Why drift is stronger? Drift is stronger because of this electric field. This external electric field is making this drift stronger, and if this drift is stronger, then what will happen? The electron would be drifting in this direction, and if they are drifting in this direction, that means there will be some drift current that would be set up. So in this particular direction, drift current would be set up, and I told you a very simple way that whatever the direction of battery is there, based on that you can understand what will be the direction of current. If you don't want to think this much diffusion, drift, if you don't want to think in this direction, what you can simply say, so battery direction is this one, so from battery always the current would get out. So current would always get out from here. Or what you can see, sir, diffusion and drift were equal under the equilibrium. Now what you have done, you have made drift stronger. Why drift stronger? Because E built in and EB, they are supporting each other. They are in the same direction. So if the drift has been becoming stronger, that means electron would be drifting much more now. So because of that, the drift current would be more than the diffusion current. So eventually drift and diffusion were cancelling out each other, but now the drift has become even more stronger, and because of that the final current would be because of that drift, right? And if electrons are drifting in this direction, that means the current would be in this direction. So what will be the direction of current? This would be the direction of current. So all these points we have already discussed, just we are revising and we are getting to know that what was wrong there, right? What was wrong? The wrong was that, sir, this is how the diagram should not have been made, because you are saying that, what you are saying? Sir, you are saying that EC is, the slope in EC is uniform, that means your electric field would be uniform, okay, which is not the correct case. Now I want to ask you another question. What I want to ask, let's just say this is 5 volt, okay, so how this 5 volt will be dropped down across the semiconductor? What I am asking, I am saying that, sir, VB is 5 volt, and I am saying that this is 0 volt. If this is 0 volt, then surely this will be 5 volt, right? So let's remove this EB for now. This EBI I am making here, okay. So what I am saying, this is 5 volt, this is 0 volt. Now how this 5 volt and 0 volt will be dropped down? This is what you need to comment. Like, will it be dropping down equally? Like 5 volt, then here 4 volt, then sir here 3 volt, then sir here 2 volt, then here 1 volt, and then sir 0 volt. Will it be dropping down equally? No. Why is that so? What did I tell you? That this particular electron has more tendency to leave, right? This particular electron will have more tendency to leave. This particular electron will have more tendency to leave. But this particular electron will not have tendency to leave. So eventually what kind of scenario you will be getting? Sir, here plus 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 has been made, and here plus with electron, plus with electron, plus with electron, plus with electron, plus with electron. And I told you in semiconductor, who is responsible for the current? Who is responsible for the current? These electrons, these movable electrons. These electrons can move. So these movable electrons are responsible for the current. Now what is happening here? You are only getting the charge. This positive charge will not move, no. Who will move? Electrons will move. This positive charge will not move. That means in this particular region, what you have done? At the junction, what you have done? At the junction, you would see that the number of electrons which are present, that are very, very less. The number of electrons which are present, the number of movable electrons which are present, that has been gone. Because of that, this particular region will have more resistivity. Like if charge carriers are present, that means n value is high. What is the value of sigma? Sigma is n q mu. So if charge carriers are present, then n is good enough. If n is good enough, that means sigma is good enough. If sigma is good enough, that means J equals to sigma, current would be good enough. Basically, if sigma is good enough, then resistivity, what is the resistivity? Resistivity is rho, that is 1 by sigma. If sigma is good enough, that means resistivity will be low. That means this particular part is having lesser resistance and this particular part is having more resistance. Why is that so? Because this particular part has lost its movable electron and eventually it has become only plus 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 plus. And since it has lost its movable electron, that means its resistivity has become higher. So what does that mean? If I make the equivalent diagram, can I make it in this manner? That here there will be lesser resistance, but here there will be much more resistance, and here as well there will be lesser resistance. Why is that so? Because the important part would be happening at the junction only. Are you able to understand this point? The important part would be happening at the junction only. This will say, sir, I don't see much of concentration gradient. Why is that so? Because he can see that one electron is there. He can also see that one electron is there. But what he will see, sir, 3 electrons are there. I can see this electron as well. I can see this electron as well. Sir, I can see this electron as well. Right? Are you able to understand this point? Okay. So more electrons from here would come this side. They will not be reaching towards till this side, but most of the electrons would be reaching here only. Are you able to understand this point? Right? And all these things we will see in our PN junction as well. But as of now, what did you understand? That at the junction, there is high resistivity. So because of that, this 5 volt will not be dropped equally. Most of the 5 volt will be dropped at the junction only. 4.9 will be dropped here only. So if this is 5, this will be 4. Or let's call it 4.8. So if this is 5, this will be 4.9, and if this is 0, this will be 0.1. So you are getting 4.9 minus 0.1, 4.8 volt here. So at the junction, from this VB, most of the potential will be dropped at the junction only, because at the junction you are having very high resistivity. Why you are having very high resistivity? Because at the junction the movable charge carriers are gone, the movable electrons are gone. This was having some electron, this was having some electron, but this guy has lost all its electron. Right? So this VB will also not be dropped equally. Most of the part of VB will be dropped at the junction only. Are you able to understand these points? Okay. From here only all the concept of PN junction has been built up. Okay. But directly we start from PN junction, and that's why sometimes we find PN junction as a tougher topic. But we will build up all the concept here. When we move to PN junction, you would realize that it is simply a piece of cake. Okay. So this diagram we have made. Now let's understand these particular scenario by some other sense. What kind of sense? So what I am doing, I am picking one N plus semiconductor and one N semiconductor. Both are same material. Basically, I had a silicon semiconductor, same material was there. What I did more doping here. But I did lesser doping here. So this is also N type, this is also N type. Right? But here there is more doping, here there is lesser doping. So that's why I am calling this one as N plus, this one as N. So I am calling this is N plus type of semiconductor and this is N type of semiconductor. Okay. So can I make the energy band diagram for them? Surely I can make the energy band diagram for them. How can I make the energy band diagram? Sir, EC, EV. Sir, EC, EV. Sir, why this gap is same? Why this gap is same? Because they are made from same material. Same material means they will be having same band gap. EC minus EV represent band gap only, no? So they are made from same material. So they will be having same band gap. Right? Now where would the EFI come into action? It would be right in between. Okay. So here would be your EFI. Now I will make EFN now. Right? Fermi level I will make. So this is more highly doped. That means EFN would be closer to EC, right? More doping means more closer to EC. These much basics you already know. And lesser lesser doping means far from EC. Although it is N type only, that's why the EFN, the Fermi level would be on the upper part of intrinsic Fermi level, that's for sure. But here there is more doping. That's why this EFN is here, and here there is lesser doping, that's why this EFN is here. Do you understand this gap? This gap is lesser. That means it is showing more doping, and this gap is more. that means it is showing more doping. Here also you can verify the same thing. Less gap here, more doping. More gap here, lesser doping, right? Now if I join them, okay, what I do, I join them. I join them in this manner. I have joined them. Now one thing I know, that eventually this semiconductor would get into equilibrium. Eventually this semiconductor would get into equilibrium. At equilibrium, what will happen, that I don't know. Although I know what will happen at the equilibrium, but as of now, let's consider that, sir, I have joined both of them. What will happen at the equilibrium, I don't know, but I know one thing, that at the equilibrium, current has to be 0, because there is no external bias. So current has to be 0. If the current has to be 0, what does that mean? That means this EFN plus and this EFN has to be flat. Are you able to understand this point, what I am saying? When I joined them together, I know that, sir, I don't know anything, but I know that current would be 0. At the equilibrium, current would be 0. If the current is 0, that means if I make the Venn diagram, then whatever the Fermi level I make, that has to be flat. Whatever the Fermi level that I make, that has to be flat. What does that mean? If you want to make the energy band diagram for this one, then the Fermi level has to be flat. So what you can do in this diagram, that this part goes up downward and this part goes upward. This EFN plus goes downward. This is your EFN plus, this is your EF. This part goes downward and this part goes upward. Then they would come together. Are you able to understand this point? EFN plus goes downward, EFN goes upward. So they would come together. That means this part need to come downward and this part need to go upward. So what will happen? This EC would go upward and this EC would come downward. So if you make the diagram, how it would look like? So this EC has gone upward and this EC has come downward. And eventually what you can see, sir, EFN has become flat. I hope you are able to visualize this particular thing. I should not write down EFN, I am simply putting EF, because if I write down EFM, then people will think that this did not move, only this guy moved. But actually both are moving, right? This one is going upward, this one is going downward, because I know that the Fermi level has to be flat. So I am simply putting EF. Similar thing would be happening with EV as well, but you don't need to think of EV. Why is that so? Because you know that whatever the structure EC is having, the same structure EV would have. So I don't need to think much about I don't need to think much about EFI and EV, because I know that they will follow the same structure as EC. So we are only talking about EC now. We are only considering about EC now. So what really happened? These guys move upward and this guy went downward. So I will simply make two arrows in this manner, that this one moved, this one moved downward and this one moved upward. So EC went above. Here also, like, both were at the same level previously, because both were made from the same semiconductor material, no? So both were at the same level previously. But now what really happened? This has went upward, this has went downward. Now you know one thing, when I go from x equals to 0 to x equals to L, okay, when I go from x equals to 0 to x equals to L, I know that my electron concentration is decreasing. If electron concentration is decreasing, what does that mean? That means the gap between EC and EF should rise up. Basically, you need to join these lines. Are you able to understand this point? And when you walk through this particular scenario, what do you see? This gap is continuously increasing. This gap is continuously increasing. What does that mean? That means your electron concentration is decreasing. If this gap increases, that means electron concentration is decreasing. Are you able to understand this point? Very simple point. Very, very straightforward. If the gap between EC and EF is more, that means your electron concentration is less. So why I joined them? This is the main target. Why I joined them? I joined them because I know that when I move from here to here, this gap should rise up, which is rising up as well. So I joined them in this manner. Sometimes in books, what you will find out? In books, you will find out that they have joined like this. But if I join like this, there is some error. What is the error? What do you think? The same error that we discussed. What is the error if I join by a straight line? If I join by a straight line, the problem is that you are saying that built-in electric field will be uniform. But is your built-in electric field uniform? No. That is a function of x, because more built-in electric field you will get here. Are you able to understand this point? So this is how I should join them. Okay, and when you find out the slope, you will see that at the junction you will get the maximum slope. Why at the junction you will get the maximum slope? Because you know that at the junction you will have the maximum E field, maximum electric field. So whatever the kind of structure of EC you are getting, the same kind of structure of EFI you would get, and the same kind of structure of EV you would get. What I do is that I will simply copy it. Okay. I don't need to make EFI, so I'm not making EFI. Okay. Now let's see more things. What all more things we can see from here? But this gap is looking lesser now, so it doesn't look good. Basically, both are N-type only, no? So the gap between EF and EV would be more only. What I mean to say is that this gap would always be more than this gap, no? Right? So this gap should look larger only. Although this gap would be very, very larger. This particular gap would be very, very larger. Right? But anyway, this gap, and if you compare this gap, so this gap would always be lesser. Why is that so? Because both are N-type. Although this is highly doped, that's why this gap is very less, and this is lightly doped. But both are N-type only, no? So they can never be closer to EV. Here also this gap has to be more only. That's why I made this diagram. Now more things we can see. So the correct way of representing the diagram would be like this, not like this. So in the examination, if the diagram is coming for this particular diagram, then the diagram would be made in this manner, not in this manner. In the worst case, if it is made in this manner as well, what you would do, you will click on the correct answer. That's why this is correct. But actually, it will be made in this manner only, not in this particular manner. Is that clear to you? Okay. And why I made them flat here? Nearly they will be flat. Why nearly flat? Because you know that here the electric field, the built-in electric field will be very, very less. Why it would be very, very less? Because you know that the tendency of leaving the electron is very less here. Because this is not seeing much of concentration gradient. Although he knows that there will be concentration gradient, but if you just look here, then there is not much concentration gradient. And if there is not much concentration gradient, then tendency of leaving the electron is very less here. So that's why I made it nearly flat, and then this kind of slope I was getting. Okay. Now more things I can see. On this side there is more electrons, no? This is your x equals to 0, and this is your x equals to L. So here there is more electrons, and here there is less electrons. Yeah, that's fine. Okay. The built-in electric field is in this direction. Now you let me know, if electron wants to move from here to here, the electron wants to go uphill. The electron wants to go uphill. So what could be the motivation to go uphill? Diffusion. Whenever electrons wants to move uphill, the motivation is diffusion. And whenever the electron wants to go downhill, the motivation is drift. What I actually mean to say is that if you are standing here, and if I push you, if I just give you some push, what will be happening? You will be rolling down, right? If you are standing here, and if I give you a light push, will you be reaching here? No. If you are standing here, and if I give you light push, will you be reaching here? No. But if you are standing here, and I just give you a light push, what will happen? You will roll down. It might happen that, sir, the push was not very strong, so I reached till this point only. But what I am saying is that with respect to the applied electric field, if I am applying an electric field in this direction, or you can say this is built-in electric field only, which has been come up from the material only. So if there is an electric field in this direction, what does that mean? That means you are putting the force on electron in this direction. So these electrons will move from uphill to downhill because of the external force. But this external force will not make them move from here to here. Right? Basically, if you are standing here and I am pushing you this side, basically this electric field, what is the meaning of this electric field? The meaning of this electric field is that force on electron will be on this side. So if you are standing here and I am pushing you this side, what does that mean? That means I am stopping you to go to the uphill. So this particular electric field is making them come downward, and this particular electric field is stopping them to go uphill. But there is some motivation to go uphill. What is that motivation? That motivation is diffusion. Like here there are more number of people and here there are lesser people. So what do you think? Sir, I don't want to settle down here. Where you will be settling down? You will be settling down in Delhi or you will be settling down in Manali. Where you would want to settle down? Where there is less crowd. So motivation for these guys is diffusion because there is lesser crowd. Always we want to diffuse from lesser crowd to, from more crowd to lesser crowd. So from more electron density to lesser electron density, they want to diffuse. So this is the diffusion. But what is the force here? People from Manali also want to settle in Delhi. Why is that so? Because in Delhi, you will get better facilities, right? There will be better hospitals, there will be better schools. So there is some force which is making them go downward. That is drift. Because of the drift, they want to go here. And because of the crowding, they want to go from downward to upward. So did you understand my point? This I am telling for electrons. For holes, it will be completely opposite. Holes will try to, they can move from here to here because of the drift. Like whatever the process that happens in electrons, the opposite process happens in holes. This I have already told, right? So electrons will move from, holes. What about the holes? If I talk about holes here, so here there are lesser holes and here there are more holes. Although this is n-type semiconductor, but in n-type semiconductor as well, there will be some holes, no? So if there are lesser electrons, that means there are good amount of holes. And if there is more electrons, that means there are lesser holes. Although the number of electrons in this side would be more than the number of holes only. But if I compare, here there will be lesser holes and here there will be more holes, right? So if electron wants to move downward, then what is the motivation? The motivation is diffusion. And if they want to move upward, then what is the motivation? Motivation is drift, because built-in electric field is in this direction. So what this built-in electric field would do? Built-in electric field would force the electrons, it would force the holes to go upward. So are you able to understand this point? I am writing down one conclusion. What is the conclusion? That I am writing for electrons. For holes, it will be completely opposite. We will not think in the direction of holes. We will always think in the direction of electrons. So what I am saying, for electrons, downward I can write down. Downward motion means drift, and upward motion means diffusion. Now under the equilibrium, what is happening? Let's remove all these guys. Okay, so under the equilibrium, what is the scenario? The same number of guys are moving upward and the same number of guys are moving downward. So concentration here and here remains same. Basically the same number of guys are moving upward. That means the same number of electrons are diffusing and the same number of electrons are drifting as well. That means drift and diffusion current is same, and drift and diffusion current is same. What does that mean? Total current is zero, and that's why this particular condition is known as equilibrium condition, right? So motivation to move upward for electrons, that would be diffusion, right? Why is that so? Because of the concentration gradient. And motivation to move downward, just a little force would make them move downward. So that would be drift. Because of the electric field, you are moving downward. Is that clear to you? And here in this scenario, drift and diffusion are equal to each other. Now what do? I apply an electric field. What do? This scenario I have already understood. So this was the scenario. This was flat. So they were joined together. The same structure I got here. So this was flat only. Now if I apply an electric field which is in this direction, I am applying this electric field which is in this direction. So what do you think what will happen now? If I am applying an electric field which is in this direction, what does that mean? Positive multiply with negative, that means their energy would go down, and negative multiply with negative, their energy would go up. So the same diagram, what it will happen? This particular part would go up, this particular part would go up, and this particular part would go downward, right? What will happen if I apply an electric field? Then this particular part would go up and this particular part would go downward. So what kind of diagram you will be getting? Sir, whatever the barrier that I was having, that barrier has increased now. So here only this much barrier was there. What this barrier is known as, we will talk about it. Although you already know the name, but we will talk about this particular barrier. So sir, this barrier will be increased now. So this particular barrier would be increased. So this particular barrier has been increased now, sir. Okay. And another thing that would happen is that, sir, now current is also not a 0. So will I make the current diagram like this? What do you think? Like, should I make the current diagram in this manner? Not current diagram. Should I make EFN in this manner? That's the EFN should be made like this. Is that correct? If I say I current is flowing here, then how much current would be flowing here? Sir, I only. Here also, sir, I only. Here also, sir, I only. Here also, sir, I only. So everywhere the same current is flowing. So ideally, how I should make my EFN? What did I say? And this is a function of x as well. Current is same, no? So ideally, this is how it should be made. Okay, but even in the examination, if it is made in this manner as well, then also it is fine. Okay, but I will make in this manner. In the examination, if it is made in this manner or sir in this manner, you would click on this that is correct. But ideally, current would be same only, no? So I would make down in this particular manner. Okay, and same goes for EV as well. But here the important part to understand, one important part we are understanding here, what we are understanding. Just join it. Yeah. So what we are understanding, that this barrier has increased now. This barrier has increased. Previously, this barrier was, this is known as built-in potential only. Sir, why it is known as built-in potential? We will discuss that. But now this barrier has become V built-in plus VB. Because whatever the built-in potential that was set up here, this particular electric field is supporting this built-in potential, right? So I should not make by arrow because potential is simply a potential only. So I should not be making it with arrow, but I should make it with plus minus. So this plus minus is being added with plus minus. That means both are supporting each other. So this barrier has increased. You can understand by the simple concept of energy band diagram as well, or you can simply say that in the direction of built-in potential only we are applying some VB. So this barrier has increased now. Now you will just let me know one thing. Here there were more electrons, right? Here there were more electrons, and here there were lesser electrons. Which process has become simpler now? Diffusion or drift? Let's just say in this scenario you are standing here, and in this scenario you are standing here. Now I am applying a force of 1 Newton on you, like I am pushing you by the force of 1 Newton. And here also I am pushing you by the force of 1 Newton. Where you will roll more? In which condition your rolling will be more? Like when you reach here, in both of the conditions, let's just say you are reaching here. When you reach here, in which condition your velocity will be more? In this condition, no? In this condition, right? Why in this condition? Because sir, here the slope is more, no? The slope is more. That means I will be moving faster. Or you can say that, sir, here the electric field has increased. The applied electric field has increased. That means you are putting more force on me. But the barrier has increased now, sir. Barrier has increased. Sir, this particular barrier has increased. When this was the barrier, even with this barrier, not a lot of electrons were able to move. Now, sir, the barrier has increased now. If it is increased, then sir, going from here to here, the probability has reduced even more. Previously, at least one electron was moving here. But here, sir, even one electron would not be able to move. Previously, what was the scenario? One was moving here and one was coming downward. So drift and diffusion were same. But now what is the scenario? So 2 would come downward, but 0 would move upward. That means drift has increased. And did we discuss the same thing here? The same thing we discussed here. The drift current would be increased. Because electric field has been set up more. Previously, whatever the diffusion was there, that diffusion also had become a bit lesser. Along with that, the drift has increased more. So this current is dominated by drift. Here what was the scenario? Drift was equals to diffusion. But here what is the scenario? The drift is more than diffusion. So this current was dominated by drift. You see here, you can understand by the analogy as well that if I am pushing you from here to here, you would be able to move faster. That means more electric field is there, more force you will feel. Even if I am applying a force of 1 Newton, here also I am applying a force of 1 Newton, but here you would feel, sir, you have put more force because I would be rolling more here. But sir, here I would be rolling less. So here what was the scenario? The amount of electrons that was diffusing and the amount of electrons that were drifting, both were same. But here you have made diffusion even lesser because you have increased the barrier. So increased barrier would reduce down the motion, would reduce down the diffusion. So this particular scenario is drift dominant. Are you able to understand this point or not? Like we understood the scenario, we understood the same kind of scenario in basic semiconductor physics as well. We are understanding the same scenario with this particular diagram as well. And now we are understanding the same scenario with the simple energy band diagram as well. So with respect to formula, with respect to energy diagram, with respect to physical meaning, from every single thing you can understand your semiconductor physics. Are you able to understand this point? Sir, why you are teaching all these points? The topic name was PN junction. Everything would come up, but believe me guys, if you have studied this particular part from n plus to n, then PN junction would be simply a cakewalk. I will be explaining there, but there you would say that, sir, I already know everything. Okay, here what we are doing, n plus and n, no. There what we will do, this side will be p, this side will be n. So here there will be more number of holes, here there will be more number of electrons. That means if there are more electrons, there will be lesser holes. So here there will be more number of holes, there will be lesser number of holes. Here there will be more number of electrons, there will be lesser number of electrons. So PN junction is nothing but it came from the concept of n plus and n. So what I am telling you here, that without a bias, this was the condition. When I applied the bias, I have increased the drift. Now if I apply the opposite bias, in this manner, this was the scenario that we already discussed, right? This is your equilibrium. Equilibrium we have already discussed. So here this was your barrier. Now what I do, I apply the electric field. This was the VB. Now I have interchanged the polarity, right? So now previously what was the scenario? Sir, VBI was set up in this manner. Now VB I am setting up in this manner. Why I am making most of the VB here? Because you know that most of the part would be lying across near the junction only, right? Near the junction only most of the part would be applied. So that's why I am making VB not like this. VB I should have made by this, but I know that most of the part of VB would be dropped across this particular junction only. So that's why I am making VB like this. Now this VBI is opposing this VB, but we will not understand in this scenario. We will understand by energy band diagram. So what does your energy band diagram say? Let me make it more better. So now what this energy band diagram would say, that sir, negative potential is applied here, positive potential is applied here. Sir, positive potential multiply with electrons. So sir, this energy would go down. And sir, here negative multiply with negative, their energy would go up. So now what will happen? Sir, these guys would go up and these guys would come downward, right? Negative multiply with negative, positive. That means here the energy is becoming more. So positive multiply with positive. Sorry, positive multiply with negative. Here the energy is becoming lesser. So this part is becoming downward, this part is coming upward. So what does that mean? The gap between this EC, the gap between this EC and the gap between this EC. So previously if the gap was VBI, now the gap has reduced to VBI minus VB. Are you able to understand this point? The gap has been reduced now. This gap has become VBI minus VB, right? So along with that, what you would see, there will be a current that would be set up in this direction, right? So current would be set up in this direction. Basically what you can see is that this part is going downward, no? So this EFN is going downward and this EFN is going upward. So this kind of current you will be getting, right? What I am saying is that, so this EFN is going downward and this EFN is going upward. So what do you see? This kind of scenario would see. This kind of scenario would see, right? So here I should write EF, not EFN, because people will be getting confused that, sir, this EFN and this EFN is same. So here I am writing down EFN, here I am writing down EFN plus. Okay, so that you don't get confused. Here only I am putting EF. Only I am putting EF. And you know that picture of EC and EV would be same only. Right? But always make sure one thing, that this gap is looking lesser, which is not correct. So this gap should always be more. Okay, this gap should always be more. So what do you think? This current would be dominated by diffusion or drift? The current that you are getting in this scenario, that would be motivated or dominated by diffusion or drift. Sir, in this scenario, we were not able to diffuse. Sir, in this scenario, we were not able to diffuse, or whatever the diffusion we were getting, the same drift we were getting. But now, sir, barrier has reduced now. So now I can diffuse more. But if you are standing here and you are standing here, if I give you a force of 1 Newton, if I give you a force of 1 Newton, in which scenario you would feel more force? Sir, in this scenario, I would feel more force because the slope is more, no? Like if I am standing on flat surface and I push you, then you would feel that, sir, I did not feel much force. But if we are on a slanted surface and if I push you, then you would roll down more. So similarly here, the effective electric field has reduced down. The effective electric field, although electric field is still in this direction, what I am assuming is that this VB is lesser. Okay, VB is not that high. So if electric field is still in this direction, right? The electric field that I am saying, that is still in this direction, but that electric field has reduced now. This electric field has reduced now. So because of the electric field, very less electrons are moving. But because of the diffusion, more electrons would move, because previously they were not able to climb up. But now they will be able to climb up because the slope has become lower. So here there were, basically what I would do is that I would take this scenario here. Okay. So previously they were not able to climb up, but here these more number of electrons, they will be able to climb up more. And if they are able to climb up more, then what will happen? They will be moving in this direction, and since they are moving in this direction, so current would be set up in this direction. So more diffusion would be there. Although some electrons will still be moving here. Some electrons, let's just say 1 electron is moving here, but 3 holes will be diffusing here. If 1 electron is moving here, that means drift current would be in this direction. But this drift current would be lesser, but more electrons are diffusing. That means more diffusion current would be there. So this is your drift and this is your diffusion. So diffusion would be more than the drift. So total current would be flowing in this direction, and which we can directly see that this is the direction of current. Okay, not able to make in correct manner, but you can see that or from the battery as well, you can see that, sir, this will be the direction of current. So in the semiconductor, current is flowing like this. So are you able to understand the depth? Right? Diffusion, drift. Drift is lesser, diffusion is more. So what I would say, this is diffusion. Here what I write down? Yeah, drift dominant. So here I will write down diffusion dominant. Now the question would come up, sir, why you are doing all these things? So remember the first lecture. In the first lecture, what did I say? Why we are using semiconductors? Sir, we are using semiconductor to become controlling. What we need to do? We need to control. I want to be controlling. Controlling for a human being? No. Controlling for current. Sir, I want to be controlling. So first scenario what we studied, that sir, by doping you can control. Sir, there was intrinsic semiconductor that was having very lesser current. So sir, you did the doping. When you did the doping of p-type and type, you were able to get more current. So sir, by doping you can control. So first thing is already studied. Now second thing is, sir, if you have done the doping, that means you have made a particular device, no? Let's just say this fan is running at a speed of 4. Now I want to run this fan at a speed of 5. So will you say buy a new fan? Right? This is not the criteria, no? Using this fan only, you need to control the current. So using the same material only, using the same semiconductor only, I need to control the current. If I was using this kind of semiconductor, uniformly doped semiconductor, then whether you apply the electric field in this direction or you change the electric field. Let's just say if I had applied the electric field in this direction as well. Previously I am applying electric field in this direction. So whatever the current that I am getting, that is same. If I interchange the polarity, then also the current would be same only, no, just the direction would change. But the amount of current remains the same only. I am just telling why we are studying all this topic, why we actually study PN junction. Because we want to be controlling. First controlling we did with the doping. Now you know that again and again, sir, I cannot change doping. Let's just say at a particular scenario, I'm getting 2 milliampere of current. Now someone says that, sir, I need 0.5 milliampere of current. So what you will say? Change the doping. Here you are doping 10 to the power 16 atoms. Now you dope 10 to the power 14 atoms and you will get this much of current. Which is not a good way, no? Because device has been already fabricated. You cannot change the device. So what did you get to know? That from uniformly doped semiconductor, sir, I cannot achieve anything good, right? From uniformly doped semiconductor, sir, I am not able to achieve anything productive. Then I went to non-uniformly doped semiconductor, N plus and N. Sir, when I am changing the bias, here I am applying this kind of biasing and here I am applying this kind of biasing. Sir, with respect to changing the bias, what I can see? In one of the scenario, my current is becoming diffusion dominant. In one of the scenario, my current is becoming drift dominant. So somehow, sir, I am able to control the current just by changing the biasing. And this is what you wanted. In electronics, what we want to be controlling, not controlling for a particular device, right? Or a particular circuitry. Like if I change my input, based on the input, things in my circuitry should change. This is what I want to make. As an electronics engineer, this would be my target, that if I only change the supply, my things should be changing, my output should be changing. So if I am only interchanging the supply, like let's just say here I am applying 5 volt and here I am applying minus 5 volt, right? You are not even changing the battery. What you are doing, first you are applying 5 volt, here you are applying minus 5 volt. So when you applied 5 volt, your current was drift dominant. When you are applying minus 5 volt, your current was diffusion dominant. So basic idea I am getting that non-uniformly doped semiconductor can do something for me. When N plus and N can do this much for me, then what will PN would do for me? And from here the concept of PN junction came into action. Because here very lesser concentration gradient is there, no? But in PN, a lot of concentration gradient would be there. One side is P. That means here number of holes will be 10 to the power 16, but number of electrons would be 4, 10 to the power 4. And here number of electrons will be 10 to the power 16, but number of holes will be 10 to the power 4. So concentration gradient is very high. Concentration gradient is very high. So if in N plus and N, what was the scenario? So 10 to the power 16 electrons here, 10 to the power 11 electrons here. So concentration gradient is not that high. If I want to make the highest concentration gradient, what I need to do? One side you take P, one side you take N, and you control the current. And from here, the concept of PN junction came into action. And from PN junction, we made diode. Are you able to connect the dots now? If I started from PN junction directly, it would make zero sense. You wouldn't even understand what we are doing. But now you have the target that, sir, what we are actually doing, what was our target? Our target was to become controlling. First scenario we studied due to doping. But if I am doping, that means I need to change the complete device only. So again and again, I cannot change the device, right? If someone says that I want this feature in my phone, and now some guy came into action and he said that I want some different feature. So what you will say? Change the mobile. This is one scenario that you can change the mobile. Second scenario would be the same company. He will include more features. So similar scenario we are doing, that we will take that kind of semiconductor. Which kind of semiconductor we are going to take? That kind of semiconductor we are going to take. If I only change my input with respect to the change in the input, he will be able to change the output as well. But if I was taking uniformly doped semiconductor, then this was not happening for me. Then I took non-uniformly doped semiconductor, N plus, and then this was happening for me. And then I thought that if this much of concentration gradient is doing this much of magic, then what if I take PN junction? So that would make more magic, right? So that's why we studied all this scenario with respect to N plus and N junction. Although we will write down the summary, we will summarize the whole points. So comparing all three scenarios, these were the scenarios. First was the scenario, there was no bias applied, then this bias was applied, and then opposite bias was applied. So here if I say, sir, why this is VBI? Why this is built-in potential? Because if N plus and N was there, no? Like when they were different from each other, at that time, this was the scenario. And when they came into action, when they came together, what really happened? This bending took place, no? This bending took place. Previously, there was no bending. This is known as bending. This was flat, EC was flat, EC was flat, EFN was flat, everything was flat. When they came together, I know that EF would be flat only because there is no current. But some bending took place in EC. Why this bending took place? Because there was some built-in potential. So this particular scenario, this particular height, what this would represent? Sir, this would represent QVBI, not VBI. Why QVBI? Because sir, VBI would be having a unit of volt and charge can have the unit of, so this would be electron volt. So this is energy, no? From energy to voltage, how we would go? Sir, let's just say my energy is KT. If I want to write down voltage, what I would do? KT by Q. That would be my VT. So here, instead of writing VBI, I should write down QVBI. Are you able to understand this point? Very simple thing. Voltage, charge. Voltage into charge. Energy is equals to E equals to QV. So voltage multiplied with charge, that would be energy. So if I am making the diagram of energy, here better I should write down QVBI, not VBI only. Okay. So what I would write down? VBI. So this band bending took place because of what? This band bending took place because of the built-in potential. So this would represent your built-in potential. So this is your built-in potential. So here QVBI multiply with Q, multiply with Q. Okay. So this would be your QVBI. When you applied this bias, then this was your VBI already, right? Here what really happened? Sir, VBI plus VB. Again, like arrow sign should not be made. Better would be I should represent it by plus minus, right? Because arrow sign we make for electric field. For the potential, we always make plus minus sign. Here what really happened? Sir, VBI was there, but it was opposing each other. So this was the scenario of QVBI. Now this has become QVBI minus VB. And here you can see that sir, diffusion, it would be diffusion dominant. So here sir, diffusion is more. What about this one? Sir, this particular, what do we call it? This particular height has been increased now. Previously it was QVBI, but now this has become QVBI plus VB. So barrier has increased now. Barrier has increased, that means diffusion would be less, but drift would be more. So this has become drift dominant. Okay. In both of the condition, there would be current. EF and I should not write down. EF I am writing now. And here also EF I am writing now. Okay. And we can see that sir, we are able to control the current just by changing the polarity. Here I am applying 5 volt, here I am applying minus 5 volt. Or you can say sir, this is 5 volt, this is minus 5 volt. It would be relative, no? Someone says this is 5 volt, then he would say this is minus 5 volt. If someone is saying this is 5 volt, then this would be minus 5 volt, right? So here drift is more, diffusion is more. Here there is no current. Here there is drift equals to diffusion. Okay. Now let's find out the expression of this built-in potential. We have already found out the expression of built-in potential, but using the mathematics. Now using the diagram only, I will find out the built-in potential. So what is the meaning of built-in potential? When there is no external bias, or you can say open circuit, when there is no external bias, then what is the potential that has been set up inside the semiconductor? That is known as built-in potential. Okay. When the semiconductor is under equilibrium, when the semiconductor is under equilibrium without any external bias, no external bias means equilibrium condition only. When the semiconductor is under equilibrium, then what kind of potential has been built up? That is known as built-in potential. So what really happened? When they were not in contact before junction, this was the scenario. Again, yaar, this EC is near to, like this EC and this EC is same only, right? Both are same. This EV and this EV is also same because they are the same material. So I am using the same material. So EC, 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 EFN, EFN, this was the scenario. But what really happened? As they came into action, equilibrium will be maintained. Equilibrium will be maintained. That means current would be 0. That means this has to be close to each other. Both has to be close to each other. That means what really happened? This part came downward and this part came upward. So this was the scenario that we were getting. And sir, this was representing my QVBI. QVBI. Now look at the diagram carefully. Just let me know what is the value of this one. Let's just say here I am saying that my doping is ND1. Okay. And here I am saying that doping is ND2. And you know that ND1 is much more than ND2. So what will be this particular width? Sir, it would be KT ln ND1 by Ni. And what do you think, what will be this particular width? Sir, it would be KT ln ND2 by Ni. Now those who are smart enough, or those who are putting good amount of concentration, just let me know, can I write down QVBI equals to KT ln ND by Ni, ND1 by Ni minus KT ln ND2 by Ni. How did I write it down? Just let us say this guy is not moving, only this guy is moving. Okay, this is what I am saying. Now this EFN has to reach to this EFN plus. EFN has to reach to the level of EFN plus. So how much distance this EFN needs to travel? EFN needs to reach to EFN plus, right? EFN, I am saying that EFN plus is not moving, only EFN is moving. So EFN want to go to EFN plus. That means EFN should cover this much of distance. And what is this distance? So this distance is equal to KT ln ND by Ni. EFI would be at the same place. EFN wants to go to EFN plus. Then how much EFN need to walk? Equals to the built-in potential. Built-in potential multiplied with the charge. So built-in potential multiplied with Q. Or you can say, sir, this distance KT ln ND1 by Ni minus this distance, like already it is there at this particular point, it needs to go for, sir, KT ln ND1 by Ni minus KT ln ND2 by Ni. So that would be equals to QVBI. Is that clear? Without mathematics we are doing, with the mathematics we have already done. And there also I told you formula will be VT ln higher concentration. There we used to write down in terms of N plus and N. So higher concentration divided by lower concentration. Then I told you this will be your built-in potential. But now with respect to energy band diagram as well, we are understanding what we are doing. This guy will actually come downward and this guy will actually come upward. So from here it will be tough to understand, but what I am saying, let's just say this guy remains as it is, but this guy goes upward. So how much distance it needs to walk? How much distance this needs to walk? So this needs to walk for KT ln ND1 by Ni minus KT ln ND2 by Ni. So your QVBI would come out to be KT ln, you can see that, sir, this is ln A minus ln B, so that would be ln A by B. So sir, simply it would come out to be ND1 divided by ND2. And sir, I can take this Q downward. So this will be the scenario I will be getting. So this is my built-in potential. Higher concentration divided by lower concentration. What is Q, KT by Q? That would be equal to VT at the room's temperature, right? What is KT by Q? KT by Q is VT only, right? VT is equal to KT by Q. And what is the value of VT? Sir, 26 millivolt at room's temperature at 300 Kelvin, right? All these things you already know, right? So V built in equals to VT K ln ND1 by ND2. Higher concentration divided by lower concentration. Okay, so by the energy band diagram, we have understood the mathematics as well, right? So let's solve the question. This has been asked in GATE examination only. N plus and N silicon device is fabricated with uniform non-degenerate doping concentration ND1, ND2 is given considering N plus and N region respectively. At the temperature T, assume complete impurity ionization. What is the meaning of complete impurity ionization? That means I am doping 10 to the power 18, all are becoming electrons. I am doping 10 to the power 15, all are becoming electrons as well, right? So this is the meaning of uniform doping. Value of Ni is given, you need to find out the built-in potential. So those who did not study in a good manner, what they would do? They would apply the concept of PN junction. In PN junction, the same formula would come out to be KT ln NAND by Ni square. Okay. So they would multiply both of them divided by Ni square, they would mess it up. But forget about all these things. I know that what kind of junction I am making, N plus N. Higher concentration divided by lower concentration. N plus N. There is no P, right? So what will be my built-in potential? That would be KT ln higher concentration divided by lower concentration. So they have given the value of VT, that is 25 millivolt ln 10 to the power 3. You will get the answer. Okay. Similar kind of question was asked for P plus and PA junction as well. So whatever that we have studied for N plus, right? Whatever that we studied for N type silicon. We can study it for N type, we can study it for P type semiconductor as well. So now this is the question that is coming on P type semiconductor. So what do you think, what will be the answer? Answer would remain the same only, no? Vt ln higher concentration divided by the lower concentration. So in 2017 it came for N type, then in 2018 it came for P type. So higher concentration divided by the lower concentration. Just make sure that this is also concentration of P and this is also concentration of P. Okay, just make sure this is the concentration of P and this is also a concentration of hole. Let's just say here they would have given 10 to the power 3 concentration of electrons they have given. They could have mentioned that I am having concentration of electrons, but here whole concentration divided by whole concentration, whole concentration divided by whole concentration, electron concentration divided by electron concentration, electron concentration divided by electron concentration. So always the same concentration I need to divide, right? So Vt ln 10 to the power 2. So 25 only let's take. So that will be the answer you will be getting. Okay, so you can get the answer. I will simply pause the video and then we will start PN junction. Now PN junction will simply be a cakewalk for you. All the formula, everything you will derive, built-in potential you can calculate and you will get your answer. So 25 millivolt ln 10 to the power 3, 25 millivolt ln 10 to the power 2. Both has been asked in gate examination only. Okay, so they are gate question only. So I hope you have understood the whole scenario of a non-uniformly doped semiconductor. So the first half of this video was completely dedicated to non-uniform semiconductors. Sir, why you spent so much of time? I hope now you guys are able to appreciate why I spent so much of time. As of now, we are not able to appreciate. Then when we study PN junction, at that time you would be able to appreciate that, sir, why you spent so much of time. Now PN junction would be completely a cakewalk. Along with that, I wanted to make you understand that, sir, why we are studying PN junction suddenly. Previously P-type semiconductor, then N-type semiconductor, then sir non-uniformly doped P-type semiconductor, sir non-uniform doped N-type semiconductor. We studied so much of physics. Suddenly, sir, why do we want to make PN junction? Because I want to be controlling. Okay, I want to control the current. Control the current I could have done with respect to doping, but I don't want that. What I want to control with respect to the applied input, my current should change. So I know that in one condition it is coming drift dominant, in other condition it is coming diffusion dominant. Don't mug it up. Okay, nothing you need to mug up here. I hope you will not be doing that, sir. If I am applying the electric field in this direction, then it would be diffusion dominant. No. Don't remember anything. If I want you to remember anything, that means that will be written in conclusion. But as of now, we are not writing down any conclusion. That means you don't need to remember anything. You need to have the tendency to analyze. Also, when we studied in basic semiconductor physics, we studied this kind of diagram, which kind of diagram, this kind of diagram, but they were not completely correct. The actual scenario would be this. As of now, in this particular scenario, we did not talk much about electric field. But now what we would see, we will be talking about electric field as well in PN junction. So in PN junction, we will talk about electric field as well. Okay, and that would make you realize that maximum electric field will be happening at the junction only. Intuitively as well, you can say why maximum electric field will be at the junction. Because at the junction, these electrons will feel the maximum concentration gradient. These holes will feel the maximum concentration gradient. And if you are feeling maximum concentration gradient, that means maximum electric field would be set up at the junction only, right? Okay. So all these scenario we are going to discuss. So in this video, we will understand PN junction under equilibrium only. We are not going to apply any bias. Okay. Although for N plus and N, we have given the bias as well. But in this particular video, we will not apply any bias. PN junction would be under equilibrium. From next video onwards, we will start applying some bias. Okay. So let me take a break and drink some water. You should also drink some water and revise everything that we have studied. You can get the answer of these guys, whatever it is. You can get the answer and revise everything. Just important part was this one, that I am able to increase the drift current here. I am able to increase the diffusion current here. Okay, then yeah, let's meet in the next lecture. Sorry, not in next lecture, in this lecture only, but we'll take some break and then we will come back. Yeah, hi everyone, welcome back. So now we are going to discuss about PN junction. Okay, so I was having a semiconductor which was doped with the acceptor atom. So I got a P-type semiconductor and then I got a N-type semiconductor as well. Now what I will do, I will join them. So once I join them together, then this kind of scenario I would be getting. What kind of scenario? This kind of scenario I would be getting. Okay. and wherever I have joined them, this particular part is known as junction. Okay, this part is known as junction. Look, actually what you are doing, you are not doing this particular thing that sir I am getting P and then N and then I am joining them. Here also this scenario was not happening, that you are getting some N plus and then you are getting N and then you are joining them. No, actually what do? Actually you would have a semiconductor. I am just telling the fabrication. You would be having a particular semiconductor. Okay, now I will put this semiconductor into two halves. Okay, I have equally divided this semiconductor. Let us say this semiconductor was silicon. So I was having a piece of silicon. I am calling this particular axis as at x equals to 0. This is my x equals to 0. So this particular part which is in the left hand side, this has been doped with acceptor atom, and this particular part is doped with donor atom. So this is what you are actually doing. Okay, you are taking one piece of silicon, one part with acceptor atom, one part with donor atom. Actually you are not joining them. There is no concept of joining. Like if you join them, you have to join by a wire, and when you join by a wire, another junction would be made here. Like if I join them by a wire, so between the semiconductor and wire there will be one junction, between this semiconductor and wire there will be another junction. So it will not behave in a manner that we want it to behave. So actually you don't join. What do? You take one semiconductor, one side doped with N type, one side doped with P type. Okay, so this is how you make a PN junction. So this particular part where they are joined, this part is known as junction. Okay, so first we will understand the physical meaning and then we will see with respect to energy band diagram as well. So now we are seeing the physical meaning. So what will happen? Sir, this is doped with the acceptor atom. That means here number of holes are more. Let's just say this silicon was having intrinsic carrier concentration of 10 to the power 10. 10 to the power 10. You did the doping of acceptor atom, that was 10 to the power 16. So number of holes will be 10 to the power 16 and number of electrons would be 10 to the power 4, right? Because you know that because of the mass action law, 10 to the power 16 into 10 to the power 4 would be equals to 10 to the power 10 into 10 to the power 10. So 10 to the power 20 divided by 10 to the power 16. So number of electrons will be 10 to the power 4. So here also you did the same thing. Here what you did? Here sir, number of electrons were 10 to the power 16 but number of holes were 10 to the power 4. So what do you see? Here sir, holes are 10 to the power 16 but this side holes are 10 to the power 4. That means there is a concentration gradient. 10 to the power 16 and 10 to the power 4. Sir, there is a concentration gradient and because of that what will happen? Holes will move from P side to N side because of the concentration gradient, because you are having more holes on P side and lesser holes on N side, and because of the concentration gradient holes are moving from P side to N side. So this hole is moving from P side to N side. Similarly sir, electrons will also move from N side to P side because of the concentration gradient, because at the N side you are having more electrons and at the P side you are having lesser electrons. So electrons will also move. Electrons will also move and these holes will also move. Holes will also move. Right? Now what you would see, these electron and holes are moving. So one hole and one electron. When they meet each other, what they would do? They would recombine with each other. Electron and hole will be recombining. There were two processes, generation and recombination. What is the meaning of generation? The electron and hole were generated. What is the meaning of recombination? They were killing each other. So now what will happen? Electron and hole will kill each other. And if they are killing each other, that means electron hole pair will be gone. So hole decided to move from P side to N side and electron decided to move from N side to P side. What they did? They cancelled out each other, and what really you are going to get? So whatever the hole that you are having here, this hole will be gone, and whatever the electron that you are having here, this electron would also be gone. This hole will be gone. This electron would also be gone. This hole will be gone. This electron would be gone. This hole will be gone. This electron would be gone. Similar thing can happen with these holes and these electrons as well. But who will have the more probability of getting eradicated? What I am saying, whatever that has happened with this hole and this electron, that could have happened with this hole and this electron as well. But who will have the more probability? Sir, these holes will move before these holes, because these holes will see the highest concentration gradient. All these concepts we have already studied in N plus and N junction. So first, this electron hole pair will be eradicated. This electron hole pair will be eradicated. Now in this particular region, electrons and holes are not present. Okay. So now what will happen? There will be a particular region where electron and holes are very, very less. There will be a particular region where electron and holes are very, very less, and this particular region is known as depletion region. So if I say this is my x equals to 0, so left hand side I will put by negative. So this I am calling as x equals to minus xp. Depletion region towards the p side, and this point I will call as x equals to x1. Depletion region towards the n side. Okay. So now there is a depletion region made, and in this depletion region there are no electron and holes. This is simply a positive charge, this is simply a negative charge. Positive charge, negative charge. And this positive and negative charge will not contribute in current. Who contributes in current? Sir, holes contribute in current, electrons contribute in current, but sir, this positive charge will never contribute in current. This negative charge will never contribute in current. Okay. So electron hole pairs are gone from here. So this particular region is depleted of charge carriers. That's why this region is known as depletion region. As of now, you don't need to write down anything. We will do the proper naming. Don't worry about the naming. But as of now, what did we understand? Holes from the p side are diffusing towards n side, and electrons from the n side are diffusing towards p side. Because of that, holes and electrons will get recombined and they will be killing each other. So what will happen is that we will get a particular region which is depleted of charge carriers. In this particular region, charge carriers are not present. Okay. And what you will get a positive charge here and negative charge here. This positive and negative charge will not contribute in the current because it is not having any carrier. Okay. So these are unmovable positive and negative charge. Unmovable. Holes can move, electron can move, but this cannot move. This cannot move. So unmovable positive and negative charge we are having. So these will not contribute any current. Now what do you see? Now because of this positive and negative charge, what we can see here, there will be a built-in electric field that will be built up here. There will be a built-in electric field that will be built up here, right, from positive to negative. Now again this hole will say, sir, I am seeing concentration gradient. Here there are more number of holes, sir, here there are lesser number of holes. What I would do? Sir, I will move. So hole said that, sir, I will move. But what this built-in electric field will say? You want to move in this direction? Go back. Because previously what really happened, hole moved here and electron moved here, right? Because of the holes were moving here, electrons were moving here. Because of both of them, we were getting some diffusion current. Because if electrons are moving here, then the direction of current would be this one. And if holes are moving here, then the direction of current would be this one. So because of them, we were getting some diffusion current. Now, hole wanted to move here. Hole wanted to move towards this side. But what this electric field will do? Electric field will push them backward. So here they were diffusing, right? Holes were diffusing. Electrons were diffusing. Now, because of this electric field, what will happen? Holes will drift. What is the direction of electric field? This is the direction of electric field. And holes will drift in the direction of electric field. So what will happen now? Holes will drift in the opposite direction. Holes will drift in this direction. And now what about the electron? Sir, electron always drifts in the opposite direction to the electric field. So this is my electron, and direction of electric field is this one. So where the electron will drift? In this direction, electron will drift. So electron will drift in this direction. So holes are drifting in this direction, electron is drifting in this direction. So what do you think? What will be the direction of current? The direction of drift current would be this one. This is the direction of drift current. And at the equilibrium, drift and diffusion will cancel out each other, and eventually your current would be 0. Whatever the scenario that was happening in N plus, and the same scenario is happening in Pn as well. Nothing new we are learning. Holes started to diffuse from P side to N side. Electrons started to diffuse from N side to P side. Both were killing each other. Because of that, we got a built-in electric field. Now this electric field, what it would make? It would make the holes drift in the opposite direction. First they were diffusing from 0 to positive direction. Now they will drift from 0 to negative direction. So diffusion and drift both are in the opposite direction. That means their current will also be opposite. They will cancel out each other, and eventually the total current would be 0 under equilibrium. So this is the physical meaning we have understood. Let's understand the same scenario with energy band diagram as well. So we can understand the same scenario with energy band diagram. So when they were separate, P were separate, N were separate. So what kind of energy band diagram you are getting? Sir, EC, EV, since it is P type, so our Fermi level will be nearer to valence band. Sir, since it is N type, our Fermi level will be nearer to conduction band. Now I know that, sir, when I join them together, there cannot be any current because there is no external bias applied. There is no external energy source, so there cannot be any current. What does that mean? That means, sir, this guy and this guy would become flatter, right? That means this particular energy band diagram, has to come downward, and this particular energy band diagram has to go upward. Is that clear to you? Right? So when I join them together, there is no external bias applied. That means the current has to be 0. That means my Fermi level has to be flat. If I want my Fermi level to be flat, then this guy needs to go upward and this guy needs to come downward. That means this EC will come downward and this EC would go upward. So what kind of scenario we would be getting? So somewhat this kind of scenario I would see. So one EC has gone upward, other EC has come downward. Same goes for EV as well. EFI is not important, so I am not making it. But sir, my Fermi level has become flat. Fermi level has become flat. Right? Now the electric field will be uniform. What I am asking, will the electric field be uniform? Can I join it like this? No, because I told you electric field will be maximum at the junction. At the junction only maximum electric field would be there. So you cannot actually make it like this. Okay, you have to show some slope. You have to show some slope. Okay, and by this diagram as well, you can see that in the direction of electric field, what do we know? So electric field is proportional to dEC by dx, or dEV by dx, you can say. In the direction of electric field, the slope of EC has to be positive. So in this direction, slope of EC has to be positive, and you can sense that, so this is your built-in electric field. And what do you think what this would represent? So this would represent QVBI. Because what is the region of movement? What is the region why they are moving? Region means this is region I am saying. What is the actual reason why this particular EFN and EFP are moving? Because of this built-in potential, you can say. So because of this built-in potential, this EFN and EFP are moving. That's why this gap has come into action. Or you can say this gap will also be the same. This gap will also be QVBI only. Is that clear? And then there is a built-in electric field. Now you can see, either we can sense with the now I need to analyze this particular energy band diagram. So I can analyze it with respect to electrons, or I can analyze it with respect to holes. So I will analyze it with respect to electrons. So towards this side, there are lesser electrons, right? There are, let's just say, only 2 electrons. And towards this side, there are more electrons. Is that clear to you? And side, there are more electrons. This is the diagram that has been made with respect to X only. I hope that you understand. Energy versus X. So on this side, there are more electrons. And this side, there are lesser electrons. Now, what is the motivation of going upward? The motivation of going upward is diffusion. What is the motivation of going downward? Motivation of going downward is drift. So electrons will be drifting in this direction and electrons will be diffusing in this direction. Are we correct? Electrons are diffusing in this direction. So yes, electrons are diffusing in this direction. Electrons will be drifting in this direction. Electrons are drifting in this direction. And the number of electrons which are drifting and the number of electrons which are diffusing, both are equal to each other. And that's why the total current is 0. So this much barrier is good enough to make drift and diffusion equal to each other. If I reduce this barrier or if I increase this barrier, then I will be able to control my drift and diffusion currents. And based on that, I will be getting some current. And from here, the concept of forward bias and reverse bias would come into action. In forward bias, what I will do, I will reduce the barrier. And in reverse bias, what I would do, I would increase the barrier. So if I have increased the barrier, then what will happen? So drifting would become easier, but diffusion would become difficult. Do you remember this thing? When we compared here. So when you increase the barrier, then what really happened? This was drift dominant. That means if I have increased the barrier, then diffusion became difficult. But here diffusion became easier. Here diffusion and drift were equal. If I increase the barrier, then what really happened? The diffusion became difficult, but drift became easier. So this was drift dominant. So here what really happened? Sir, when I decreased the barrier, then what really happened? So diffusion became easy, but drift became difficult. Right? So based on that, the concept of forward bias and reverse bias would come into action. That we will check. Okay. As of now, we are only considering the equilibrium condition. So equilibrium, I am able to explain with respect to physical meaning as well. Physical meaning you understood, right? Physical meaning you have understood, and you have understood the energy band diagrams as well. So let me repeat what we studied. Electron try to diffuse, holes try to diffuse, electron try to diffuse, both cancelled out each other. Positive charge, negative charge you are getting, they are not movable, they will not contribute in current, they will bring a built-in electric field. Now this built-in electric field will put the force on holes in the same direction. That means holes will be drifting in this direction from right to left, and electrons will be drifting in the direction of left to right. Previously they were diffusing from left to right, and drift has been done from right to left. So what really happened? They are cancelling out each other and total current is zero. With respect to energy band diagram, sir, I know that in equilibrium the current has to be zero. That means EFP goes upward, EFN goes downward. That means I will get a particular slope in this manner, right? Now one doubt may come up. What kind of doubt may come up? Sir, you said that in this depletion region there will not be any charge carrier. Sir, you said that in this depletion region there will not be any charge carrier. What does that mean? That means there should not be any electron or hole. Now I know one thing. What does this gap represent? What does this gap represent? So this gap is saying that there are number of electrons, there are number of holes are very more, because if EF and EV are having lesser gap, that means number of holes are good enough. Here also there is a certain gap, no? Like the gap is not infinity, right? Gap is not infinity. What does that mean? That means surely some electron and holes are present here. Like this gap is not infinity, no? What does this gap represent? Do you remember the equation n equals to nc e to the power minus ec minus ef by kt? Although if you don't remember this equation, then also it is fine. But you know that if the gap between EV and EF is less, what does that mean? It is representing that more holes are there than electrons. And if the gap between EC and EF is less, that means it is saying that there are more electrons. So the gap is representing either holes or electrons. When I come to depletion region, this is my depletion region, no? What is my depletion region? When I made this diagram, sir, this is my depletion region. This is x equals to minus xp and this is x equals to xn. So in the depletion region, what I am noticing? At minus xp and xn. Sir, you said that electron and hole will recombine and they will kill each other. So that means there should not be any electron and hole. But what do I see? There is a certain gap. There is a certain gap. That means electron and holes are present. So surely they are present. So I will do a separate discussion regarding the depletion region. But in our assumption, what we will assume? That in the depletion region is completely depleted of charge carrier. That means there are no charge carriers present. But actually some charge carriers are present. But they are much lesser than this particular region. They are much lesser than this particular region. So complete discussion I will do, a very, very good discussion it is. But as of now, what you need to understand, that in the depletion region there is no charge carriers present. But actually charge carriers are present in the depletion region. The statement saying that in the depletion region there are no charge carriers present, that statement is wrong. Because with respect to the energy band diagram also you can see that if there is a certain gap, that means there are certain number of holes present. There are certain number of electrons also present. So in the depletion region there are electron and holes present, but that number would be very lesser than what we expect. And I will do the complete discussion. Just have some patience. After 10 to 15 minutes that discussion would start. Okay. So as of now we have understood the scenario. We have understood the meaning of our PN junction. So now what I will do? I will derive the formula of built-in potential. What is the matter of concern for us? Built-in potential. Along with that I have written down the theory as well. So you would be able to understand the theory. Just read line by line. When a p-type and n-type semiconductor are joined together, a PN junction is framed. Initially, holes from the p side will diffuse towards the n side and electrons from the n side will diffuse towards the p side due to the concentration difference. As they cross the junction, they recombine with each other, leaving behind immobile. Immobile means not movable. Okay, immobile. What is the meaning of immobile? Not movable. Not movable. Not movable means this positive and this negative. They are not movable, right? They are not movable. This negative, this positive, they are not movable. So immobile charged ions near the junction. These uncovered ions from that depletion region, which is depleted of mobile charge carriers. Again, there is something missing here. Depleted of mobile charge carriers. What is the meaning of mobile charge carriers? Electron and holes. What is the meaning of mobile charge? Electron and holes. So electron and holes are not present. Positive ion, negative ion is present, but this electron and this hole is gone. This electron hole is gone, right? Now this region now contains a fixed negative acceptor ion on the p side, fixed negative acceptor ion on the p side, and fixed positive fixed positive donor ion on n side, and fixed positive donor ion on the n side. This charge separation creates an electric field directed from n side to p side, directed from n side to p side. This field opposes further diffusion of carriers. As the diffusion current increases, the electric field produces an opposite drift current, and at the equilibrium the diffusion current is equals to the diffusion current, and resulting in zero net current across the junction. The potential difference that has been developed, that is known as built-in potential. Okay. Thus, under equilibrium, the PN junction maintain balance of diffusion and drift, and no current flows. Okay. So our matter of concern is now the expression of this built-in potential. So what do you think? What should be the expression of built-in potential? Have some patience and derive it on your own. What should be the expression of this built-in potential? Let us say I hold on to this one and I say that only this guy is going upward. What I am saying? I know that this guy will move downward and this guy will move upward. But what I am saying, this guy stays at its own place, but this guy will move upward now. So what do you think, how much distance this EFP needs to travel to reach to EFN? What will be the target? EFP would want to reach till EFN, right? So this EFP needs to travel this much distance plus this much distance. So total distance is need to travel is this much and this much. So can I write down my QVBI KT ln, what is this distance? KT ln Na by Ni. I hope you remember the formula from basic semiconductor physics. Plus it needs to work for KT ln Nd plus Ni. Sorry, not Nd plus Ni, Nd by Ni. Is that clear to you? I hope without any mathematics you are able to understand these kind of things. This could have been derived with respect to mathematics as well, and you would see everywhere at most of the places they will derive it with mathematics, but we are going with the energy band diagram. What we are doing? Sir, I know that EFN would also move, EFP would also move, but what we are considering, EFN stays as it is, EFP is moving. That means this gap plus this gap, this much they need to move so that EFP and EFN becomes at one place only. So KT ln Na by Ni plus KT ln Nd by Ni. What you are getting? KT ln Na Nd by Ni square. Divided by Q. So this is the formula that you are getting, or what you can remember, sir, VBI is coming out to be VT ln Na Nd by Ni square. What could be the other way of writing down this formula? You will remember this one, okay? But what could be the other way? KT ln Na I am keeping as it is. What is this? Nd by Ni square. This is your Na divided by Nd divided by Ni square, and this Nd comes downward. Ni square by Nd. What this Ni square by Nd is representing? Ni square by Nd is nothing but the holes concentration in N side. What is this Na? Na is electron concentration, sorry, Na is hole concentration on P side. And what is this? This is your hole concentration. This is your hole concentration in P side, and this is your hole concentration in N side. Do you agree to this point? Formula is Na Nd upon Ni square. Na looking upward, downward what I am getting? Ni square by Nd. What is Ni square by Nd? Ni square by Nd is hole concentration in N side. This is your electron concentration in N side. This is your hole concentration in P side, and this is your electron concentration in P side. And everything is under equilibrium, so I can put a note here because all these things are under equilibrium. So what this Na is there? Can I represent Na as hole concentration at P side under equilibrium divided by, what is Ni square by Nd? Ni square by Nd is nothing but hole concentration in N side under equilibrium. And I told you higher concentration divided by lower concentration. What formula we get? Higher concentration divided by lower concentration. This was also for holes. This was also for holes only, right? This was for electrons. So this was also for electrons only. So higher concentration divided by lower concentration. So when I am writing down this formula, higher concentration divided by lower concentration. Same thing I could have done with the other thing as well. What I could have done? VBI is equals to KT I am keeping Nd as it is. So what is Nd? Nd is electron concentration of N side. What is Ni square by Na? Ni square by Na is electron concentration of P side. There you go. So built-in potential formula is same for everyone. It is not different for PN junction or any other junction. If any kind of junction is made, formula is KT by Q. Okay, KT by Q. Formula is Vt, or in place of KT by Q, simply write down Vt. Formula is some Vt ln higher concentration divided by lower concentration. Just make sure that if you are writing down whole concentration here, here also you will write down whole concentration. If you are writing down electron concentration here, in that denominator as well, you will write down electron concentration only. So whole concentration divided by whole concentration, electron concentration divided by electron concentration. Take the ln, multiply with Vt. So better remember this formula, because most of the chances are there that they will give the value of Na, Nd and Ni. If they are giving whole concentration only, then you can apply this formula. If they are giving electron concentration only, then you can apply this particular formula. Is that clear? So concept of built-in potential is clear. Okay, everything is clear. So what we need to do, we need to discuss about this depletion region. We will do that, but first let's do the naming. So what these things are known as? So this is my x equals to 0. Okay, this is your x equals to 0. This I call as x equals to minus xp, and this I call as x equals to xn. This whole region is known as depletion region. What it is known as? Depletion region. Just let me know one thing. This whole semiconductor, this is one semiconductor only, no? Like initially I was having a silicon, then I did the doping of p side, then I did the doping of n side. So there is one semiconductor. So I can call it one semiconductor. This whole semiconductor is electrically neutral or not? Yes, it is electrically neutral. Sir, negative hole, negative hole. So then negative charge, positive charge, 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 negative charge, positive charge. So negative charge, positive charge, negative charge, positive charge, negative charge, positive charge, negative charge, positive charge. Positive, negative, positive, negative, positive, negative. So positive charge is equals to negative charge. That means this whole semiconductor is electrically neutral. This whole semiconductor is electrically neutral. For sure. There is no doubt about that. Right? But can I call this particular region as Can I call this particular region as depletion region? I will write downward. Okay, between minus xp to xn, I am calling this as depletion region. Can I call this region as neutral p region? Why I am calling it neutral p region? Because this particular side, that would be negatively charged. But although negative charge is balanced by positive charge, so total charge is 0. But what I will call this as? Depletion region on or better, let's not write down here. I will simply write down here only. So this particular thing I will call as depletion region on p side. Sir, what is the meaning of adding neutral word here? Why it is known as neutral p region? Because this particular part is neutral, this particular part is negatively charged. Now this particular part is positively charged. This negative charge and positive charge will cancel out each other. So can I call this part as depletion region on, only the naming, nothing else, okay? Depletion region on n side. Say yes or no. So what I will call this part as? Neutral n region. Right? So I can keep this particular thing here now. So middle part is known as depletion region. So depletion region, neutral p region, neutral n region. This particular part is depletion region on p side. This particular part is depletion region on n side. What is this? Like this line. What this line is known as? This line is known as junction. what this is known as? Edge of depletion. Okay, edge of depletion region on P side. What this is known as? Edge of depletion region on N side. So just the naming, like when I am explaining a particular concept, I will say at the junction. So what should click to you? Okay, this is the junction. If I say neutral P side, what should click to you? This side should click to you. Neutral N side, this side should click to you. Depletion region on N side, this should click to you. Depletion region on P side, this should click to you. So just the naming, nothing else. Okay. Now, if I say something called depletion width, so can I call this particular width as depletion width? Depletion width, W. What would be your depletion width? Depletion width would simply be, sir, Xn plus Xp. Let's just say value of Xn was 3 micrometer and value of Xp was minus 2 micrometer. So here what I would have written? Here what I would have written? Minus 2, and here what I would have written? 3. So what will be the complete width? 5 only, no? From minus 2 to 3 you are going. So junction I am assuming at x equals to 0. This is my junction, right? Xn value I am taking as 3, Xp value I am taking as 2, not minus 2. Xp value is 2. So this x would become minus 2, this x would become 3. So depletion width would be Xn plus Xp. Is that clear? Very simple thing, very straightforward, right? Depletion width would be Xn Xp. What do you think what your Xn would be known as? Xn would be known as depletion width on N side, right? And what do you think what your Xp would be known as? Xp would be known as depletion width on P side. And both added would become total depletion width. Total depletion width. That would be W, which would be equals to Xn plus Xp. So naming is clear. Let me repeat the naming again. Neutral N side, neutral P side, depletion region of N side, depletion region of P side, junction, total depletion width, edge of depletion on P side, edge of depletion on N side, depletion width of P side, depletion width of N side. Naming is clear to you. So whenever I explain a particular concept, I will take these names and you will not be getting confused, right? So till this point in PN junction, what we have studied, we saw the physical meaning, we saw the energy band diagram, and from there we derived the formula of built-in potential. Only one formula you need to remember, and with respect to that particular formula, you will be able to derive other formulas as well. What is that formula? Sir, Vt ln Na Nd by Ni square. Okay, Vt ln Na Nd by Ni square. Is that clear to you? So this kind of a built-in potential you have understood. Now let's do a discussion on depletion region, because what a lot of people think is that depletion region is completely depleted of charge carriers, but this is not the actual reality. So let's do some discussion on depletion region. Okay. So this was a diagram I was getting under equilibrium, and here I explained that, sir, if there is a certain gap, that means there has to be some certain number of electrons present, there has to be some certain number of holes present. So if there is a certain gap, that means a certain number of electron and holes are present here. Okay. How do you explain it? Do you remember something called mass action law? N into P equals to Ni square. What did I say? When your semiconductor is under equilibrium, then mass action law will be valid. At what point this mass action law was not valid? Do you remember? When this mass action law was not valid? Sir, when you had a semiconductor and you are throwing some light. So some external energy you are providing. When you provided some external energy, sir, what really happened? Some delta P and delta N was created. So your P became actually P plus delta P, and your N became actually N plus delta N. So that's why P into N was not equal to Ni square. But sir, when it was under equilibrium, there was no issue. Always N into P equals to Ni square will be valid. Now what is this PN junction? PN junction is nothing but a semiconductor only, no? One side doping you did P, one side you doping you did N. Some junction was made, some electric field was built up, whatever the process happened, eventually it is under equilibrium only, no? Eventually it is under equilibrium only. And if it is under equilibrium, it has to follow mass action law. And that I will prove with mathematics as well. Don't worry, mathematics also we will do. But it has to follow mass action law. So on this particular semiconductor, everywhere mass action law will be valid, no? Like sir, here n into p equals to ni square, here also n into p equals to ni square. Sir, inside the depletion region as well, n into p equals to ni square should also be valid. Say yes or no. Are you able to understand this point? What I am saying? Mass action law has to be valid under equilibrium, no matter what kind of a semiconductor you are having. But there should not be any external bias. If I am not giving any external energy, that means mass action law has to be valid. So here as well, mass action law has to be valid, right? So number of electrons multiplied with number of holes should be equals to ni square. And if I am saying that 0 electrons are there, 0 holes are there, is it equals to ni square? Let's just say ni is 10 to the power 10. So is it equals to 10 to the power 20? No. That means something wrong I am doing here. What does that mean? That means electron and holes are actually present here. Surely they are present. Okay. But what is the problem? The problem is that these electron and holes are much lesser than these electron and hole concentration. What I mean to say is that, sir, this is your p side. Sir, this is my neutral p side. Sir, this is my depletion p side. But on hole, this is my p side, no? And on hole, this is my n side. So in this p side, what you are expecting? That I am expecting holes. And here what I am expecting? I am expecting electrons. Let's go to our energy band diagram. So what you can see? So what you can see? Sir, here the gap between EF and EV is very less. That means here a lot of holes are there. But as I move into the depletion region, let's just say I am at this point. At this particular point, what is the scenario? Sir, this gap has increased. So the gap between EF and EV is, let's just say here it is alpha. So now, sir, it has increased to alpha plus 0.1. Right? So here if you are having, let's just say 10 to the power 16 holes. Here if I was having 10 to the power 16 holes. So in this particular region, sir, I will be having 10 to the power 14 holes only. Now, do you really think that 10 to the power 16 and 10 to the power 14 is comparable to each other? This is 100 times of this one. 100 times. Now, if I say you are having 10 to the power 14 holes, someone will say a lot of holes are there. But we need to compare, no? We are on the p side only. One side of p side is having 10 to the power 16 holes. Other side is having 10 to the power 14. 10 to the power 14 alone is a very high number. But when you compare 10 to the power 14 with 10 to the power 16, this number is very lesser, no? It is the 100 times of this number. Let's just say some guy is getting 1 mark and you are getting 100 marks. Will you say both are same? Like both did the same amount of hard work. Both are having the same brain. Will you say that? No. Because you are getting 100 times more marks than this guy. Not 100 times more. You are getting 100th part of this particular guy. Right? So when you compare 10 to the power 16 with 10 to the power 14, 10 to the power 14 is much lesser than 10 to the power 16. So eventually there are holes present, but the number of holes are much lesser than what number of holes you are getting here. Are you able to understand this point or not? Okay. Now let's see another point. We are currently on the p side only. So in p side, someone will say that, sir, this gap is higher. This gap is higher. And sir, here at this point, this gap is lower. Let's just say, sir, this gap was beta. So now, sir, this gap is beta minus 0.1 beta, right? Now someone will say, sir, this gap is representing the number of electrons. This gap is representing number of electrons. The gap between EC and EF would represent the number of electrons. The gap between EF and EV would represent the number of holes. This gap is very much more. What does that mean? That means, let's just say here I am having 10 to the power 4 electrons. So just let me know at this particular point, how many electrons you would be having? More than 10 to the power 4 or less than 10 to the power 4? So surely more than 10 to the power 4, because sir, this gap has reduced. Are you able to understand this point? What I am saying, at this particular point, if I am having 10 to the power 4 electrons, then in this region I am having 10 to the power 4 electrons? No, I would be having more than 10 to the power 4 electrons. That would be 10 to the power 6 electrons. So what did you see here? From the neutral p region, in the depletion p region, you are getting more number of electrons. But this 10 to the power 6, 10 to the power 4 is nowhere compared to 10 to the power 16. In this particular p region, what you are looking for? You are looking for holes. In the neutral p region, what did you see? That, sir, I am having 10 to the power 16 holes. When I moved ahead, when I reached to this point, sir, I got to know that my holes are 10 to the power 14. But sir, at this particular point, I get to know that my electrons are 10 to the power 6. So you are saying that, sir, I am having 10 to the power 6 electron and 10 to the power 14 holes. Both of them are nothing compared to 10 to the power 16 holes. So who is the majority? Majority is the hole which is 10 to the power 16 only. So even though the concentration of electron has increased here, what I am saying, even though concentration of electron has increased here, but this concentration as well is nothing compared to the concentration of holes. So that's why we say that depletion region is depleted of charge carriers, but actually it is not depleted of charge carrier. If I say one statement in the examination, the question is given, which of the following statement is true? The statement would be written, in neutral p region, the number of electrons, what I am saying, in neutral p region, the number of electrons is lesser than that depletion p region. Is this statement correct? Someone will say, in neutral region, less electrons, less charge carriers. This statement is wrong, but it is actually correct. Why it is correct? Because actually the concentration of electron is increasing. From the Venn diagram, we can see that the concentration of electron in depletion region, in depletion p region, that is actually increasing only. But the increase is not significant. And sir, why it is increasing? Sir, why the concentration is increasing here? Because we need to follow the mass action law. Here we were following the mass action law. This point was minus xp and this point was xn, right? So for x less than minus xp, what was the scenario? So number of holes were 10 to the power 16 and sir, number of electrons were 10 to the power 4. Now let's say this point is what should I give? So this point is minus xp plus delta x. Okay, this particular point is minus xp plus delta x. So this distance is delta x only. So at x equals to minus xp plus delta x, what is the scenario? Sir, number of holes got decreased, that is 10 to the power 14. So what will be the number of electrons? That has to be 10 to the power 6. So this has to increase. If this is decreasing, this has to increase because mass action law has to be valid. So surely in the depletion region, you are getting more electrons than the neutral p region. In the depletion p region, you are getting more electrons than the neutral p region, but still these electrons or anything is not comparable with the 10 to the power 16. You are in the p region, you are looking for holes. So these are the majority holes. So towards the p side, I only care about the holes and I see that the holes are much lesser than what I get in the neutral side. Although in the depletion region number of electrons are increasing, I don't care about that. Why so? Even if they are increasing, they are not increasing in significant amount. From 10 to the power 4, you have got 10 to the power 6, doesn't matter. From 10 to the power 4, if you have got 10 to the power 16, then somewhere you are comparable. Are you able to understand this point? A very good interview question it would be. Like a lot of people would be saying that, yes sir, I know. Like in some other videos as well, you will find out that, sir, in depletion region, there are charge carrier present. But what is the region? What is the explanation? How would you explain? How would you explain with respect to this Venn diagram? Is that everything clear to you? Although this particular question is not important for your GATE examination, in GATE examination, what kind of question could be coming? That I will frame in my test series. In our test series, you would find this statement. Which of the following statements are true? First one, in depletion p region, the number of electrons would be more than the neutral p region. Statement is correct. But a lot of people would mark that statement wrong. Why so? Because they would think that depletion region means depleted of charge carrier. That means there will be no electron, there will be no holes. So how electrons could be more than the neutral p region? It could be more. Surely it would be more. Why is that so? Because it has to follow mass action law. Okay. So in the gate examination, statement wise question can come up. So whenever you think that sir is teaching too much of theory, but in the gate examination numerical would come up, why sir is teaching so much of theory? So the theory can be asked as true or false statement. Which of the following statement are true? So that's why in EDC theory becomes very important. In analog, I teach zero theory, right? Because in analog, never ever they would ask theory. They will ask circuit analysis. In digital, I teach zero theory. In communication, I teach zero theory. In control system, in signal system, nearly zero theory we teach. But only in EDC, I focus on the theory as well. And surely I will focus on the numerical part as well. Why I focus on theory? Because in EDC, the question would come up, which of the following statement is true? So there, the theory part would play a very, very important role. Is that clear to you? So if I make concentration versus explode, what I am making? Now the same scenario that I explained here, the same scenario could be understood from the N side as well. You see this gap? So this gap is lower, but when I go ahead, the gap is increasing. That means number of electrons are reducing, but number of holes will increase. So what I am doing, I am making carrier concentration versus explode, but I am making it on log scale. Okay, this has been framed on log scale. Sir, you said that, sir, from 10 to the power 16, your electron concentration, just as you walk for some distance, hole concentration became 10 to the power 14. Sir, why this much of drop? Because the relation is exponential. P equals to Na e to the power minus here, EF would come ahead, right? This is the relation. So if EF minus EV has increased, then drastically, exponentially, it will decay down. Are you able to understand this point? The relation is exponential. E to the power minus 1 and e to the power minus 2. Very large difference is there. Or e to the power minus 3. Right? E to the power minus 3 is nothing compared to e to the power minus 1. E to the power minus 3 is nearly 0. But e to the power minus 1 is decent enough number. Right? Are you able to understand this point? Relation is exponential, no? So if you walk only a minute distance, then drastic drop would be there. So here more holes, suddenly you would see very lesser holes. So drop would be drastic, and now I am plotting it on log scale. So ln scale you can say. So in ln scale it would look linear. Basically the graph would look something like this. Sir, that sir, on this side, this much holes I was having. And sir, on this side, this much electrons I was having. As I move ahead, the concentration of holes will go down. Or better, I should write down here. What I should write down? Number of holes on P side under equilibrium. That is equals to Na. And here I should write down the number of electrons on N side under equilibrium. That was Nd. And again, under equilibrium condition only I am making. So under equilibrium, number of holes in N side under equilibrium. So that was equals to Ni square by Nd. And sir, here as well, number of electrons on P side under equilibrium. So that was Ni square by Na. Now sir, what will happen in the depletion region? In the depletion region, sir, what will happen is that the hole concentration will decrease and electron concentration will rise up. Now if someone who is looking at this graph, what he will think? Sir, here whatever the number of electrons are there, and here whatever the number of holes are there, and here whatever the number of holes are there, they are comparable. But you are actually drawing on log scale. What you are doing? You are actually making it on log scale. So let's just say this number was 10 to the power 16. So on log scale, that number would become 16 only. And this number was 10 to the power 14. So on log scale, this number would become 14 only. So 16 and 14 are comparable. But 10 to the power 16 and 10 to the power 14 are not comparable. So on the graph, it may look like that, sir, this concentration and this concentration, not much difference. But actually, there is very different. Actually, there is a very high difference. So when I was a student, I used to look at this graph, and I always used to think, not much difference is there. If not much difference is there, then how we can say that a depletion region is depleted of charge carriers? Actually, it is log scale. So on log scale, the difference is not visible. But in actual, it is 10 to the power 16 and 10 to the power 14. So on log scale, it is looking like 16 and 14. But actually, it is 10 to the power 16 and 10 to the power 14. So there is a very high difference. Is that clear to you? Okay. So you can verify from this diagram as well that as I am going into the depletion region, till the junction, what I would see that, sir, this gap is reducing. That means the number of electrons are increasing here. Number of electrons are increasing here. And sir, this gap is going forward. Like this gap is increasing. What does that mean? That means, sir, the number of holes are decreasing. So number of holes are decreasing. And when I reach here, the number of holes will be very less and number of electrons will be very high. So how this diagram came into action, is that clear to you? Okay. And I'm pretty hopeful that one day they will frame a question from this particular topic. And they would frame only one question: which of the following statement is true? In the depletion region, I say this particular statement: in the depletion region, the number of holes in depletion n type, the number of holes in depletion n type would be more than the neutral n type. Neutral n type. Number of holes. Is this statement true? What people will think, sir, in depletion region there are no charge carriers, so how it could be more? Statement is wrong, but actually it is correct. Right? Actually it is correct. The concentration of holes, what this particular line is showing? This particular line is showing the concentration of holes, and this particular line is showing the concentration of electron. So concentration of holes is more than the neutral n region. So here this is the concentration and here this is the concentration. This is your neutral n region and this is your depletion n region. So in depletion n region, the concentration of hole is more than the concentration of electron. So what do you see? This line is showing holes, right? This particular line is showing for holes, and this particular line is showing electron. This what I should have done is that I should have used one color of pen for electrons and one color of pen for holes, right? So let's make it a bit better. I will make this diagram a bit better. How would I make it better? I would make it better in this manner. This is for red color I am using for electrons, okay, and this brown color I am using for holes. Red for electrons and brown for holes. So now this diagram would be more clear to you. Okay, I hope this particular diagram is clear. Holes, this is holes, this is also holes. So this is completely showing the number of holes, and you can see that here the number of holes is decreased from this particular side, and here the number of electrons has increased from this particular side. So in the neutral p region, the number of electrons are less than the depletion p region, and in the neutral n region, the number of holes are more than the in a depletion n region, the number of holes are more than the neutral n region. Is that clear to you? I hope complete discussion is clear to you. With respect to this Venn diagram also you can understand. With respect to this particular diagram as well you can understand. What mostly people do is that, sir, they will make this diagram and then they will simply join it. Why we are joining? Because of this diagram. Okay. So this theory has been written here. So this particular slide took a lot of time, but I hope you have understood the depth of this particular slide. What is the depth of this particular slide? This slide is saying that depletion region is also often said to be free of charge carriers, but in reality it is not completely empty. The number of mobile charge carriers in this region is much smaller than in the neutral region. For example, in the depletion p side, the hole concentration is much less than the neutral p side. In depletion p side, hole concentration is much less than the neutral p side. So towards the p side, what you are looking for? In the p side, I am looking for holes, and then I got to know that in this particular side, the holes are very less than this particular side. That's why I am calling it depletion region. And in the depletion n side, what I would be looking for? Electrons. So I go to know that electron concentration is much less than in a neutral n side. Okay, so in depletion n side I was getting very less electron concentration than the neutral n side. Hence depletion region is not completely free of charge carriers, but it is highly depleted compared to the neutral region. And when it comes to majority charge carriers, so these statements are written for majority charge carriers. Majority charge carriers, not for minority, because in the depletion region minority is actually increasing, right? In the depletion region minority charge carriers are actually increasing, not decreasing, but majority charge carriers are actually decreasing. That's why we call it depletion region. I hope it is clear to you. I hope this particular concept is clear to you. In the gate examination, very rare chance that question would come up, but in the interview someone can ask a good question from here. Okay, well and good. Now why this mass action law will be valid? We can prove that as well. Okay, although it is not a very good derivation, like it will not be of any use, but still we will prove it, because when we bias, when I give forward bias or when I give reverse bias, then we would see that mass action law will not be valid. So this law would become law of junction there. So all these things we will see, but as of now we are doing the derivation. What I am saying, for neutral p side, what is the scenario? EFI minus EFP for neutral p side. Let's go here. EFI minus EFP for neutral p side. EFI minus EFP. What that would be equivalent to? Sir, KT number of holes divided by Ni, right? And for neutral n side, EFN minus EFI. EFN minus EFI. EFN minus EFI. What that would be equivalent to? KT ln number of electrons divided by Ni, right? For the neutral side, you are sure that, sir, mass action law will be valid. Nothing is happening here. Here also mass action law will be valid. Sir, Nd divided by Na square by Nd, Na divided Na, and here I am getting Na square by Na. So no issue there. The issue is in the depletion region, right? The main problem comes here. Here you are worried, right? For depletion region, under equilibrium, what will happen? Sir, EFN would become equal to EFP. In the depletion region, EFN is equal to EFP when under equilibrium, and that I can write as EF. So what I am getting? EFI minus EF is equal to this thing, and EF minus EFI is equal to this thing. Now what is this P? This P is different, okay? This P is of depletion region. So what I am putting here, P depletion, okay? Number of holes present in depletion region, number of electrons present in depletion region, okay? Inside the depletion region, what is PD? Holes in depletion region, hole concentration in depletion region. Not important for your examination although, okay? So what do I see? If I add both of them, what I will get? Equation 1 added with 2. EF will get cancelled out, EFI will get cancelled out. So 0 would be equivalent to KT ln, and these two will be added. So what I will be getting? Ni square. From here what you see? Inside the depletion region, the concentration of electron multiplied with the concentration of hole would be equal to Ni square. And it is pretty obvious as well. No matter, even if the depletion region is framed, who cares about that? Unless and until you are having equilibrium condition maintained. So under the equilibrium, always I have to follow this mass action law. Simple question what they can ask, that inside the depletion region at x equals to minus xp plus delta x, I am having the whole concentration as 10 to the power 14. My Ni value was 10 to the power 10. Find out the electron concentration. In this simple question only, a lot of people will struggle. What they would think, okay, inside the depletion region, how holes are coming? Holes are zero there. So they will struggle here. But you know that if my device is under equilibrium, N into P equals to Ni square will always be valid. Till what point? Equilibrium. Just as I give forward bias, the scenes would change. The scene would become N into P equals to Ni square e to the power Va by Bt. We will see that. Okay, don't worry about that. But under equilibrium, everything we are discussing under equilibrium. So under equilibrium, always this condition will be maintained. Okay, so what do you see? Under equilibrium, no matter PN junction is framed, no matter depletion width is framed, always I know one thing, the number of electrons multiplied with the number of holes would be equals to Ni square, no matter wherever I go. Someone wanted to prove it by mathematics, we can understand it. Someone want to see the intuition, we can understand it here. So here if I talk about the number concentration of electron and concentration of hole, if I multiply both of them, what I will be getting? Ni square only. But it doesn't mean that here charge carriers are of the same amount. What I mean to say is that 100 into 1 is also equals to 100 and 10 into 10 is also equals to 100. If I give you 10 candies, sorry, if I give you 100 candy and I give you 1 candy, that means I need to give you 101 candies. If I give you 10 candy and then 10 candy, that means I need to give you 20 candies only. So what was the scenario? 10 to the power 16 holes and 10 to the power 14, 10 to the power 4 electrons. This was the scenario of a neutral P region, right? But here what really happened? Here 10 to the power 14 and 10 to the power 6. So here the charge carrier was 10 to the power 16 plus 10 to the power 4, which was nearly equals to 10 to the power 16 only. And here what is the total charge carrier? 10 to the power 14 plus 10 to the power 6, which is nearly equals to 10 to the power 14 only. And 10 to the power 14 is nowhere compared to 10 to the power 4. Similar scenario you can understand by this example as well. 100 into 1. Although mass action law is valid. Mass action law, what I am saying. Although this law N into P equals to Ni square, that is valid. Right? It is known as mass action law only. यार इस लो का नाम भूल गया मैं, मास सेक्शन लो ही था ना इसका नाम, n into p equals to ni square. It was mass section law only, or what it was? Yeah, it was mass section law only, whatever it is. So that will always be valid, but you know that it doesn't mean that charge carriers are same. No, 10 to the power 16, 10 to the power 4, 10 to the power 14, 10 to the power 6. Huge difference is there, right? 10 to the power 14 is nowhere compared to 10 to the power 16. And 10 to the power 6 as well is nowhere compared to 10 to the power 16. So who is the boss? Boss is neutral P region, right? All good, all fine. So let me take a break. We will understand some more formula. We will derive some formula and we will start solving some numericals as well. Okay. So charge neutrality I need to see. What do you mean by charge neutrality? So from now onwards, what is the assumption I will make? Wherever I go, what is the assumption? Assumption will always be there that I will not care about charge carriers inside that depletion region. Will be always ignored. Now what I need to do, I need to apply the charge neutrality equation. What does that mean? That means what I am saying is that this particular semiconductor is neutral. Okay. Basically what I am saying is that this particular semiconductor is neutral. So I will copy this diagram. Yeah, sorry for the interruption and welcome back. So I took a break in between. You can also take some break. You can also take some water. We need to study about charge neutrality now. So assumption, what assumption we are going to make, that also I have mentioned, and this was our PN junction, right? So in this PN junction, this was your P side, this was your N side, and this depletion width I was calling as minus xp. This was my x equals to 0 point and this was my plus xn point, right? Now I know that this PN junction is electrically neutral because here negative charge is cancelling out positive charge, negative charge cancelling out positive charge, positive charge is cancelling out negative charge, positive charge cancelling out negative charge. But what do I see here? Sir, here there is a negative charge, but here there is a positive charge. So positive charge has to be equals to the negative charge. In the neutral region, positive and negative is cancelling out. That's why we call it neutral. So where is the issue? Issue is there in the depletion region. So in the depletion region, whatever the positive charge that I am having, it has to be equal to the negative charge. If both are equal, that means there is no issue. If both are not equal, that means there is a problem. So under equilibrium, every semiconductor would be, any material, forget about a semiconductor, any material will be electrically neutral, right? There is no external bias, so it has to be electrically neutral. So total charge has to be 0. So what does this charge neutrality says? The total charge in the semiconductor should be equals to 0. That means positive charge should be equals to negative charge. In the neutral region, I don't have any issue. I only have the issue with the depletion region, right? So in this particular region, from minus xp to x equals to 0, what I mean to say is that from minus xp to x equals to 0, from minus xp to 0, what you are having? In this particular region, you are having negative charge, right? And between 0 to xn, what you are having? You are having positive charge. So total negative charge should be equal to total positive charge. If this condition we are getting, then our job is done. This is what your charge neutrality will say. Now, how much negative charge is there? What is the unit of charge? Coulomb, right? What is the unit of charge? Coulomb. So how much Coulomb charge is there, that I need to find out. So what is the level of doping? This is my p side, this is my n side. So what is the level of doping? I have doped Na amount of atom and here I have doped Nd amount of atom. So I have done the doping of Na atoms per centimeter cube. Na atoms per centimeter cube, right? This much doping I have done. Let's just say value of Na is 10. So I have doped 10 atoms per centimeter cube, right? Now this semiconductor you will see in 2D. This semiconductor you are seeing in 2D, but it is actually a 3D structure. Like it is this structure, no? Let's just say this is your semiconductor. This mobile phone, that is your semiconductor, right? So it has some cross section area as well, no? Like if I have made this one, then actually this is a 3D structure. Actually this is a 3D structure, no? So it has a particular cross section area as well, right? So some cross section area would also be there. So if I multiply Na into A, what does that mean? That means you are talking about the atoms per centimeter length. And when I multiply Na into A with x, what does that mean? Na into A into x. X, in place of x I am putting xp. That means in this much of region, how many atoms I have doped? Do you understand this point or not? Okay, just one second. Just one second. Yeah. So what this particular quantity is representing? Na into A into xp. What does this represent? Na was total atoms per centimeter cube volume. When I multiply with the area, that would become total atoms per centimeter length. And when I multiply this with xp, that means in this much of length and this much of area, you are having these many atoms. How many atoms you are having? These many atoms you are having, right? Now each atom is giving you one negative charge. That means this much atom would give you this much negative charge. But this is the unit of atom, no? One atom would give you a charge of 1.6 into 10 to the power minus 19 Coulomb. So this much atom would give you a charge of, multiply with Q. So this much negative charge you are having here. Are you able to understand this point or not? Are you able to understand this equation? Na into A into xp, that was representing atom. One atom would give me one negative charge, right? One atom would give me one negative charge. That means one atom would give me Q amount of charge. So these many atoms would give me how much amount of charge? This much amount of charge. Similarly here as well you can do Q into ND into A into Xn. Why I am multiplying with Xn, or why I am multiplying with Xn or Xp? Because I need to find out the total positive charge in this particular region only, in this particular region, whatever the region that we are getting here. In this particular region only, I need to find out the total negative charge. In this particular region only, I need to find out the total positive charge. I don't care about these regions because I know that these are electrical neutral only. So in the from 0 to Xp with area A, right? From 0 to Xp with area A, how much atoms you are having? Na into A into Xp. These many atoms you are having. Multiply with Q, that would be the total negative charge. In this much area, what you are having? Area and this length. So in this much volume, how many atoms you are having? Sir, in this much volume, I am having Nd into A into Xn. This much atoms I am having. Multiply with Q, what I will get? Total positive charge I would get. And total negative charge should be equal to total positive charge. Usually people don't understand this equation. They will just remember it. Those who are studying EDC for the second time, they would realize that we used to mug up the final result. What will be the final result we are going to get? Q and Q is getting cancelled out, A and A is getting cancelled out. So people will usually remember Na into Xp is equals to Nd into Xn. But now I hope you are able to understand what was the meaning of this particular relation. So meaning simply says that your semiconductor is electrically neutral. Your semiconductor is electrically neutral. This is what this particular relation is saying. So total positive charge is equals to total negative charge, and they are already neutral only. They are already neutral. So from here, what do you see? Na by Nd is equals to Xn by Xp, right? Or I can write down Na ratio Nd would be equals to Xn ratio Xp. So from here directly you can say that, sir, my Xp is inversely proportional to 1 by Na. Can you say in this manner? Xp Na, inverse relation is there, no? So basically if more doping is there, lesser depletion width would be there. Are you able to understand this point? More doping, lesser depletion width. Are you able to understand this or not? Forget about it. If you are not able to understand, so let's see here. What will be your total depletion width? Total depletion width. So total depletion width could be given as W. So that would be equals to Xn plus Xp, right? So W would be equals to, in place of Xn, what I can put? Na by Nd into Xp, right? Na by Nd into Xp plus Xp, right? So what you are getting? So Xp would be Nd upon, from here you can find out the value of Xp, Nd upon Na plus Nd into W. So this is the value of Xp you are getting. Similarly, you can find out the value of Xn as well. What you will be getting? In this manner, if I find out the value of Xn, so this is what I will be getting. Now this is something you don't need to mug up. You will be able to understand it. Let's understand it with respect to an example. I will simply write down a very simple example. What I would do, I would add a page and I will simply write down an example that, sir, PN junction is under equilibrium. PN junction under equilibrium. Okay. The depletion width, total depletion width came out to be 2 micrometer. Okay. What we did the doping. We did the doping in this manner that P side was doped with 10 to the power 16 atoms per centimeter cube, and N side was doped with, N side was doped with 10 to the power 15 centimeter cube inverse. You need to find out Xp and Xn. This is what you need to find out. So can you do it? What do you think? What will be the answer? Sir, if I just apply the formula, let's apply the formula blindly. So what we are getting, sir, Xp equals to W into Nd upon Na plus Nd. So what I would do, let's make it 2.2. It would become much easier for us. Let's make it 2.2. Okay, 2.2 micrometer. So what would be my Xp? What did I say from this relation? Sir, doping more. Na is having more doping, right? P side is having more doping. That means the depletion width on the P side will be lesser. So answer would be 10 to the power 15 upon 10 to the power 15 plus 10 to the power 16 into W. So what that would be? 1 upon 11 into W will be 2.2. So answer would be 0.2 micrometer. So what do you think? What will be the answer of Xn? 0.2 is there on the P side, so 2 would be there on the N side. But we can see the answer. What will be the answer? 10 to the power 16 upon 10 to the power 15 plus 10 to the power 16 into W. So what I will be getting? So here this would be 0.1. 10 to the power 15 if I take common, so 10 by 11 into 2.2. Answer would be 2 micrometer. Okay, so you can see here. So what you can see, this was the semiconductor material I was having. Okay, and this was my midpoint. This was my x equals to 0. Here I did more doping. Here I did more doping. Na was more. And here I did lesser doping. Moderate doping was there, which was 10 to the power 15. But I know that charge neutrality has to be same. Let's just say here there is more doping. So can I show it in this manner? Here there is more doping. Right? So in this manner I will show it. And here there is lesser doping. So can I show it in this manner? Can I show it in this manner? Okay, this is P side. Sorry guys. This is your P side, right? So here there is more doping. And what is your N side? Lesser doping is there. Right? So let's just say this is the depletion width we are getting. In the depletion width, whatever the amount of total positive charge you are having, the same amount of negative charge you need to have. So it is pretty obvious that if this particular side is having more doping, then in one column only you are getting 4 negative charges. But here lesser doping is there, no? So they will be far away. Are you able to understand this point? So here in 2 columns you are getting this much positive charge. Basically, if here you are getting 4 positive charge, so here only you will get 4 positive charge only. So this would be my XP, minus XP you can say, and this would be my XN. So you can say that sir, XN would be much wider than XP, right? This length would be 2 micrometer and this length would be 0.2 micrometer. This would be 0.2 micrometer. So 0.2 micrometer, 2 micrometer. This much gap is there. This would be 2 micrometer. This is 0.2 micrometer. Here I can show it. This is 0.2 and this is 2. This much gap is there, right? So more doping, lesser depletion width. So if Na was more, I was having lesser depletion width. Nd was lesser, so I was having more depletion width. And it is pretty obvious as well. Intuitively also you can see that, because positive charge has to be equal to the negative charge. So here this kind of doping would be there. This kind of doping would be there. I don't care about the neutral region, but here this kind of doping would be there. This kind of doping would be there. Right? So here 4 positive charge would be equal to 4 negative charge. So I would require only this much of width. Here I would require this much of width. So let's not do anything here. And by the example as well, I have understood. So do you really think that, sir, you need to mug up this formula? Only remember this thing. Na into Xp equals to Nd into Xn. From where it came? Charge neutrality. Positive charge equals to negative charge. That's it. Na into Xp equals to Nd into Xn. Charge neutrality. You remember by this, you get the expression, and somewhere in a lot of problems it will happen that we will get the value of depletion width, but in the examination they would ask how much depletion width is there on the P side. So what you would do? Xp equals to inverse relation is there. So Nd upon Na plus Nd into W. Right? So this we are doing. Nd upon Na plus Nd into W. Very simple thing, right? Now the whole lecture will be based on mathematics and problem solving. That's it. Concept has been cleared. Whatever the concept that we wanted to learn, starting with PN junction. When you revise, how will you revise this lecture? Till this point, how would you revise this lecture? It's been roughly around 2.5 hours, but within 5 minutes, you will be able to revise everything. What you would do? Starting with this particular point, nothing new here. Here also I know everything. Then I go to know that in this manner I can understand EFN would go lower, this guy would come lower, this guy would go upper side. So from here I go to know that, sir, in this particular scenario, I get to know that this was my equilibrium condition. In equilibrium condition, I am getting some built-in potential. This built-in potential is making sure that the amount of diffusion is equal to amount of drift. Diffusion would go from, electrons would be moving from downward to upward, that motivation would be diffusion. If it is moving from upward to downward, that motivation would be drift. So this particular part you need to revise, that's it. Then I saw that, then what did I see? if I apply an external bias which is supporting my built-in electric field, that means the barrier has increased now. If the barrier has increased, then diffusion has become even more tougher, but drift has become easier. So this will be drift dominant. If my external electric field is supporting the built-in electric field, then it would become drift dominant, otherwise it would become diffusion dominant, right? All this scenario I understood. Then I compared all the scenario. Then how would I find out the built-in potential? So from the geometry only, from energy band diagram only, I can find out the built-in potential, which will be Vt ln higher doping divided by the lower doping. Okay, higher concentration divided by the lower concentration, making sure that if I am writing down 4 holes, then higher hole divided by lower holes, and if I am writing down 4 electrons, then higher electrons divided by the lower electrons. This I will make sure, right? So here both of the concentration of electrons I am putting, right? Then we saw the numerical. So this part will be revised within 1 minute. Then what about this part? PN junction would be made, built-in potential would be there, under equilibrium we are considering. So drift and diffusion would be cancelling out each other. One built-in electric field would be set up, right? So this built-in electric field, what it would make, it would want the holes to travel from right to left, but because of the diffusion, holes will travel from left to right. So diffusion and drift would cancel out each other and total current would be equals to 0, right? But in the depletion region, then this is the nomenclature which you don't need to revise. Again and again we will be using this word: depletion region, neutral region, depletion region on N side, depletion region on P side, junction it is, and then depletion width would be Xn plus Xp, depletion region on N side would be Xn, depletion width on P side would be Xp, depletion width on N side would be Xn. So these nomenclature you don't need to revise. Then important part, some discussion on depletion region. So discussion on depletion region, only conclusion is that always mass action law will be valid. N into P equals to Ni square will always be valid, right? But in the depletion region, the concentration would be much lesser than the neutral region. But again, there will be some electron and holes will be present. There is no doubt about that. And the multiplication of electron concentration to the multiplication of hole concentration would be equals to Ni square. This derivation is of no use. You can simply ignore it. But this derivation would make a greater impact when we study forward bias, when we study reverse bias. So there, this derivation would make greater impact. That's why I wrote down the derivation here. So if your device is under equilibrium, there is no external bias, there is no external light, everything is happening under dark. Okay, nothing, no light, nothing is there. Then N into P equals to Ni square will be valid, right? And we can see, we can comment about the electron concentration and hole concentration. So when I move into the depletion region, from P side to I am moving into the depletion region. So what I would see that my hole concentration is actually decreasing, but my electron concentration is actually increasing. And when I move from N side to the depletion region, from N side to the depletion region, so my electron concentration is actually decreasing, but my hole concentration is actually increasing. So this kind of plot I get. This is not a linear plot, this is the plot on log scale. So on the linear plot, it may feel like that this concentration and this concentration is nearly equal only, but they are not actually equal. One is 10 to the power 16, other one is 10 to the power 14. Big gap is there. But always N into P equals to Ni square will be valid, right? Then we talked about charge neutrality, Nd into Xp equals to Na into Xn. From here we get this formula. Okay, so now the mathematical part is going on. Okay, so more expression we need to derive. What all expression we need to derive? Sir, some electric field will be built up, right? Some electric field will be built up. So I need to find out the expression of electric field. Sir, some voltage will be built up. It could be in this direction. Sir, I need to find out the expression of that voltage as well. Built-in potential we have already found out, but in terms of electric field, what will be the expression? That also I need to find out. Sir, depletion width formula, that also I need to find out. Sir, this W that I am putting up here, the value was given 2.2 micrometer. So this formula also, this value also I need to find out. So all these things I need to find out. So some mathematics is required, some electrostats is required. So now what we are going to see? We are going to see the electrostats of PN junction under equilibrium. All the calculation we are doing under equilibrium. When I apply some external bias, the same calculation would go on, just the formula will change. Only a minute change will be there in the formula, rest all the things will remain same. So derivation is important, very important. Okay, derivation is important. It's not derivation, it is concept only. Just understand it as a concept only. But before that, some basic concept of electrostat should be clear to you. Do you know that what is the relation between electric field? This is my electric field, okay? E is my electric field. So what is the relation between electric field and the potential? Surely I know that, sir. from the first chapter only, I have already studied this particular thing, right? And from here, I can derive what would be my Vx. So that would be minus infinity to x ex dot dx. Is that clear to you? This relation we already know. Now another relation is there. So electric field is equals to charge density, volume charge density dot dx divided by epsilon. Integration goes from minus infinity to x. Okay, can you remember this formula? We will derive it in in our EMFT. Del dot d equals to rho v, Maxwell equation. If I only consider one dimension, then del would be replaced with d by dx. D could be written as epsilon e. Epsilon e. This epsilon can go downward. So what I will be getting? If this epsilon goes downward, so what I will be getting? This is the same thing only. Now this goes here. So what you are getting? Rho v by epsilon dot dx and then integration. This is the same thing I have written. So del dot d equals to rho v. You always remember that. In EMFT also you will always remember it. Del dot d equals to rho v. Okay. From here very easily you can derive this expression. Again and again we are going to use this expression in this chapter. So as of now you will remember it, but in longer way, in longer run, let's just say after 3 to 4 months you are studying this chapter, then how will you remember? In EMFT we will study del dot d equals to rho v. So from here you will be able to derive it very easily. D would be epsilon e, epsilon goes downward, so del e by del x is equals to rho v by epsilon. So E would be rho v by epsilon and then integration dot dx. Okay. What do you think? What is the unit of rho v? What is this rho vx? Rho vx is volume charge density. Volume charge density. Okay, so what do you think? What will be the unit? Unit will be coulomb per centimeter cube. So do you remember kq by r square? I am just telling how to remember this formula. Do you remember kq by r square? Yes, sir. Electric field is equals to kq by r square. What was your k? Sir, it was 1 by 4 pi epsilon naught or epsilon q by r square. So this would be coulomb per centimeter square. Coulomb per centimeter square divided by epsilon. Are you getting the same thing here? What is rho v? Coulomb per centimeter square. Multiply with x centimeter divided by epsilon. So what you are getting? Sorry, rho v is coulomb per centimeter cube. Rho v is coulomb per centimeter cube. So this and this get cancelled out. So what you are getting? Coulomb per centimeter square divided by epsilon. So coulomb per centimeter square divided by epsilon. So this is how you can remember it. Any way we need to remember. I have told 3 to 4 ways of remembering this particular formula. So electric field x, which could be a function of x, that would be equals to rho vx by epsilon dot dx, where rho vx is volume charge density. Okay. So we will see more about it, but these two formula will be used in our further analysis. Right. Now what we are doing? We are making a PN junction. But this time in place of making PN junction, I am making P plus N junction. It is not necessary that sir Na value should be equals to Nd. What I mean to say is that if I am doping Na amount of atom here and I am doping Nd amount of atom, so it is not necessary that Na would be equals to Nd. Here Na is not equals to Nd. You can clearly see that Na is greater than Nd. So my doping on the P side is more than the doping on N side. Is that clear to you? My doping on P side is more than the doping on N side. That's why I am putting it as P plus N junction. P plus N junction. So if I make the doping concentration with respect to distance, so this is my x equals to 0. This is my x equals to 0. So here there will be negative x and here there will be positive x. So in the negative x, what I am doping? I am only doping the acceptor atom. In the negative x, I am only doping the acceptor atom. And in the positive, let's just say I am doping Na amount of acceptor atom. Now here on the positive x, what I am doping? I am doping the donor atoms. So will I make the donor atom here or I will make the donor atoms here? I will make the donor atoms downward because Na is more than Nd. Y-axis is doping concentration. So Na is 10 to the power 16, Nd is 10 to the power 15, right? This example we took, no? 10 to the power 16, 10 to the power 15. So here there is more doping, here there is lesser doping. So Na is more and Nd is less. right? So if this value is 10 to the power 16, this value will be 10 to the power 15. It could be any value, but this is how I can show. This is how I can show my doping concentration, right? Now in this particular example, can you tell which will be larger, Xn or Xp? Which will be larger? Xn would be larger or Xp would be larger? If lesser doping, that means more depletion width. What does that mean? Xp would be lesser than Xn. In this example also you can verify. Xn would be more than Xp. Xn is more than Xp. Right? Well and good. So let's see some diagrams now. So first what I will draw, where I need to go. From rho V to I will go to E, and from E to I will go to V. Is that clear to you? If I have the expression of rho V, if I know the diagram of rho V, I can get electric field. If I know electric field, I can get potential. So first what I would draw volume charge density versus X. So I will move on my semiconductor from here. This is my X equals to 0. This is my X equals to 0. So I am moving on my semiconductor from this side. So in this region, how much charge I am getting? 0 charge. Because positive charge multiply with, positive charge, negative charge cancelling out. Negative charge, positive charge cancelling out. Negative, positive cancelling out. So here there is 0 charge. So what is the charge I am getting? Sir, from minus infinity to minus xp. This point I am considering as minus infinity. And this is my plus infinity. So from minus infinity to minus xp, you are getting 0 charge, sir. Till this point, you are getting 0 charge. Then what you are getting? Then you are getting negative charge. So here I will get the negative charge. But charge is uniformly doped. This is the case of uniform doping only. Now no one will say that, sir, here Nd is lesser, Na is more. So this is non-uniform doping. No. Doping is defined with respect to one region. This particular region has been uniformly doped. This particular region also is uniformly doped. It's not that, sir, here there is more doping, and then, sir, here there is lesser doping, then again, sir, there is more doping. So this is not non-uniformly doped. Uniform doping is there, no? You can see uniform doping is there. So P side is uniformly doped, N side is uniformly doped. So this is the case of uniform doping. So what I mean to say is that, what does your rho Vx represent? Charge per volume. What it is represent? Charge per volume. But this charge per volume is a certain value, no? Like when I am moving from minus xp to 0, my charge per volume is Qna. Do you agree to this point? It is equals to minus Qna. Why is that so? My charge per volume is minus Qna. Why is that so? Because what is the doping I am doing? I am doping Na acceptor atoms. I am doping Na acceptor atoms. Atoms per centimeter cube. What do I require? I require charge per centimeter cube. So this much atom I am having. Each atom would give me this much of charge. So I am having Qna charge, but that charge is negative. So from minus xp to 0, this much charge per unit volume you are having. Are you able to connect this point or not? Are you able to connect to this diagram or not? Again, let me repeat what I am saying. From minus xp to 0, I am having negative charge. How much negative charge? What this rho v would represent? This rho v would represent Coulomb per centimeter cube. So Na is atom per centimeter cube. So Q into Na would be this much charge per centimeter cube I am having. So minus Qna, this much charge per centimeter cube I am having. When you go from plus infinity to xn, plus infinity to xn, from plus infinity to xn, in this much region, how much charge you are having? 0 charge. Positive cancel out with negative, positive cancel out with negative, positive cancel out with negative, positive cancel out with negative. So 0 charge you are having. So from infinity to xn, you are having 0 charge. But between 0 to xn, what you are having? Between 0 to xn, I am having positive charge. And how much is that positive charge? So that positive charge would be equal to Q and D. Say yes or no. Here we did the doping of Nd. Although I know that my Nd was lesser than Na. Are you able to understand this point or not? I hope it is not very difficult for you. total negative charge, total positive charge, right? Not total, because this is density only, so this is not representing total charge. What it is representing, between minus xp to 0, what is your charge density? That means how much amount of charge per unit volume you are having. So I am having q and a amount of charge per unit volume, and I am having q and d amount of charge per unit volume, right? So this is the rho vx I am having, charge per unit volume. Now from here, can you make the expression of electric field? If I am having this particular expression, can you draw the diagram of electric field? What we are drawing? We are drawing the diagram of electric field. So can you draw it? So what is my electric field? Here I will write down the formula. You integrate from minus infinity. So basically you integrate this waveform and then divide by epsilon. That's it. Can I write it down in this manner? That I integrate my this waveform divided by epsilon. Integrate the waveform divided by epsilon. So this is the electric field that I am getting. So integrate this waveform divided by epsilon. So now what I will do? I will integrate this waveform. I hope you are comfortable with signal system. So between minus infinity to minus xp you are getting 0. Nothing you are getting. Now from minus xp to 0 I need to integrate. What is the meaning of integration? Integration means simply area. So here this much area I will be getting, then area would keep on increasing. So total negative area I will keep on getting. So when I reach till this point, how much area I have got? So this area is minus QNA. What integration represent? Integration simply represent the area. So this area will be the value here. This is a step function, no? What is the integration of step function? That would be ramp. If you integrate this, what you will be getting? Ramp only you will be getting, right? So this is step, what you will be getting? Ramp. I don't think it will be very difficult for you to understand, right? Or what you can think, integration is nothing but the area. So first this much negative area I am getting, then this much negative area I am getting, then this much negative area I am getting. So negative area will keep on increasing. So total this much negative area I am getting. This much negative area I am getting. So this is the total negative area we are getting. So how much is this negative area? That is minus QNA XP area divided by epsilon. So this is the value I am getting. So let's write down this value later on. Let's write down this value here. Minus QNA XP divided by epsilon. After that, what will happen? Positive area would come into action. So whatever the total negative area I was getting, I need to add up positive area here. Okay. So from 0 to xn I need to integrate. From 0 to xn I need to integrate, because after that everything would be 0 only. So just let me know what will be the value at xn you will be getting. Like what will be the value of electric field at xn? Use your brain. So that value will be 0. Why is that so? Can you understand that? Why this value will be 0? At xn, why the value will be 0? Because this particular area would be equals to this particular area only. What do you mean by this area? What this area would represent? So this area was giving me Q and D xn. Q means coulomb, and D means per centimeter cube. Multiply with xn, centimeter. What you are getting? Total charge per centimeter square, right? So rho Vx dot dx Q and QNA XP, QNA XP, Q and D xn, or you can say QNA XP, you can say. So if I forget about Q, what do I know? ND into xn would be equals to NA into XP only, no? Here only we derive, no? And NA into XP would be equals to ND into xn. So ND into xn would be equals to NA into XP only, and both sides is multiplied with Q. So basically whatever the total area that I get here, what will be this area? So this area would be equals to Q and D xn, right? This area is, this area is Q and A xn. Let me write it down again. What is this area? So this area is Q and A multiply with XP. So this much area is Q and A XP. And what is this much area? So this much area is Q and D xn. and I know that ND into Xn is equals to Na into Xp. If I multiply with Q on both of the side, both will be equal only. So this total negative area is equal to total positive area. Total negative area is equal to total positive area. What does that mean? That means total integration here would be equals to 0. Is that clear to you? Usually I have seen that people blindly make this diagram. They don't understand the meaning of it. We need to understand the meaning of this geometry that we are doing. If we are studying mathematics, then purely mathematics we should study, no? Are you able to understand this point? Okay, here I am not going to write down some complex expression that you integrate from minus infinity to x, and just pure mathematics. Just do the integration, you will get this answer, right? So can you just let me know one thing? This particular expression that I am writing down, isn't it my maximum electric field? Can I call it E naught max? This 0 is coming because it is at equilibrium. So from now onwards I will write down xn naught, xp naught, xn naught. Okay, why this note I am putting up? Because we are talking about equilibrium, no? So this is my depletion width at equilibrium, depletion width on n side at equilibrium. So here also xp naught, xn naught. So isn't it E naught max? What do you think? What is the value of E naught max you are getting? Sir, E naught max I am getting as minus q Na xp divided by epsilon. Sir, q epsilon I keep as it is. Na into xp, can I replace it with nd into xn? Na into xp I can replace with nd into xn as well, divided by epsilon. So I can call this as my maximum electric field as well. Although it will be negative. Why it is negative? Because it is coming in the negative direction. Basically, Na into xp is equals to nd into xn. So this is the maximum electric field I am getting, and that is nothing but equals to the area of this one. Why it is equals to the area of this one? Because you know that the expression of electric field would be given by this. This is the expression of rho Vx. You are just integrating it. This was the step, you integrated it, it became ramp. Then another ramp you are getting. Total area would be 0. So this kind of electric field expression you are getting. So your all electric field is there in this particular region only. Between minus xp naught to xn naught, you are getting non-zero electric field, which is giving me this kind of expression. Is that understandable to you or not? So what they would ask, they can ask the maximum electric field, and where maximum electric field is occurring. Maximum electric field is occurring at the junction, and I told you this thing, the maximum electric field will always occur at the junction only. So where the maximum electric field is occurring? Maximum electric field is occurring at x equals to 0. So this we got at x equals to 0. Say yes or no. Now in the examination, let's just say they ask you the electric field at this point. Okay, what they do? They ask you the electric field at, let's just say xn naught is 2 micrometer, and they are asking you electric field at 1 micrometer. What do you think? What you will do? You need to find out electric field at 1 micrometer. So at x you need to put 1 micrometer. That means what you will do? You will integrate from minus infinity till 1 micrometer. From minus infinity to 1 micrometer you will integrate. That means this much area plus this much area. That would be your answer. So usually what people do is that they will derive some expression of electric field and they will remember that expression. No. In the examination, if they are not asking me maximum electric field, let's just say they are asking me electric field here at 1 micrometer. So will I derive some expression or anything? No. What I would do? I would make my charge density plot, volume charge density plot I will make. I remember this expression that I need to integrate this graph divided by epsilon. So what I will do? I will calculate this particular area, integrate this graph means this much area I will calculate divided by epsilon. We will see the problem. I have framed a numerical question. So with respect to that numerical question, everything would be clear. Okay. So I am just telling that they can ask the electric field at any point. Till this point in the gate examination, in the history of gate examination, they have always asked the value of maximum electric field. Till this point, always. In the history of gate examination, they have always asked the maximum electric field. They have only asked this particular thing. But who knows, they can ask electric field at a certain point as well. So can you find out the electric field at a certain point? Surely I will be able to find out the electric field at a certain point as well. What I need to do, I just need to draw the graph. Which graph I need to draw? Sir, I only need to draw this particular graph. Which particular graph? This particular graph. Then you can ask me electric field at any point. If you ask me electric field here, I will integrate from minus infinity till this point, which will be equals to 0. If you ask me electric field here, so I will integrate from here to here. That means this much area I will calculate and then divided by epsilon. If you ask me electric field till here, then this much area I will calculate divided by epsilon. If you ask me electric field here, then from here to here, this much area I will calculate divided by epsilon. What that area would be equals to? Because this area and this area would be equal to each other, so total area would be 0. So 0 divided by epsilon, that would be also 0. So here you can see that electric field is 0. If you are asking me the electric field at the junction, then this much area I will calculate. What that area is equals to? Q Na xp naught divided by Q Na xp naught or xn naught divided by epsilon. Or Q and dxn naught divided by epsilon. Is that clear? Okay. Let's write down the expression of a voltage now. So again, for the voltage, what I need to do? For voltage, this is something, but negative sign is also there. Okay, again and again, let's not make it bad. What I do, let's keep it here only, and here I write down the expression of voltage. So voltage expression is integration of this one, integration of electric field. Basically, it will be the integration of electric field. That's it. Integration of the electric field, but with the negative sign. So this is a ramp. Can you integrate it? I am really hopeful that people will be able to integrate this particular scenario. Okay. What we need to do, we need to start integrating from minus infinity to plus infinity. We need to integrate. So if I want to find out, if I am integrating from here, 0 integration 0 0 0, everything would be 0. So till this point, everything 0 I will be getting. All good. After that, what will happen? Negative area would come into action. So I am calculating the area. Here, 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 it will keep on increasing. Again, negative area is coming into action. So area will keep on increasing, keep on increasing. So total, this much area I will be getting. Total what I will be getting? This much area I will be getting. This is my total area. If I am integrating, what I am doing? I am integrating. Here also I was doing the integration only. I said that integration is nothing but the area. So integration area, negative area, negative area, negative area, negative area, negative area, negative area. Then positive area start coming into action. That means negative, positive, negative, positive, negative, positive. So the graph was reducing. Eventually it came out to be 0. Now here negative, 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 negative. Again negative, 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 negative. So this much negative area I will be getting. But there is a negative sign as well. So the total negative area would become positive area. Are you understanding what I am saying? Negative, 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 negative. All the total negative would become positive only, no? Because there is a negative sign. And what is the integration of a ramp? That would be parabolic. So this kind of a parabolic result I will be getting. Is that understandable to you or not? I hope it is understandable. And after that, no further area will be added. So after that, it will become constant. Now, can anyone let me know what this height would represent? Basically, what this height would represent? Can anyone let me know what this height would represent? So this height would represent built-in potential. What I am drawing? I am drawing Vx versus x. So that means this potential minus this potential, isn't it built-in potential only? Isn't it VBI only? Here positive potential you are having, here negative potential you are having. So positive potential minus negative potential, whatever the potential that your depletion width is having, that potential is built-in potential only. So starting from here, from 0 to how much potential you have built up. But basically, if you integrate this particular graph, this is what you will be getting. If I integrate this particular graph, this is what I will be getting. But since I need to take the negative sign, because there is a negative sign, so this reflection I will get, right? Mirror image I will be getting. So this negative graph would become positive graph. Can anyone tell me what will be the magnitude here? What this would be equals to? This would be V built in would be equals to area of this one. Is that clear to you? Very simple thing it is, not very complex. Again, mathematics it is, so I don't know how to explain mathematics. Like this could be my best part or it could be my worst part, that I don't know how to explain mathematics, like what I would explain here, right? So this much area would be the built-in electric field only. Just there is a negative sign, so it would become positive. So this much area, what will be this much area? So this area would be half into base. What is your base? Xn naught plus xp naught divided by height. What is height? E naught max. So xn naught plus xp naught, what that would be? Depletion width. So it would be half into depletion width E naught max. Do you agree to this point or not? Again, let me write down what I am getting. My built-in field is actually coming out to be, that would be equals to this area, because what I need to do, my potential is minus infinity to x ex dot dx. So I will integrate from minus infinity to x, right? But I need to find out the built-in potential, so total potential that has been developed. So I will integrate from minus infinity to infinity. From minus infinity to infinity I will integrate to find out the built-in potential. Basically, what will be your built-in potential? Your built-in potential will be minus infinity to infinity E of x dot dx. So this total area multiply with the negative sign. So that would be half into base. What will be base? Base will be depletion width into height. So that is the relation we are getting. Again, it is mathematics. You need to do the work in your rough notebook. You will be able to understand this. And really sorry to say, we are going to do much more complex mathematics in the further analysis. Okay. After some time, here luckily the doping was uniform. Uniform doping here, uniform doping here. Till this point, always in the gate examination, they have always given uniform doping. But who knows later on what they can do? They can give you non-uniform doping as well. So I will make you prepared for non-uniform doping as well. So in that non-uniform doping, this graph will not become step. This graph will become ramp. If this is ramp, this will become parabolic. If this is parabolic, then this will become x cube, right? Because this is not a function of x. This became a function of x and this became a function of x square. In the examination, what may happen? This become a function of x. This would become a function of x square and this would become a function of x cube, right? So till this point, always they have asked about this condition only. So people usually what they do, they remember three formulas. What three formula they will remember? They will remember this particular formula. They remember the formula of E naught max as well. So can I write down the formula of E naught max? Maximum electric field that will occur at the junction only. If I talk about the magnitude, magnitude is coming out to be, sir, Q Na into xp, total charge, right? Na into xp, total charge, Q Na into xp, xp naught I will put, divided by epsilon. How will I remember this formula? Sir, very easy. Sir, Kq by r square I remember, right? K is 1 by epsilon, Q by r square. That means you need to write down charge per centimeter square. I am having the value of Na. If I multiply with Q, what I am getting? Charge per unit volume. I will multiply with xp. So what I am getting? Charge per area square. Sorry, not area square. Charge per area I will be getting. That means charge per centimeter square I am getting divided by epsilon. So Q into Na, xp naught divided by epsilon. That's it. Okay. And that would be equivalent to Q and D xn naught divided by epsilon. So people usually remember this formula. So are you going to mug up this formula? No. You will have the diagram clear in your mind. Sir, QNA here, QND here. I will integrate it. So QNA XP, QNA XP I am getting divided by epsilon. That will be my electric field. So maximum electric field they are asking which is occurring at the junction. They may ask the electric field here as well. We will solve with respect to equation. They may ask the electric field here as well. Anywhere they can ask the electric field. We will solve all these electric field with respect to particular question. Okay. But maximum electric field, it should be stuck in my mind. What that would be? Sir, Q NaXP divided by epsilon. Okay. Rest, what all we can see? We can see built-in potential as well. built-in potential in terms of maximum E field. So what is your built-in potential coming out to be? Sir, built-in potential was coming out to be half into base into height. Height would be E naught max, right? So can it be written as half into, what is my E naught max? That is QNA XP naught divided by epsilon, right? Okay. From here, E naught max also you can write down. E naught max would be nothing you will mug up actually. Okay, you will not remember these formulas. What you will remember, you remember the concept. At least like this formula you try to remember, and this particular formula also I will keep in the box. You try to remember this one as well. Now from these formula only we will derive some expressions. Okay, so let's not write down this thing what I am doing here. It doesn't matter. So let's derive some expressions now. What I do, shall I do it here only or later on I can do? Here if I teach this. So here only let's derive the formula of this depletion width. Okay. So what I'm going to do, I'm going to derive the formula of depletion width in terms of built-in potential. So what I need to eradicate, I need to eradicate this E naught max. Okay. So what I need to do, I will derive the formula of this depletion width in terms of a built-in potential. Okay, this VBI is my built-in potential. So what I will do, I will eradicate this E naught max. So I will write down the expression and I will get the formula. This is completely mathematics. Let me take a break, drink some water. You also drink some water, and then we will come back and we will derive this particular expression. Okay, very simple mathematics it would be. Okay, so let me drink some water and then I will come back. Yeah, welcome back. So did you try deriving the expression? Okay, you can try it on your own as well. So let's get started. V built-in is equal to 1 by 2 W depletion. I need to eradicate this E naught max. So what I would do, I would put the expression of E naught max. Either I can put this one as well, I can put this one as well. So what I would do, Q Na divided by epsilon XP naught divided by epsilon XP naught. Look, epsilon is a constant value, Q is a constant value, Na is a constant value, 2 is a constant value. I require the built-in potential as well. So basically what I would do, I would put the expression of XP naught in terms of W. What do I know? That my XP naught is given as W into Nd upon Na plus Nd. Say yes or no? Depletion width on P side would be proportional to Nd, right? So W into Nd upon Na plus Nd. So what I can do, this 2 epsilon divided by this Q, right? 2 epsilon is going here divided by Q, and here we are getting V built in. Is that clear? 2 epsilon into V built in divided by Q. Na let's keep here only. So W into Na. In place of XP naught, what you will put? W Nd upon Na plus Nd. So W and W would become W square. Is that clear to you? Just I am putting the expression, just mathematics it is. If you use your own pen, then you will be able to understand it. If you are just looking at the screen, then you might not be able to understand. Right? So 2 epsilon by Q, V built in, W as it is, Na as it is. XP naught is W Nd upon Na plus Nd. So W and W became W square. Right? Now this Na plus Nd divided by Na Nd goes this side. So what you are getting? W square equals to 2 epsilon by Q Na plus Nd upon Na Nd and V built in. This is what you are getting. So from here, what is the value of W you are getting? So that is coming out to be 2 epsilon by Q 1 upon Na plus 1 upon Nd V built in. So this is the formula that you need to remember. Okay, so this formula you will remember in your sorry under root I forgot. Under root will also come, no? Under root I forgot here. Under root 2 epsilon by Q. So this formula you will always remember. Okay, under root 2 epsilon by Q into 1 upon Na plus 1 upon Nd into V built in. Okay, so again we will write down and we will use this formula again and again, so eventually you will be able to remember, but a very important formula. Under root 2 epsilon by Q into 1 upon Na plus 1 upon Nd into V built in. Well and good. Okay, so this is the depletion width under equilibrium. Depletion width under equilibrium. Equilibrium. Now let's talk about, let's just say I am having P plus plus N junction. What is the meaning of P plus plus N junction? That means Na is very greater than Nd. Some special case we are seeing, nothing else. Na is very greater than Nd. That means 1 upon Na would be very lesser than Nd. 1 upon Nd. Say yes or no. So what will be the depletion width formula? The depletion width formula would come out to be under root 2 epsilon by Q under root 2 epsilon by Q 1 upon Na. Sorry, 1 upon Na is very less than 1 upon Nd. What does that mean? Only 1 upon Nd I will get. Basically this value is very much larger than this value. So 1 upon Na could be ignored, no? If Na is very large, that means this value will be very low. So very low plus something, 1 plus something, 1 plus 10 to the power 4, nearly it would be equals to 10 to the power 4 only, no? Right? So this can be ignored. What you will be getting? 1 upon Nd into V built in. So this formula you can get, right? Let's not put it in the box. You can simply see, like, this is just an observation. And what if I am using P N plus plus junction? So there is very much higher doping of what? Nd. So Na is less than Nd. So 1 upon Na would be very greater than 1 upon Nd. Right? So what will be the formula? Eventually the formula will be under root 2 epsilon by Q 1 upon Na into V built in. So this is the depletion width formula. Let's not put it in the box. We can simply remember it. Sorry, no need to remember. You remember this formula only, and based on that you can derive it. Okay, so they are known as one-sided PN junction. So in Niemann they are separately mentioned. That's why I am just writing it down here. One-sided PN junction they are known as. Why one-sided PN junction? Because on the one side there is very high doping. And what you can see here, Na is very greater than Nd. That means your W depletion would nearly be equals to Xn only. Why is that so? Because P side very high doping, that means very less depletion width. So most of the depletion width would be coming towards Xn only, and here most of the depletion width would be coming towards Xp only. So if P N plus plus junction is there, no, so your whole discussion would revolve around P only, because your depletion width would be towards the P side only. Even in the formula of W depletion, you are using Na only. Are you able to understand this point? So your whole discussion will shift towards P, and here your whole decision will shift towards N. Although they are not separate topic, in Niemann it is mentioned separately. So just I wrote down here, nothing else. And in this case, what will be your Xn XP? Xn naught I should say, because we are talking about equilibrium condition. So from here, can you find out Xn naught? Yes, that would be equals to W into Na upon Na plus Nd. And can you talk about xp naught? So that would be equals to W into Nd upon Na plus Nd. Right? So this will be your xn naught, this will be your xp naught. If I have find out W, then I can find out other things as well. So what all formulas you need to remember? Every formula I will write down here. So these three formula you need to remember. What is the formula of Emax you are getting? Before that, one charge neutrality condition also I will remember. What is that? Sir, Na into xp equals to Nd into xn. Is that tough to remember? Absolutely not. Na into xp equals to Nd into xn. Total positive charge here, Q into Nd into A into xp. Sorry, Q into Na into A into xp. So Na into xp equals to Nd into xn. Not very tough to remember, very simple thing, right? What was your Emax we were getting? Sir, area of Qna xn, right? What will be the area? Sir, it would be Qna, total positive charge here, multiply with the width Qna xp divided by epsilon, or total negative charge Qnd. So this is charge per centimeter cube, charge per volume, multiply with xn divided by epsilon. Sir, what is the formula of built-in potential? So previously we got the formula kT ln NAND by Ni square, right sir? But this time here we got another formula. What was that? Sir, half into base, base was width, half into base into height. What was the height, sir? E naught max, that was the height. Okay sir, what is the formula of depletion width? Sir, two formula we saw, sorry, only one formula we saw, that is only one formula was there, 2 epsilon by q into 1 upon Na plus 1 upon Nd multiply with V built. Okay, 2 epsilon by q into 1 upon Na plus 1 upon Nd multiply with V built-in potential. Along with that, other things also you can see that my xp naught would be equals to W into Nd upon Na plus Nd, just in the inverse proportion. Similarly, your xn naught would be equals to W into Na upon Na plus Nd. And I surely know this thing that xn naught plus xp naught would be equals to W as well. And this is also P naught, P naught. Okay. Can we see more things from here? If someone wants to remember E naught max, then it would be equals to 2 into V built in divided by W. Right. So a lot of formula could be derived, but on a top level, this slide you need to revise, and your all the formulas will be revised. Is there anything that we are leaving behind? Let me check if there is any formula that we have left. N into P equals to Ni square, that we already know, and this was the formula. That's it. So on top level, like most of the people do, they remember this slide only and they try to solve the gate PYQs, and most of the PYQs will be solved. But if they want to frame a very good question, then I guess they would frame from here. They would ask the electric field here, right? They can ask the potential between any two random point. What if they ask me the potential between this point and this point? This is the built-in potential that I have calculated. 1 by 2 W into E naught max. This is the built-in potential. That means across the semiconductor, what is the total potential that we are getting? This is what I have calculated. That is my built-in potential. But what if I ask you the potential between any two random points? So that also I can do, no? So we have framed a question. Now whatever that has been mentioned in this particular problem, from PN junction under equilibrium, apart from this, no question can be framed. Only from this problem, only from this particular concept, only questions will be framed in PN junction. That I can guarantee you. So you solve this question and your whole chapter is revised. Not chapter, your whole topic is revised. So I will leave it up to you. You can do it on your own. Here are the answers. These are the answers. Okay. So these are the answers. You can do one by one. So let's get started with the built-in potential first. So what is the formula of built-in potential? So I directly remember kT ln NAND by Ni square. What I would see, so temperature I would see first. 300 Kelvin is given. 300 Kelvin is given. So I don't need to care about this kT value. kT by Q it would be. So here also kT by Q. Again and again, this is something that I forget again and again. kT by Q it would be. But never ever we are going to put the value of kt. What we are going to put? We are directly going to put 0.026, right? So did they mention about the vt value? Did they mention the value of vt? No. So we will take, it is 0.0259 volt. Okay, ln na and d. What is the value of na? Na into nd would become 10 to the power 31 divided by ni square, that would be 10 to the power 20, 10 to the power 16, 10 to the power 15, 10 to the power 20. Okay, so this you will solve and you will get the answer. Zero two five nine, 0.656 volt, 0.6548 they are giving, so 0.656 also you can get, whatever it is, volt. Okay, so this is the answer of first one. What about the second one? In second one, what they are asking? Depletion width they are asking, depletion width. So I will solve every question such that it is a separate question. Let's just say in the examination they mentioned all the values and only they asked about a built-in potential. Now they are asking about depletion width. So only one formula I know about depletion width. Sir, only one formula that I know, that would be under root 2 epsilon by q. I would apply this formula, sir. And just as I apply this formula, what I would get to know? Just I am applying this formula, 2 epsilon by q upon multiply with 1 upon na plus 1 upon nd multiply with V built-in potential. So just as I apply the formula, I will get to know that I need to find out the built-in potential as well. So built-in potential also I will have to find out. So if I need to solve option B, that means I need to find out built-in potential as well. So this calculation also I will have to do. So what I would do? This is something I would do. Okay. Take epsilon. Epsilon is 11.7 into 8.85 10 to the power minus 14 farad per centimeter. So look at the calculation very carefully. Okay, here calculation is very important matter of concern. Farad per centimeter, everything is going in centimeter. Even na and d if I put, that also I will put in centimeter only. So everything is going in centimeter. What is q? That is in coulomb. So I don't need to care about this coulomb. But wherever the length will come into action, length will always be in centimeter. Okay, length will always be in centimeter. So what is the value of na? Na is 1 by 10 to the power 16 centimeter cube inverse. So 1 by 10 to the power 16 plus 1 by 10 to the power 15 and built-in potential 0.656. Okay, so what it would become? 10 by 0.1 by 10 to the power 15. 1 by 10 to the power 16 is there. So 1 by 10 into 10 to the power 15. So 1 by 10 is 0.1. So 0.1 divided by 10 to the power 15. So 0.1 plus 1, that would be 1.1, right? So calculation is very high matter of concern. So you just look at me and I will tell you how I would do the calculation in the examination, because 90% of the guys, if they are doing this particular question in the examination, they will mess up in the calculation. So we need to have the patience. Okay, 2 into 8.85 divided by 1.6 into 10 to the power minus 19, 1.1 divided by 10 to the power 15 into 0.656. Okay, now what I would see? Sir, 10 to the power minus 4, here I am getting 10 to the power minus 10. What this would be? 10 to the power 15, 10 to the power minus 19. So this would become 10 to the power minus 4. 10 to the power minus 4, upper side 10 to the power minus 14 you are having. So 10 to the power minus 10 you will get. So under root 10 to the power minus 10, that would be 10 to the power minus 5. But what if I was getting 10 to the power minus 11? What I would have done then? If somehow I was getting 10 to the power minus 11, then what I would have done? So what I would have done? I would have adjusted it in this manner. 10 to the power minus 1 into 10 to the power minus 10. Is that clear to you? So somehow I would have adjusted this 10 to the power minus 1. Is that clear to you? Is that clear what I am saying? Although here luckily 10 to the power 15, 10 to the power minus 19, that would become 10 to the power minus 4. And this is 10 to the power minus 14. So 10 to the power minus 14 divided by 10 to the power minus 4, that would become 10 to the power minus 10. And luckily I will be able to take 10 to the power minus 5 outside. But if it was 10 to the power minus 11, then this is how I would have adjusted. Okay. So now what I can see, 2 into 8.85 divided by 1.6 into 1.1. अरे यार 2 into 8.85 into 1.1 into 0.656 divided by 1.6. Then you take the under root. So 2.82. So 2.82, 2.82, 10 to the power minus 5. What I will write down here now? Centimeter, meter, micrometer. What I will write down? Centimeter. Because all the calculation were going into centimeter itself, right? Are you able to understand this point? Is that clear to you? So what is the answer we are getting? Calculation error. Okay, what is the calculation error we have done? We forgot to put 11.7. So I said that 90% of the guys would be doing the calculation error, and I belong to that 10% only. Sorry, not 10%. I belong to that 90% only, those who will be doing the calculation error. Okay, so I also did the calculation error. What calculation error I did? I forgot to put 11.7. So I am no different. Okay, during my gate attempt as well, like I matched up at least 20 marks. Okay, 20 marks because of the calculation error only. Same goes for my JE attempt as well. Even in the JE attempt, I matched up the whole question paper just because of the calculation errors. Concepts and all, I am pretty confident about myself. But when it comes to calculation, you would see that those who are studying more subjects from me, not only EDC, so those who have studied from a longer time from me, they would notice that I use calculator even for smaller calculation. Okay, so this is a problem with me. 11.7 under root 2.82, 9.64. Okay, so yeah, 9.645. What we are getting? 9.645 into 10 to the power minus 5. Here what I will write down? Centimeter, because everything I took in centimeter, right? Everything was going into centimeter. You see this particular value, this was also in centimeter, this was also in centimeter. So everything was in centimeter. That's why answer I am getting in centimeter. Is that clear to you? So what I can write down? 9.646, sorry, 9.645 into 10 to the power minus 7 meter. Okay, is that clear to you? Now this 10 to the power minus 1 goes here, so it would become 0.964 micrometer. Is that understandable? Okay, so this is the depletion width we are getting. Depletion width under equilibrium, so W naught I can put. So 0.964 micrometer. Although they did not ask XP naught, XN naught, but still we can calculate it, right? What would be your XP naught? So that would be depletion width on P side. So 0.964 into ND. What is the value of ND? 10 to the power 15. Plus 10 to the power 50. 0.087. 0.0876 micrometer. So this will be your depletion width towards the P side. And now what will be your depletion width towards the N side? Although they did not ask it, but still I can calculate. Do I need to do any calculation? What is the ratio here? Na ratio Nd. What is your Na ratio Nd? So that is 10 to the power 16 ratio 10 to the power 15. That is 10 ratio 1. So what do you think? What will be your XP naught ratio Xn naught? That would be 1 ratio 10. So it would be 10 times of this. So what is the answer you will be getting? 0.876 micrometer. Is that clear? So this is the thing we are getting. Although they did not ask it, but still we have calculated. Now option C, electric field. So in the examination, if electric field is asked, what they are asking, maximum electric field they are asking. Find the electric field in the PN junction. At the junction they are asking. At the junction they are asking the electric field. That means at the junction I know that at the junction E field is maximum. So what would be my E naught max? So what would click to me first? the diagram would click to me. Sir, your E naught max would be, sir, QNA into XP divided by epsilon. This thing would click to me, and then here QNA. I don't know why I again and again write down ND. QNA XP divided by epsilon, XP naught I can put. So this is the first thing that would click to me. Now if I have solved these two things, then what else could click to me? So if this is clicking to me, then what do I know? I know the value of Q, I know the value of Na, I know the value of epsilon. For calculating the value of epsilon, what do I require? Sorry, for calculating the value of XP naught. For calculating the value of XP naught, what do I require? I require the depletion width, right? Because I know that XP naught would be equals to depletion width into ND upon Na plus ND. And to get the value of depletion width, what do I need to require? What do I require? 2 epsilon by Q into 1 upon Na plus 1 upon Nd. And here I require my V built in. Are you able to understand this point? In the examination, only this particular thing was asked, that you need to find out the E field. So first thing that would click to me, so QNA by epsilon XP naught. This is what it would click to me. Then I would know that I need to get the value of XP naught. XP naught is not given. I need to get the value of XP naught. For XP naught, I would require W depletion. For W depletion, I would require built-in potential. That means eventually I will have the built-in potential value as well, and I will have that depletion width as well. So better than that, what do I remember? Sir, my V built-in was half into base into E naught max. Say yes or no? So in the examination, first this would click to me, but from the requirement, I would solve my question in this manner. Is that understandable to you? So from here, what I would do? Sir, my E naught max would come out to be 2 into V built-in divided by depletion width. 0.656. Depletion width. What is your depletion width? 0.964. Answer would come out to be volt upon micrometer, right? Volt upon micrometer. This is your micrometer. So what you would see, 2 into 0.656 divided by 0.964. 1.36 micrometer. Yeah, okay. So 1.36 volt per micrometer. What if the answer is mentioned in volt per centimeter? So what you can do? 1.36 volt per micrometer could be written as 10 to the power minus 4 centimeter. So answer would be 1.36 into 10 to the power 4 volt per centimeter. This would be your E naught max, right? From here also you could have find out what you need to do. 1.6 into 10 to the power minus 19. Na value is 10 to the power 16. XP naught. So everything is going in centimeter. So this also I will write down in centimeter only. That would be 0.964 into 10 to the power minus 4 centimeter divided by epsilon. What will be the value of epsilon? Epsilon will be 11.7, 8.85 into 10 to the power minus 14 farad per centimeter. So everything is happening in your centimeter only. So volt per centimeter answer you will be getting. So this you can solve. You will also get the same answer only, 1.36 into 10 to the power 4 volt per centimeter. Okay, well and good. So A, B, C all are done. So did you understand what will click to me in the examination and how would I proceed in the examination? Now the next question, I am leaving it up to you. I hope you would be able to do it. You need to find out the electric field at minus 2xp by 3 point and at 2xn by 3 point. So try finding out the electric field. Do it on your own. What I would do, I would make the setup. Okay, Na is there, Nd is there, PN junction is there. At x equals to 0, they are considering the junction. So minus xp plus xn. So what I can do, I can make up the setup and I would get to know what they are trying to ask me. Okay, so let's make the setup and then I will be able to get that potential difference as well. So what I would do, I would make a setup of my PN junction. This is my x equals to 0. This is your p side, this is your n side. You can see that doping is more in the p side and lesser in the n side. So depletion width also on p side depletion width would be lesser, and on n side depletion width would be more. This depletion width would be lesser and this depletion width would be more. So this is your xn node and this would become your minus xp node. Okay, and this is your x equals to 0. What I can do? Everything would come down to only one guy, and that guy is volume charge density. If you are able to plot volume charge density, your job is done. After that, everything is mathematics. So surely, sir, I will be able to plot my volume charge density. Sir, here I am having negative charge, and then I would have positive charge. Sir, QNA value is more than QND value. So I will make the diagram in a better manner. What would be the better manner? This would be the better manner. Okay, understandable, right? And next, what I need to do, I simply need to integrate it. Okay, so when I integrate, integration I am putting down here. So I am making a bigger diagram actually. This is my XP node. Let's make it even more bigger. This is my XP node. Okay, and this would be my XN node. So when you integrate, this is what I will be getting. So integration would throw this value would become QNA XP node divided by epsilon. Why divided by epsilon? Because you know that this is my electric field versus X. Okay. So where you need to find out the electric field this time? I need to find out the electric field at minus 2xp by 3. So where will be my minus 2xp by 3? Here will be my minus 2xp by 3. At this point, I need to find out the electric field. Right. So can anyone find out? Mathematics it is. What I need to find out? E of x at minus 2 xp node by 3. If someone is smart, if someone is very smart, what he would know? That if you are working for xp node distance, then this much decay I am having in electric field. Mathematics, again mathematics. When I am working for the distance of xp node, this much decay I am having. So when I work for the distance of 2 by 3 xp node, then how much decay I would have? 2 by 3 of this one. So answer would simply come out to be 2 by 3 decay you would have. That means what will be left? 1 by 3. QNA xp node divided by epsilon. Those who are not able to understand this, what they need to do? They need to write down the equation of this line. Can you write down the equation of this line? What will be the equation of this line? So first I need to see the slope. Slope is negative. So what will be the slope? The slope would be minus QNA upon epsilon. This would be the slope, right? Y by x. X is xp node. Xp node will get cancelled out. Minus QNA by epsilon. That would be the slope. And at x equals to 0, what is the value we are having? This value we are having. So what value we will be getting? And this value is actually negative, right? So plus xp node. So this would be the equation of the line. This is the equation of Ex. Writing down the equation I am leaving up to you. And you can check as well at x equals to 0. If you put x equals to 0, what you are getting? Minus QNA epsilon x plus xp node. Right? So this is the equation of electric field from minus xp node to 0. Okay. This is the expression of electric field from minus xp naught to 0. This is the expression we are getting. We need to check at minus 2 xp naught by 3. So here I will put minus 2 xp naught by 3. What I will be getting? Xp naught by 3 multiply with this one. So my answer would come out to be minus qna xp naught by 3 epsilon. So it is equals to your E naught max by 3. Right? So what is your E naught max? E naught max came out to be this one divided by 3. So that would be the answer. You can see that E naught max divided by 3. This is the answer we are getting. So when you divide it by 3, that same answer you will get. So 1.36 divided by 3. So roughly around 4.5 into 10 to the power 3 volt per centimeter. Is that understandable to you or not? What do you say? And sir, directly how did you write down this expression? Directly just think about it. No, what is the meaning of slope? When I am going from x equals to 0 to xp naught, my magnitude is going from this much to 0. That means when you work for a distance of xp naught, you lose this much of amplitude. So when I work for the distance of 2 by 3 xp naught, then how much amplitude I will lose? 2 by 3 of this time, that means how much will be left? 1 by 3 of this time, no? So answer would come out to be 1 by 3 q na xp naught divided by 3. Is that understandable to you or not? I hope it is understandable. Next, where I need to find out? Here I need to find out. So what I can do? Again, I can find out the equation, but like if someone is having the brain, he would know that sir answer would come out to be same. Or what someone can do? He can find out the equation. Or what someone can think that if you are working for a distance of x naught, then this much you are losing. Okay, same answer would not come out. Okay, wait a second. I don't think same answer would come out. At we need to find out at 2x naught by 3, right? 2x naught by 3. So this would be actually equals to q and d x naught by 3 as well. Yeah, same answer would come out actually. This value q by epsilon, q by epsilon, q by epsilon and q by epsilon. Now naxp naught could be replaced with ndx naught, right? So what I can see from here, if I am moving for a distance of x naught, then I am losing this much of amplitude. So if I move for the distance of 2 by 3 x naught, then how much amplitude I will reduce? I will reduce by 2 by 3rd amplitude. That means how much amplitude would be left? 1 by 3rd of this one. So again, if they are asking me electric field at 2x naught by 3, this is where they are asking, right? 2x naught by 3, 2x naught by 3. So that would also come out to be the same, right? That would also come out to be the same, and that would also be E naught max divided by 3 only. Otherwise, what other guys can do, they can write down the equation. If they don't want to write down this particular expression, what they can do, they can write down the expression of this electric field. What will be the expression of this electric field? So here only I am writing down from 0 to x naught. I am writing down the expression of electric field. So sir, peak value, only this value I know. So the sir, peak value is this much. And what will be the slope? So qna, sir, qna xp node divided by x node epsilon. This would be the slope. Although this would become very, very complex answer. Okay, this would be the slope. Multiply with x. And at x equals to 0, this is the answer you are getting. So what you will be writing down? X equals to 0, qna xp node divided by epsilon. Not xp node. Yeah, xp node only. Yeah, so this expression you will be getting. This kind of complex expression, if you want to write down, you can write it down. Doesn't make much sense, or someone can write down the expression in this manner, because people would be knowing that sir, this value will be equivalent to this value. So what they can do, sir, slope will be, here the slope will be positive. So my answer would come out to be q and d x naught divided by x naught. So q and d by epsilon x, and at now at x equals to 0, what I will be getting? I will be getting this much value. So q and d naught x naught by epsilon. Yeah, so this is the answer you will be getting. Okay, in both of the answer would be negative, electric field would be negative. So no need to mention that electric field would be negative only. So this kind of expression I will be getting, and what I can do, I can take q and d epsilon common, and this is the expression I will be getting. This will be the expression of electric field. It's your mathematics. Here this was the expression of electric field. This was between 0 to xn naught, this was between minus xp naught to 0, from minus xp naught to 0. So you can check as well, if I put 0 here, what I am getting, minus q and d xn naught divided by epsilon. If I put xn naught here, I am getting 0 only. So this expression is correct. And in this expression, you can put 2 xn naught by 3. If you put 2 xn naught by 3, what you are getting, q and d xn naught divided by 3 epsilon. So q and d xn naught divided by 3 epsilon you will get, which is similar to this only. Next what they are asking? They are asking the potential difference between these 2 points. Potential difference they are asking. What they are asking? Potential difference. So let me add a page and let's see what is the meaning of potential difference. Potential difference between minus 2 xp naught by 3 to plus 2 xn naught by 3. What will be the potential difference? So what you need to do? 2 xp naught by 3 to 2 xn naught by 3. Ex dot dx, and then there is a negative sign. So from here to here, basically if I just take this particular diagram on the next page, so what I need to do is that I need to calculate the area. So which area I need to calculate? From here to here they are going, no? So this much area I need to calculate. This much area I need to calculate. Right? And this much area you calculate and then put the negative sign, you will get the answer. So this much area I need to calculate, I will get my answer. Is that clear to you? Say yes or no. So are you able to understand what I am writing down here? This area would be equals to built-in potential minus this area minus this area. Are you able to understand this point? This particular area would be your answer. That would be your potential difference between minus 2 xp naught by 3 to plus 2 xn naught by 3, and that would be equivalent to V built-in minus this area minus this area. Because what will B built-in represent? V built-in would be the total area. From the total area, I subtract this area and this area. And luckily, you know that this area would be equals to this area only. Right? How much will be this area? So this area would be half into base. What is base? Base is xn naught by 3 into height. Electric field at this point. Electric field at this point. And that came out to be, sir, that came out to be E naught max divided by 3. Say yes or no. Half into base is xn naught by 3. Electric field at this point came out to be E naught max divided by 3 minus half into, what will be the base? Base here will be xp naught by 3. Multiply with electric field at this point. What that came out to be? E naught max divided by 3. Okay. So actually they are not equal. Xn naught, xp naught would be different. Right? E naught max divided by 3, like basically electric field would be same here. But this length xp naught by 3 and this length xn naught by 3, both will be different, no? Right? So what we can see, V built-in minus E naught max divided by 3. E naught max not divided by 3, y divided by 3. E naught max divided by 18. Right? E naught max divided by 18, then xn naught plus xp naught. Right? Is that clear to you? V built-in minus this much area minus this much area. So half into base. What is the base? Xn naught by 3 into height. What is height? E naught max divided by 3. Height is, this particular height was E naught max divided by 3. So this particular height was E naught max divided by 3. And this particular height was also E naught max divided by 3 only. Right? So what you are getting? V built in minus xn naught plus xp naught. What that would become? W only. So can I write it down in this manner? 1 by 9 into 1 by 2 E naught max into W. What this is? This is your built-in potential only. Half into base into height. So what you are getting? V built in minus 8 by 9, sorry, 1 by 9 V built in. So your potential difference between minus 2xp naught by 3 to plus 2xn naught by 3 is coming out to be 8 by 9 into V built in. So whatever your built-in potential was there, what was your built-in potential? 0.656 divided by, multiply with 8 by 9, 0.656, 0.583. So 0.582, 0.583. So again it was complete mathematics only, okay. In the examination till this date, in the history of GATE examination, they have asked about A, B and C, that's it. But what I expected, D and E would also be coming in the examination very soon. This was your D and this was your E. It can also come very soon. Okay, electric field at a random point in the junction, they can also ask. Potential difference between two random points in the junction, they can also ask. It's not necessary that they will always ask the built-in potential. Between two random points as well, the potential difference could be asked. And if they are asking, again, very simple, very straightforward. Pure mathematics. Instead of mugging up like line equation or this, I will simply make the diagram. I will just make the diagram, and what I will see, I will try to use my mathematics. Now, better the mathematics I am having, better probability of getting the correct answer. Okay. So I would know that, sir, this much potential, this much electric field is there at the peak. So if I go from here to here, I am losing complete electric field. That means if I work from here to here, then how much electric field I will lose. If I work from here to here, then how much electric field I will lose. So from there I will get the answer. And then I need to care about this particular potential. So I know that complete area would represent V built in. But what area I would require? I would require between minus 2xp naught to 2xn naught by 3. Minus 2xp naught by 3 to 2xn naught by 3. That means this much area I require. That means total area minus this area would do the job. So half into base xp naught by 3 into height. Height is E naught max by 3. Similarly, half into base. Base is xn naught by 3 into height. Height is E naught max by 3. Then something I would adjust and I would get to know that this is nothing but 1 by 9 V built in. So 8 by 9 V built in I am getting, that is the answer, 0.583 volt. Okay, very simple thing. Not very simple, like mathematics is complex, but there is no concept involved here. Only mathematics is involved, nothing else. So from this discussion, what did you understand? I understood that this is very important. Although no one asked about it in the examination, but if you are not able to draw charge density plot, then there is no meaning of proceeding in the problem. If I am able to draw the charge density plot, then my job would be done very easily. I will be able to answer all the questions. But if I am not able to draw the charge density plot, then it will become very difficult for me. So who is the best guy here? Who is the most important guy? No one talks about that guy, and that guy is charge density plot. Okay, it's like network analysis of your gate engineering journey, right? No one talks about network analysis, but without network analysis there is no electronics engineering. So no one talks about charge density, but without charge density there is no electronics, there is no electric field, there is no potential. So now we would see that how we can draw this particular diagram for any random kind of doping. Here uniform doping was there. This was the case of uniform doping. This was the case of uniform doping. Why uniform? Someone would say that, sir, Na is not equal to Nd, so how you are saying uniform doping? P side is uniformly doped, N side is uniformly doped. Now what I am going to do, I will take a semiconductor. Now I will do different kind of doping. Here highly doped and then lightly doped. Here highly doped, highly doped, highly doped, highly doped, and then here lightly doped. So this kind of different kind of doping I am going to do. So for that different kind of doping, what kind of graph you will get? So here what kind of graph you will get? You are drawing a charge density with respect to x. So more charge density, more, then it would become lesser. Here more charge density, more, then it would become lesser. So this kind of graph you would be getting. Is that understandable to you? More to less, more to less. Oh, this was positive charge, this is negative charge. So opposite diagram I will get. What I would get? Here we are having positive charge, no? So positive charge, then zero charge, right? And then here there is more charge to zero charge. So this kind of diagram I will get. Are you able to understand this point? Okay, so this kind of things we are going to check. Surely we will check it, but after a break. So after a break, I will tell you a certain method that how you can draw the charge density plot. So as an important note we are putting, what we are putting, we need to consider that how would I draw the charge density plot, volume charge density plot. So, but after a break, you also drink some water, I will also drink some water, and then we will come back. We will study about charge density plot. Okay, yeah, welcome back. So now we are going to focus on charge density plot. So volume charge density plot we need to make. So for this particular PN junction, this was your P side, this was your N side. This time what I am doing, P side is highly doped, not plus, only plus I will put. P side is highly doped and N side is lightly doped. So why we are focusing so much on volume charge density plot? Because if I am able to draw the volume charge density plot versus X, then I will be able to comment on the electric field as well, and I will be able to comment on the built-in potential as well. So this is a very important plot, right? So for this particular diagram, it is very easy to understand that, sir, here also uniform doping is there, here also uniform doping is there. So for x less than 0, I will be getting negative charge. For x greater than 0, I will be getting positive charge. Here, sir, the width of N side, the depletion width on the N side would be more than the depletion width on the P side, because here there is light doping. So it is very easy to understand, but let's build up a certain method. Like no matter whatever kind of doping is given, we will build up a certain method. Using that particular method, we will be able to draw this diagram very easily. So let's build up that method. So what may happen in the examination, this plot may be given. This is your carrier concentration plot. I should not say carrier concentration plot. This is your doping plot, doping profile. Okay. This is a doping profile, not carrier concentration plot. This is your doping profile. What does that mean? That means that you are having a semiconductor, you are having a particular semiconductor, then midpoint I am putting as x equals to 0. For x less than 0, you are doping acceptor atoms. For x less than 0, you are doping acceptor atoms. And for x greater than 0, you are doping donor atoms. And the acceptor atoms are more than the donor atoms. This is what you can conclude from this particular doping profile. Here I am doping Na, here I am doping Nd, right? That means here I am doping negative charge hole, and here I am doping positive charge electron. This is the doping I am doing, and Na is greater than Nd. Now what do I do? I will draw the graph of Ndx minus Nax. What graph I will draw? Sir, I will draw the graph of Ndx minus Nax. Why I am drawing the graph of Ndx minus Nax, you will be able to understand. Just have some patience. What do you think what Ndx minus Nax would represent? What is your Ndx? Ndx is this thing. And what is your Nax? Nax is this thing. If they have lost their charge carrier, let's just say the donor atom has lost its electron and the acceptor atom has lost its hole, then what it will become? It will simply become a positive charge, it will simply become a negative charge. Now I know that, what is my matter of concern? My matter of concern is depletion region. Now I know that in the depletion region, I will either get positive charge or I will either get negative charge. Either positive charge I will get or negative charge I will get. So that means if I am drawing Nd minus Na, so effectively what I am drawing? I am drawing effective positive charge. Are you able to understand this point? Let's just say for this particular profile, if I draw Ndx minus Nax, what kind of result I will be getting? For x less than 0, is there any donor atom? No, only acceptor atoms are doped. So for x less than 0, what I am saying, for x less than 0, ndx is 0 and nax is equals to na only. That means for x less than 0, ndx minus nax would be equals to minus na. 0 minus na would be equals to minus na. That means, what do you understand from here? I understand that for x less than 0, acceptor atoms are doped. And for x greater than 0, what is the scenario? For x greater than 0, ndx equals to nd only and nax equals to 0. So this point would be my minus na, and for x greater than 0, I will be getting plus nd. Is that understandable to you? 0 minus na would be minus na, nd minus 0 would be equals to nd. If I multiply this particular graph with q, what I am getting? I am getting that if I multiply this particular graph with q, I am getting, here I am getting total negative charge and here I am getting total positive charge. If I have multiplied this particular graph with q, I am getting total positive charge here and total negative charge here. Basically, here I am doping only this thing and here I am doping this thing. I don't want to think anything. Okay, in the examination, my brain is not working. If it is not working, what I would think, that I would draw positive charge minus negative charge. That means ndx minus nax I will draw. ndx minus nax I am drawing. Here minus na I will be getting. Here plus nd I will be getting. If I multiply both of them with q, that means here I am getting total positive charge. Here I am getting total negative charge. But I know that before depletion region, that means from minus infinity to minus xp, I will not get any charge because this particular side is electrically neutral and this particular side is also electrically neutral. That means my matter of concern is not from minus infinity to minus xp. My matter of concern is only from minus xp to 0. My matter of concern is only from minus xp to 0 and then from 0 to xn. So this much is my matter of concern. Only my matter of concern is from minus xp to 0 and from 0 to xn. Only this much is the matter of concern. Only this much is my matter of concern. Rest all is not a matter of concern. Is that understandable to you what I am saying? Because negative charge and effective positive charge, I will be getting only this much of a distance. From xn to infinity, I am not getting any positive charge or negative charge because it is neutral. And this particular side is also neutral. So what I need to plot? I need to plot charge density, volume charge density. So here I am getting negative charge, here I am getting positive charge. How much positive charge I am getting? I am getting positive charge equals to q and d. How much negative charge I am getting? I am getting negative charge equals to minus q and a. Can I comment on xp and xn? Yes. What do I know? This particular area would be equals to this particular area. Let's just say this area is a1 and this area is a2. So what a1 would represent? What a1 would represent? A1 would represent total negative charge per unit area. Say yes or no? Because minus q na xp, this would be the total area, right? Minus q na xp, this would be the total negative area here. What does that mean? Na is per centimeter cube. This is your charge coulomb and this is centimeter. That means you are getting charge per centimeter square. In one area, how much total negative charge you are having? And what would A2 represent? A2 would represent total positive charge per unit area. This is what A2 would represent. And I know that for electrical neutrality, since this particular semiconductor will be electrically neutral, for neutrality, A1 has to be equals to A2. For neutrality, A1 would be equals to A2. And from there, I would be able to get the relation between xn and xp. Right? Basically, from here, what I will get to know is that my q na xp is coming out to be equals to q nd xn. So if I am given the value of na and nd, then I will be able to comment on the value of xp and xn as well. Is that understandable to you? Like all these things I already know, but I am taking a simple example to solve some complex problems. Now what kind of complex problems? This kind of question is surely coming in your GATE examination in future. I am putting 27 or it can come in 26 as well. So let's put 26 or 27. Surely it is coming. It is a PN junction only. Okay. This was the semiconductor I was having. Now what is the scenario? This is my x equals to 0. Here I am doing the doping. But this time I am not only purely doping Na. This time what I am doping? I am doping Na as well. I am doping Nd as well. But in this particular region, Na is more than Nd. You can see the graph. This is the graph of Na. This is the graph of Nd. This is the graph of Na. This is the graph of Nd. But you can see that here Na is more than Nd. And in this particular region, Nd is more than Na. So in this particular region, Nd is more than Na. If Nd is more than Na, what does that mean? It is N type. And if Na is more than Nd, what does that mean? It is P type. So this particular side for x less than 0, it is known as compensated P type. For x greater than 0, it is known as compensated N type. So for x less than 0, you are having positive charge as well, negative charge as well. For x greater than 0, you are having positive charge as well, negative charge as well. But here, who will be dominating? This guy will be dominating. And here, who will be dominating? This guy will be dominating. So again, carrier concentration should not be written. What should be written? Doping profile should be written. Like in the examination, if Nd minus Na plot is given, then you will be very happy because you will not have to do this process now. Now, what is given? Doping profile is given. That for x less than 0, this is how we are doping. For x greater than 0, this is how we are doping. It might happen that in the examination, they don't even give you this graph. They can simply write down for x less than 0, this kind of doping is there, this waveform would be there, this waveform would be there. For x greater than 0, this waveform would be there, this waveform would be there. So they might not even give you the graph. They will just tell you what kind of doping we are doing, and then with respect to that, you find out the depletion width. Okay, depletion width is given, total depletion width is equal to W. With respect to that, you find out the maximum electric field and built-in potential. This kind of questions they can directly ask. So what did I tell you? I will always draw rho Vx. My target is drawing volume charge density. If I am able to draw volume charge density, then my problem is solved. What is my target? My target is drawing rho Vx versus x. This is something that I need to draw. That's it. This is my target. So how will I draw it? First, I will always think of ndx minus nax. So what is my ndx minus nax? So ndx is always 10 to the power 15. Nax is always minus 10 to the power 16 plus 10 to the power 15. Right? So what will be your ndx minus nax? You can see from here 10 to the power 16x. It would come out to be 10 to the power 16x centimeter cube inverse. That means, sir, my plot of ndx minus nax, this point I am calling as x equals to 0. This point I am calling as x equals to 0. Okay. So my plot would look something like this. My plot would look something like this. This is my plot of ndx minus nax. Say yes or no. Okay. What does that mean? What kind of PN junction I was having? Sir, in PN junction, this was my x equals to 0. On this side, what kind of doping they did? On this particular side, what kind of doping they did for x less than 0? You can see that Na is very, very high here. Na is very high and Nd is this much. So, Nd was uniformly doped here. Here, Nd was uniformly doped. That means this was the doping of Nd. But what really happened with Na? So, Na was doped like this. Okay. Are you able to understand this point? Right? So, what really happened? The negative charge here is cancelling out the effect of a positive charge. Like, do you remember the thing? Like, what will be the number of holes? That would be Na minus Nd. In compensated P type, what will be the number of electrons in compensated N type, that was equals to Nd minus Na. Do you remember all this expression? Actually, the expression came out to be Na minus Nd by 2 plus under root Na minus Nd by 2 whole square plus Ni square. Then we say that this particular part would be much greater than Ni square, so this particular part you can ignore. In that manner, we get the answer. Basically, which particular part you can ignore, this particular part you can ignore, and then we get the answer as Na minus Nd. Right? So this kind of doping they are doing, and they are making it compensated P type, and they are making it compensated N type. So effectively, how much negative charge do you see? Here, effectively, more negative charge you would see, then lesser negative charge, and coming to this particular point, zero negative charge. And similarly, on the other side, you can see that Na doping is going down. Na doping is going down, but Nd remains the same. So what does that mean? That here you would see more positive charge, sorry, lesser positive charge, then positive charge would keep on increasing. Why is that so? Because Na doping is going down. That means negative charge doping is going down, but positive charge doping remains the same. What does that mean? That this kind of a waveform I will see. Positive charge is piling up. In the examination, we will not be able to think this much. That's why we have developed a method that we will always draw Nd minus Na. This will be our matter of concern always. So just remember the method. What is the method? That draw Nd minus Na. Why we are drawing Nd minus Na? Just to explain this particular part, I am explaining this much. Why we are drawing Nd minus Na? Because we are considerate towards the positive charge. Okay, so Nd minus Na is showing total positive charge. Now here Nd minus Na is becoming negative. That means total positive charge is negative. What does that mean? That means actual charge is negative. What does that mean? That means this particular side for x less than 0, this is P type and this is N type. Is that understandable to you? I hope it is very easy for you. Okay, but this is not the final plot I require. What is the final plot I require? Finally I require the plot of volume charge density. This is the final plot that I require. So what I will do? I will multiply this with Q. I will multiply this with Q. Right? Now the whole side will not get into depletion, no? Like let's just say only this much side will get into depletion. This is my minus XP, and from here some side will get into depletion. That could be Xn. So we need to find out the relation between Xn and XP. So that we will do. So what I need to do, I need to multiply it with Q. So what I will get, like what is the equation of this particular line? That is 10 to the power 16x. So if I multiply it with Q, what I am going to get? 10 to the power 16x multiply with Q. Right? So this particular thing would be 10 to the power 16x multiply with Q. Now what is my matter of concern? If you see here, matter of concern is from minus XP to 0, from 0 to Xn. That means my matter of concern would be between minus XP to plus Xn. Only this much matter of concern would be there. So I need to see how much positive charge I am having in this particular region and how much negative charge I am having in this particular region. So what does that mean? That means what value you will be getting? Sir, here the value that I will be getting would be 10 to the power 16 at minus XP. So if I put minus XP here, multiply with Q. So this much value you are getting at this point. And what about this particular scenario? Here you are getting the value of 10 to the power 16 Xn into Q. I think I should make this diagram a bit bigger on the next page. Okay, let's make the same diagram a bit bigger. Like if you see these kind of problems in other lectures, then you would just see that they have taken this particular waveform directly and then they are deriving some equations and all those things. So that will not be helpful in the examination. In the examination, numerical problem would come up. So you need to have the temperament to solve numerical problem. How would you solve a numerical problem if it is not a standard PN junction? It is not necessary that always they will give standard PN junction, or they can give any kind of doping. So if any kind of doping profile is given, always I will draw Nd minus Na. If I am able to draw Nd minus Na, just multiply with Q, and then I know that depletion bits would be between minus XP and plus Xn. That's it, my job would be done. And I know the waveform of this particular line, the waveform is 10 to the power 16 x. So I don't need to write down. I'm just writing down what would be this point. So this point would be Q into 10 to the power 6 Xn. and this point would be q minus q into 10 to the power 6, 16, not 6, xp. So this is with respect to x. So what I have drawn here, q into nd minus nax, this I have drawn. nd minus nax, this is something I have drawn. Now what this area would represent? This much area. This much area would represent that total positive charge. And what this much area would represent? This much area would represent the total negative charge. That means what I will do now, I will equate total positive charge with the total negative charge. And one thing I also know that xn plus xp is given as w. Total depletion width is given as w. And another thing what I can do is that, sir, this much area is actually representing the total negative charge, and that has to be equals to total positive charge. Since it is charge only, so total negative charge, this will come out to be negative. So let's remove it. So this is your total positive charge, this is your total negative charge. So q into 10 to the power 16, and that is getting cancelled. From here you get to know that xn is equals to xp. What does that mean? That means xn will be w by 2 and xp would also be w by 2. So this width, like this particular portion would be having half width, and this particular portion would be having another half width, which is pretty obvious as well, because you see the doping profile. Like negative charge, negative charge, negative charge, it is going down. Then positive charge, positive charge, it is going up. The system has to be electrically neutral. The device has to be electrically neutral. That means whatever the charge I will contain here, the same amount of charge I will contain here. So if I need to move for this much of distance to get my negative charge, that means the same distance I need to move for positive charge as well. Very simple thing, no? Just by looking at the graph you can say. But what if the graph was like this is having a slope of this much and this is having a slope of this much, and this point is my xp, and let's just say this point is my xn. So what do you think, what will be more, xn or xp? If I am saying that, sir, graph as of now the line was linear having the same slope, but what if the slope was something like this? What if the slope was something like this? For negative charge this was the scenario, and for positive charge this is the scenario. That means more negative charge you are getting, but lesser positive charge you are getting. Lesser positive charge you are getting. That means to cover the same amount of positive charge, you need to move more. So xn would be more than xp here, right? We just need to care about the total area. In the total area, how much positive charge is there, that should be equal to the total negative charge. If I have equated both of them, my job is done. Luckily here linear graph is there. In the gate examination as well, first they would ask linear only. Just as they have asked linear, next year non-linear graph would come up. But till this date they have always asked about this particular graph only. Till this date they have asked till this point only, till C. Okay, so slowly they will build up the level. When they build up the level, then next they would ask these kind of things, that they will start asking electric field at a particular point. Then they will start asking potential between two particular points, and then they will start asking this kind of questions. So slowly the level will be built up, no? And when they have asked this kind of questions, then what they would ask, what they would do, here there is different kind of profile and here there is different kind of profile. That means they will change the slope as well. So directly it will not be built up that, sir, directly they are asking this kind of profile. That's why we are not solving this kind of question. But the day they ask this kind of question, next year you would see that in my lecture this kind of question would be framed. But as of now, why we need to form this kind of problem? Because I am pretty sure that if they are going to ask, they will give you the linear profile, and directly you would see that my xn and xp is coming out to be w by 2 and w by 2 only, because in the Niemann as well the same scenario is given. Okay, so they will frame it from Niemann only, so the same scenario would be given. Most probably always the slope would be same. That means xn would be equals to xp would be equals to w by 2. But what if they change the slope? If they change the slope, then this kind of scenario would be there. I don't need to mug up anything. Only thing I need to remember is that my matter of concern would be that I draw nd minus na, then I multiply with q. My target would be that I always make positive charge equals to negative charge. That's it. And from there I would get the relation between xn and xp. Is that understandable to you or not? Surely it is understandable. Okay, so what this particular charge is showing, what this particular graph is showing, this particular graph is showing Coulomb per centimeter cube. So what it is your simply volume charge density. This is showing your volume charge density, right? So xn equals to xp we are getting. Next, what I need to find out? I need to find out E naught max. So what do you think? What will be the value of E naught max? For finding out the graph of electric field, what I need to do? What is my Ex? Sir, my Ex is minus infinity to x rho Vx by epsilon dot dx. So you integrate this particular graph. And find out the maximum electric field that you are getting. So what do you think, where I will get the maximum electric field and what will be the value of that maximum electric field? It is completely mathematical now. Whatever that we need to do now, next part would be only mathematics. Electronics has ended, now mathematics would start. So what do you think, what will be the answer? Sir, the maximum electric field, would simply be either this area or this area. Are you able to understand this point or not? Either sir this area or this area, because both areas are equal only. Let's draw the electric field graph. How would I draw the electric field graph? What I need to do, I simply need to integrate and then divide by epsilon, right? Integrate with respect to x and then divide by epsilon. That's it. So let's start integrating. This is minus w by 2 and this is plus w by 2. So till minus w by 2 everything is 0. And now we will start integrating. We will start integrating from here. So negative area will keep on building up. Then sir, what will happen? Then positive area will start coming. Positive area. Sir, eventually negative area and positive area both will cancel out each other. So electric field would go to 0. So this kind of graph we will be getting. Are you able to make this graph or not? Let's make this w by 2 a bit here. Sir, negative area. Then negative area will peak here. So this negative area will peak here. Then what will happen, sir? Now in the negative area, positive area will start adding up. So positive area, it will keep on adding up. Eventually at w by 2, the total positive area would be equal to total negative area. So total area would become 0. So this kind of integration I would get. Okay. I hope you are comfortable with this much of mathematics. So what will be this point? What do you think? What will be this point? This point would simply represent, this is my Ex, and this point would simply represent the maximum value of electric field. They will always ask the magnitude. Okay, what they would ask? They will always ask the magnitude. So what do you think? What will be magnitude? Do I need to write down the equations here? No. If I only need to find out the E naught max, do I need to write down an equation? No. I know that this particular point will be simply equals to this much area. What that would be? Sir, half into this base w by 2, because it is a triangle, into height, that would be q into 10 to the power 16 into xp. So what is xp? Xp is simply w by 2 only. So what is the answer we are getting? And surely we will never forget dividing by epsilon. Okay, here epsilon will also be divided. So a lot of time this happens with me, that I only write down the area but never ever forget dividing by epsilon. Okay, so what you are getting is that q into 10 to the power 16 divided by epsilon. Now sir, w by 4. Now this will also be w by 2. Xp would also be w by 2. So what we are getting? Q into 10 to the power 16, 8 epsilon w square. Okay, so this is what we are getting. 8 epsilon 10 to the power 16 w square. He forgot to multiply with q. Okay, here q would also come up. So in this answer as well, q would come up. No, so they forgot to multiply with q. So q would also come up. So electric field would be negative, so that's why negative sign is there, but they would ask the magnitude only. So q into 10 to the power 16 w square 8 epsilon. So this is the answer, E naught max. Now what they are asking? They are asking the built-in potential. Now I know that for finding out built-in potential, what I need to do? First I will write down what is my Vx. So Vx is simply minus infinity to x Ex dot dx, right? And if I need to find out built-in potential, what that would be equals to? Minus infinity to infinity E of x dot dx, or you can say, sir, from minus w by 2 to w by 2 E of x dot dx. Basically, built-in potential will simply be this much area. Can you find out the area? No. because this is parabolic, no? This is parabolic. If it was linear, in the previous cases, when we studied this particular case, in these cases, it was very easy to find out the area. It was very easy to find out this area because it was a triangular. It was a triangular structure. So half into base into height. But now, what is the scenario? Now you are getting parabolic structure. So now it is not easy to find out the area, right? But you can see that, sir, this particular diagram is a bit symmetric. So if I want to reduce my calculation, then this is how I can reduce it. But again, you would require the equation. I would require the equation of electric field to find out the built-in potential. In the examination, if only this much was asked, then I don't require any equation. But what if in the examination, this thing they are asking built-in potential. So there I would require the equation of electric field. So now I have to find out the equation of electric field. If I need to find out the equation of electric field, what I would require? I need to go to this graph. Say yes or no? So what do I require? I require the expression of electric field between 0 to W by 2 only. From 0 to W by 2. So what I would do? I would go to this graph and then I would see what is my expression of Ex. So what is my new target now? I am finding out the expression of Ex between 0 to W by 2. I am finding the expression of Ex. What that would be equals to? 0 to W by 2 rho Vx dot dx, but never ever forget to divide by epsilon as well. So 1 by epsilon I can take outside. Now from 0 to W by 2, what is your rho Vx? Sir, my rho Vx, if I come here, my rho Vx is nothing but this is, what was the equation of this line? That came out to be 10 to the power 16x per centimeter cube. Okay, this equation came out to be 10 to the power 16x, but I need to multiply with q as well. So 10 to the power 16x multiply with q. So coulomb per centimeter cube. This was my equation. So this is my rho Vx. This is my rho Vx equation, which is q into 10 to the power 16x. Q into 10 to the power 16x divided by epsilon dot dx. Okay, from here I will get the expression of a electric field, and once I get the expression of electric field, I will again have to integrate to get the expression of built-in potential. So I don't think like this calculation will be very complex to solve in the examination hall. So I don't think they will be asking built-in potential, but at least they can ask the maximum electric field for sure. Because now this calculation will be a bit complex, like you are finding out the expression of this much, then again you are integrating. So it would take a bit of time. But yeah, we will do it. 1 by epsilon is already outside. So you don't need to write down. This was your rho Vx. So this would come outside. What we will be getting. Oh, sorry guys. Like we are not finding the electric field at a particular point, no? Like here I need to integrate from 0 to x only. Are you able to understand this point? Like I am not finding the electric field at a W by 2. If I am integrating from 0 to x, then also it will not make much sense. If I integrate from 0 to x, because already at 0 I am having some electric field, no? Like if I have written down this particular expression is not making much sense, right? Why it is not making much sense? Because at like what is the value of E of 0? E of 0 is nothing but E naught max, which you are already having this much. But if I integrate here from 0 to 0, what will be the answer? Answer would be 0 only. So this answer is wrong actually, integrating from 0 to 0. So if I need to write down the expression of E of x, I need to write down in this manner. Let's go on the next page. Okay. I need to write down the expression of Ex. So how will I integrate? I will integrate from minus infinity to x rho Vx dot dx divided by epsilon. Okay. That would go out to be minus infinity to x. 1 by epsilon can come outside. What was the expression of rho Vx you were getting? So that was q into 10 to the power 16 x dot dx. Now I know that between minus infinity to minus W by 2, everything is 0. So I don't need to care about minus infinity to minus W by 2. Only I need to care about is from minus W by 2 to any random x. This is the scenario, right? So now what I'm getting the expression of electric field. So this is the expression of electric field that you are getting. So Q into 10 to the power 16 divided by epsilon x square by 2 from minus W by 2 to x. Although this calculation has become actually very complex, so I don't think they would be focusing much on this in the examination, but still we are solving it now. X square by 2 and then minus sine W square by 8. So this is the expression of E of x you are getting. What is the expression of E of x we are getting? Sir, Q into 10 to the power 16 epsilon x square by 2 minus W square by 8. And you can see here, if I put x equals to 0, that would be equals to E naught max. So what answer I am getting? If I put x equals to 0 here, the answer I will be getting is minus Q 10 to the power 16 W square by 8 epsilon. Are we getting the same answer here? Yes, we were getting the same answer only. Minus Q into 10 to the power 16 W square divided by 8 epsilon. So this is how I will write down the equation. Okay. What I was doing here, that was absolutely wrong, was not making any sense. Right. So now what I know is that my built-in potential would be, if I integrate this particular expression between 0 to W by 2, my job would be done. So my built-in potential would simply be 2 from 0 to W by 2 Q into 10 to the power 16 upon epsilon x square by 2 minus W square by 8 dot dx. This is the scenario I need to focus on. Okay. Yeah. So what I would do? So 2q into 10 to the power 16 upon epsilon x cube by 6 minus this thing from 0 to W by 2. Okay. So 2q into 10 to the power 16 upon epsilon I will have to add a page as well. Okay, another page has been already added. So this is purely mathematics, nothing else. So what will happen at 48, right? Are we doing the correct thing? It will be 24 or 48. Then here what I will be getting? W square by 16, W cube by 16. Right? So 3, 2. Yeah. So when I solve it, if I put 3 here, 48, 2, then 24, then 12. So what I'm getting? Minus q into 10 to the power 16. I'm not sure why the minus sign is coming. Minus sign should not be coming, no? Okay, area is negative, yeah. So another negative sign I have to add. What I mean to say is that here I forgot to add the negative sign. Here I forgot to add the negative sign. So everywhere this negative sign is going on. Negative sign is going on. So eventually the answer would be positive sign. Well, epsilon. So when you solve it, this is something that would come up. Okay. Yeah, q into 10 to the power 16 w cube 12 epsilon s. Yeah. So when you solve it, this is something would come up. So your built-in potential is coming out to be q into 10 to the power 16 w cube upon 12 epsilon. Okay, the calculation might be a bit complex, but let's just summarize what we were doing. Like if they are asking only E naught max, is it very tough to find out? No, because I know that, sir, how to find out this particular graph. I just need to calculate this much of area. Once I calculate this much of area, I would be able to get E naught max very easily. Next, if they are asking built-in potential, I know that, sir, I need to calculate this much of a whole area. Now calculating this much of whole area will be a tough task for me. So sir, what I would do, I have to find out the equation of this electric field now. And for finding out the equation of this electric field, what I need, where I need to go, I need to go to this particular graph, which was my rho Vx graph. Rho Vx graph, what is the technique to draw the rho Vx graph? Nd minus Na you draw, multiply with q, your job would be done. Now the matter of concern would be xn and xp. You know that you can take any random xn, you take any random xp, you know that positive area should be equal to the negative area. You equate both of them, you will get your answer. So x and xp relation I got, this is minus w by 2, this is plus w by 2. Total width is w only. From there I got to know. So now I can write down the equation. I have written down the equation of rho vx. Okay. Now I know that my electric field at any point of x could be given as minus infinity to x rho vx divided by epsilon dot dx. Okay. Now what I need to do, I need to find out the expression of electric field. Why I need to find out the expression of electric field? Because I know that my v built in is simply minus w by 2 plus w by 2 minus w by 2 plus w by 2 ex dot dx with a negative sign outside. Now whatever the area that you get here, the same area you will get here as well. So you can do it minus 2 into 0 to w by 2 ex dot dx. So now I need to find out the expression of electric field. So how would I get the expression of electric field? Sir, I am already having the expression of my volume charge density. So I get the expression of volume charge density. I integrate them. From the integration, I get to know this is something that I will be getting. Basically, this is your electric field at any point x. So you know that your electric field would be starting from minus w by 2 to any random point x. So I need to find out the expression of electric field at any random point x. So from minus w by 2 to I will integrate till x. So this is what I have done, and then I get this expression of electric field. This is the expression of electric field that I am getting, and from here I can verify as well what was my E naught max. E naught max was this much only, and I get the same answer calculating the total area as well. So I am getting the same answer. So E naught max also I am getting the same. Then what about the built-in potential? So built-in potential, you just need to integrate from 0 to w by 2 and then do the twice of it. So I got my built-in potential, that is coming out to be q into 10 to the power 16 w cube divided by 12 epsilon. So this is my built-in potential that is coming out to be. Okay, well and good. So this is the answer of this question. Now this particular doping profile that we saw here, this is known as linearly graded junction. There is a specific name for this one. What it is known as? Linearly graded junction. Why linearly graded junction? Because when you draw this particular graph, you get to know that the charge density is linearly distributed, right? Charge density is linearly distributed. So this particular graph is linear. That's why it is known as linearly graded junction. What about this particular graph? Here you can see that if I am drawing the graph of rho vx, if I draw the graph of rho vx, isn't it step graded? What I am saying, isn't it step graded? Like some value and then step jump is there, sudden jump is there, no? So this is known as step graded junction. Step graded junction. So by default, always we study step graded junction only. By default, always we study step graded junction only. By default. Okay, but this is known as linearly graded junction. Another name for this particular junction is, it is known as abrupt junction as well. So if these kind of words are mentioned in your examination, then you don't need to worry. Okay, if they are saying abrupt junction, then abrupt junction, abrupt change, abrupt means sudden change is there. So here in the volume charge density, there is sudden change, like negative charge, then suddenly positive charge you are getting. But here there is not here there is no sudden change, like negative charge, then negative charge is going down to 0, and then from 0 you are getting positive charge. So they basically negative charge is going down, it became 0, and then positive charge. This is how it is going. But here what is the scenario? Sir, same negative charge, and suddenly positive charge, right? Negative charge, then suddenly positive charge. That means there is abrupt change here. So this is known as abrupt junction or step graded junction. But here there is linear change. So this is known as linear graded junction. Now in the abrupt junction, abrupt junction or step graded junction, the doping profile is uniform. Why I will call it uniform doping? Someone would say that, sir, Na is not equal to Nd. How you are saying uniform doping? Uniform doping means one particular domain is uniformly doped. The p side is uniformly doped, n side is uniformly doped. So that's why I will call it uniform doping. But here in this case, this is non-uniform doping, no? Even on the p side as well, there is non-uniform doping. You can see that even on the p side as well, there is non-uniform doping. Somewhere Na is more, Nd is lesser, then Na is not that much more. The gap between Na and D is not constant, right? This gap is not uniform. That means Na is continuously decreasing, although Nd remains same, but Na is decreasing. So the gap between Na and D is decreasing. What does that mean? When you move from minus infinity to 0, your number of holes are decreasing. That means p side is not uniformly doped, n side is not uniformly doped. There is no uniform doping. So if there is no uniform doping, what does that mean? This is known as non-uniformly doped. Okay, so this particular profile, I will say non-uniformly doped. So for non-uniformly doped, your rho Vx would be linear, right? And then this was your linear, rho Vx became linear, and your electric field profile became parabolic, right? But here what was the scenario? It was step, or let's go here. This was step, electric field was linear, and your potential was parabolic. Here what kind of potential profile you will be getting in this case, in the case of linear? In this case, already my electric field profile is parabolic. That means already my electric field is proportional to x square. So what do you think what your voltage would be proportional to? It would be proportional to x cube, right? Are you able to understand this point? Basically, rho Vx is proportional to, let's write down as conclusion only. So what I am saying, uniform doping. What is the meaning of uniform doping? Uniform doping. Uniform doping means your charge density should not be a function of x. That means it should be a function of x to the power 0. Do you agree to this point? Uniform doping. Charge density should not be a function of x. Like when I am moving in x, the charge density should remain uniform only. Like whatever the Na doping that you are doing or whatever the Nd doping you are doing, in this particular region, Na doping should be uniform. In this particular region, Nd doping should be uniform. Na, Nd should be uniform. That means my rho Vx should be a function of x to the power 0. And you can check here. You can check in this case, your rho Vx is a function of x to the power 0. If I ask you what is the doping profile at minus xp, you would say minus qna. If I ask you what is the doping profile at minus xp by 2, you would say minus qna. If I ask you what is the doping profile at minus xp by 3, you will say minus qna. That means it is not depending on x. Is that clear to you? If this is the scenario, then how will your electric field look like? Your electric field would be a function of x to the power 1. Why is that so? Because you know that electric field is simply the integration of rho Vx, and then my potential is simply the integration of Ex. So integration of x to the power 0, what that would be? X to the power 1. And then integration of x to the power 1, what that would be? X to the power 2. But for non-uniform doping, your rho Vx could be a function of x to the power n. I don't care what is the value of n. I don't care. It could be 1, it could be 2, but n cannot be 0. If n is 0, what does that mean? If n is 0, that means that if n equals to 0, that means it will be the case of a uniform doping. So n is not equals to 0. N could be anything. It could be 1, 2, 3, 4. It could be anything. So what would be my electric field? So that would be the function of and what would be my potential? So that would be the function of n plus 2. Yes or no? Okay. So this will show uniform doping. This will show non-uniform doping. Another thing we can see, for abrupt junction versus linearly graded junction. Graded junction. What was your W depletion? That came out to be 2 epsilon by Q 1 upon Na plus 1 upon Nd into V built in. So I could see that W depletion is proportional to V built in to the power 1 by 2, right? In case of abrupt junction. In case of abrupt junction. In case of linearly graded junction, what you can see? Your V built in is actually coming out to be proportional to depletion width to the power 3. That means your depletion width is proportional to V built in to the power 1 by 3. Okay, so some conclusion you can see, like in ESC they can ask this conclusion, that in linearly graded junction your depletion width would be like Like somewhere you can use this particular expression, like depletion would be proportional to 1 by 3 power of a built-in potential. But in your abrupt junction, it is proportional to 1 by 2 power of built-in potential. Okay. But this conclusion you will remember what is the meaning of uniform doping and what is the meaning of non-uniform doping. Non-uniform doping doesn't mean that sir Na has to be equals to Na would be not equals to Nd. No. Uniform doping means whatever the p side doping you are doing, that should be uniform. Whatever the n side doping you are doing, that should be uniform. If that is the case, then my volume charge density will never be a function of x. If it is not a function of x, that means electric field would be a function of x and my potential will be a function of x square. What about non-uniform doping? Non-uniform doping means my rho Vx would be a function of x. It could be anything. It could be x square, it could be x cube, it could be simply x. So let's just say in this case, our rho Vx was, in this particular case, our rho Vx was simply proportional to x only, right? Rho Vx was simply 10 to the power 16 x cube. So 10 to the power 16 is constant, q is constant. So rho Vx was simply proportional to x. That's why our electric field came out to be function of x square. And you can check as well, our electric field, when we find out the expression, it came out to be a function of x square only. It came out to be a function of x square. And then eventually your built-in potential or your Vx would have come out to be a function of x cube as well. So this is the scenario. Okay. So you understood the meaning of uniform doping, you understood the meaning of non-uniform doping as well. Let's see this particular question. We will come back to this question, but first let's solve this particular problem, which was asked in gate examination only. So you let me know which side is P, which side is N. From where this plot would have come? You know that sir, electric field plot has been given. It would have surely come from rho Vx plot. Sir, you are having here positive slope and then negative slope. That means what kind of rho Vx plot you would have got? Like, can you comment on the rho Vx plot? Like, basically you differentiate it, no? If I differentiate it, what I will get? Basically, what will be your rho Vx? Rho Vx will simply be proportional to this thing. Integration goes here. Integration goes to the other side. What you will get? Differentiation. So you differentiate it. Positive slope and then negative slope. So what kind of rho Vx graph you would get? So this kind of rho Vx graph I will be getting. Positive slope. Here the slope is higher. So what I would do, I would make the slope higher here. And then negative slope. But this width would be more, no? This width would be more. So this kind of rho Vx I would have got, right? If this kind of rho Vx I am getting, that means here I am having positive charge, here I am having negative charge. What does that mean? This has to be N type, this has to be P type. Who is having more doping? So which side is P, which side is N? This side is N, this side is P. But we usually do, we usually take Pn, but here they have taken NP, right? Now which is highly doped, which is moderately doped? You can see that depletion width here is lesser and depletion width here is more. What does that mean? This is highly doped and this is lightly doped. Is that clear to you? Okay. Now what they are asking? Find charge per unit junction area in the depletion region of N side and P side. What you need to find out? You need to find out charge per unit junction area. So second question is charge per unit junction area. Charge per unit junction area. That means Coulomb per centimeter square. This is what I need to find out on N side and P side, in the depletion region of N side and P side. So depletion region of N side and P side, this is what I need to find out. What do you think what I need to find out then? I need to find out Q N A X P. This is what I need to find out. This would be my charge per unit area P side depletion. Say yes or no. This is something I need to find out. Now this 10 to the power 4 volt per centimeter is given. What do you think what it is? 10 to the power 4 volt per centimeter that is given. Isn't it equals to Q, here doping is Nd, right? Here doping is Nd and here doping is Na. So isn't it equals to QNA XP divided by epsilon or QND divided by epsilon? Say yes or no. If you just make this plot, what you will do, you will integrate it. What would be this point? So this point would be minus xn, and sir this point would be xp, and sir here I will get a total positive charge, here I will get total negative charge. So QND and QXP, if I make this plot again here, although now you should be able to do this problem, actually should not be very difficult for you, you should be able to do it. This is minus xn, this is xp, this is my rho vx. Here what I will get? Here I will get QND, and here what I will get? I will get minus QNA, right? Okay. When I integrate this and then divide by epsilon, what I will be getting? Electric field. So what would be my E naught max? E naught max would simply be QND divided by epsilon, or it could be equals to QNA divided by epsilon. Why they are equal? Because you know that this much area would be equals to this much of area. So from here also you know one thing, that ND into Xn would be equals to Na into Xp, right? So what I need to find out, charge per unit area in P side depletion region or charge per unit area in N side depletion region. So isn't it representing charge per unit area only? This is your charge per unit volume. P side depletion width is this much. So multiply with XP. So charge per unit area I am getting, right? So what will be my answer? Answer would simply be 10 to the power 4 volt per centimeter multiply with epsilon. What is the value of epsilon that has been given? Somewhere they would have mentioned the value of epsilon, that is 12 into 8.85 into 10 to the power minus 14. So 12 into 8.85 into 10 to the power minus 14 farad per centimeter. Farad per centimeter. Okay. So what answer I will be getting? 12 into 8.85 10 to the power minus 14, right? Twelve into 8.85. So 10 to the power minus 10. So 10.6 nanocoulomb per centimeter square. This much charge per unit area you will be getting. On N side as well, on P side as well. On N side it would be positive, on P side it would be negative. I hope you are able to understand this answer. Charge per unit area. Charge per unit area would be this much, or it would be equals to this much. So this is my charge per unit area. This is on the P side, and this will be on the N side depletion. So charge per unit area on P side depletion width, on N side depletion width, QNA XP, QND XN. Understandable? And I was given maximum electric field. From there I find out this particular expression. Okay. Next, what they are asking, N side and P side are uniformly doped or non-uniformly doped? Uniformly doped. Why is that so? Because you can see this plot. It is function of x to the power 0. Right? So it is uniformly doped. What is the built-in potential? Sir, built-in potential will simply be area of this much. Right? Built-in potential will be area of this much only. No? Because what will be my built-in potential? That would be minus infinity to infinity E of x dot dx. Surely there will be a negative sign. But they would ask the magnitude of built-in potential. Okay, magnitude of built-in potential they would be asking. So they would be asking the magnitude. So you take the magnitude. So simply calculate the area, half into base, which is in micrometer. So can I write down base is 1 plus 0.1, that would be 1.1 centimeter, right? Into 10 to the power 4 volt per centimeter. So this and this get cancelled out. 0.1 volt. Centimeter is getting cancelled out, 10 to the power minus 4, 10 to the power minus 4 is getting cancelled out. This would give you 1.1 divided by 2, that would be 0.55. So 0.55 volt, that would be the magnitude of built-in potential. Okay, very straightforward thing, very straightforward. So it was uniformly doped. Built-in potential I can find out. E naught max is given. From here I can find out the charge density as well. All the plots I can find out. Only one plot I require. If I get one plot, all other plot I can make. Right? From electric field we are going to charge density this time. Usually we used to go from charge density to electric field, but we can come from electric field to charge density as well. There is no issue. We just need to differentiate it. So when I differentiate it, this is what I get. And when I differentiate it, I get to know that this side is actually positively charged and the other side is negatively charged. That means this side has to be n type, this side has to be p type. Right? So n type and p type side will be, so that means it is np, not pn. So left side is n type and right side is p type. Now the second question was a good question, like find charge, total charge per unit junction area. Total charge per unit junction area in the depletion region of n side and p side. That means from 0 to xn, how much positive charge I am having. This is what they were asking. So qna xn, this much positive charge per unit area between 0 to xn you would have. So qnd xn, not qna xn, qnd xn, or it would be equals to qna xp as well. What next they are asking? Total negative charge from 0 to xp. Total negative charge from 0 to xp. How much total negative charge you are having from 0 to xp? This is what they are asking. So that would be q na xp. That's it. So I was already having the value of this much. What is this? This would be equals to q nd xn divided by epsilon, and this would be equals to q na xp divided by epsilon, and then I equated both of them and I got the value of q na xp or q nd xn. That is coming out to be 10.6 nanocoulomb per centimeter square. Okay. So yeah, that's it. Now let's see this question. Like you can treat it as a concept or you can treat it as a question as well. The concept says dependency of V built in on different parameters. Dependency of built-in potential on different parameters. So let's just keep this topic. So you can treat this as a question or you can treat this as a concept as well. So what they are asking, that built-in potential will increase with the doping concentration. So what is the formula of built-in potential? You know, sir, kT ln Na Nd by Ni square. So Ni square will be a constant value when it is compared with doping. Like if I am doping means I am increasing Na, I am increasing Nd. What does that mean? My V built-in will also increase. First statement is true. If doping concentration is increased, then built-in potential will also increase. Second one, if intrinsic carrier concentration increases, then built-in potential decreases. That is correct only. If Ni increases, then V built-in decreases. If this increases, then this whole thing decreases, ln decreases, so whole value will decrease. Very simple thing. Temperature we will see later on. Let's see this one. For semiconductor with larger band gap, the built-in potential will be larger. What does that mean? If larger band gap, if Eg is large, what does that mean? Ni will be low. Why Ni will be low? Because you know that Ni square is some constant t to the power 3 e to the power minus Eg by kT. So if Eg is more, then this particular value is more. That means this particular value is less. What does that mean? That means Ni is less. Right? So if Eg is more, Ni is less. If Ni is less, then this whole value will be large. So V built-in will be large. Right? Inverse relation is there. No, if Ni increases, V built-in decreases. So if Ni decreases, V built-in will increase. What about the temperature? Now temperature will depend on two parameters. Temperature would be interesting. So you think of it. If temperature increases, then this thing will increase. But what about this one? If temperature increases, Ni will also increase. No, what I mean to say is that if temperature increases, then Kt increases and Ni also increases. So this value is increasing, that means this whole value is decreasing. So Ni is saying that, what Ni is saying, that built-in potential should decrease. What Kt is saying, built-in potential should increase. Are you able to understand this point? One is saying that if Kt is increasing, then he is saying that this should increase, and he is saying that this should decrease. So what will happen? Eventually it will increase or decrease? It will actually decrease. Why is that so? We will see that. Okay, it will decrease actually. Okay, the decreasing effect would be more than the increasing effect. Why is that so? Let's see it. So I need to add a page. PN junction we were having, no? So PN, this was the scenario. EC, EV. So at the P side, and this was at the N side, and in between I was having EFI. This was my EFP, this was my EFM, right? What was your V built-in? V built-in was just simply the addition of these two guys. Basically, this was my V built-in. This was my V built-in, right? If temperature increases, this is my intrinsic Fermi level. You know that if temperature increases, Ni value increases. That means if temperature increases, this guy will come downward. If temperature increases, this guy will come downward and this guy will go upward. I hope you remember this particular thing. If temperature increases, EFN comes downward and this guy goes upward. Do you remember this thing? That means V built-in will decrease. V built-in will decrease. If temperature increases, EFN comes downward, EFP goes upward. That means this gap will be reduced. For increase in temperature, this gap would be reduced then. What does that mean? V built-in will decrease. V built-in will decrease. And one more thing from now onwards you will remember, that temperature and Ni are separable brothers. What does that mean? That means temperature would always listen to Ni. No matter whatever the kind of expression you are having, temperature would always listen to Ni. So if someone is saying temperature increases, then what you would know? If temperature increases, that means surely my Ni is increasing. This thing I told like 10 times, that if temperature increases, that means our semiconductor will move towards being the intrinsic semiconductor, right? I hope you remember the plot as well, Ni versus temperature plot. So we will be moving towards being the intrinsic semiconductor. I told that that plot is also very, very important. So you go and check out in the basic semiconductor physics that if temperature increases, this EFN would come downward and this EFP would go upward. That means built-in potential will decrease. So what I am saying, that temperature and Ni are inseparable brothers. What does that mean? That means temperature will always look for Ni. No matter whatever the other expression is there, I don't care. Other guys are saying that you increase, decrease. No. Temperature will say I will always look at Ni. If temperature increases, Ni increases. That's it. So if temperature increases, Ni increases. If Ni increases, this will decrease. So you don't need to think this much in the examination. In the examination, if any kind of statement is written, one statement is about temperature, other statement is about Ni. So whatever that is happening with Ni, the same thing will happen with temperature as well. So Ni says that if I increase, where is Ni? So Ni is saying that if I increase, then built-in potential decrease. So temperature will also say the same thing, that if I increase, then built-in potential will decrease. So temperature and Ni are inseparable brothers. This is not for built-in potential for anything, anywhere. This will always be applicable. Is that clear to you? Okay. Whatever Ni says, the same thing temperature would say. Not only for built-in potential, for anything in the whole EDC, for anything. If temperature increases, Ni will increase. So if Ni is increasing, what is happening with built-in potential? Built-in potential is decreasing. So temperature will also say that if I increase, built-in potential will decrease only. Although from the diagram we have proved it, because someone might be having confusion that, sir, there are two things. One is saying it should increase, one is saying it should decrease. So who would I listen to? So from the mathematics, we are not able to conclude. So from the Venn diagram, we are able to conclude now. And from there, we made one conclusion that temperature and Ni are inseparable brothers. That means whatever Ni says, the same thing temperature would do, or opposite also you can say that whatever temperature says, Ni would do the same thing. Is that clear? So all 4 points are true. So in true false, this kind of questions can be asked. So you write down the expression and your job would be done. Okay. Doping more, what does that mean? Built-in potential would be more. Ni more, that means built-in potential would be less. Temperature more, built-in potential would be less. And larger band gap means Ni would be lesser. If Ni is more, that means built-in potential will be large. All good? All fine? And from this, the important conclusion is this much. Okay, so this is the lecture that has ended. We have understood a lot of things about PN junction under equilibrium. So this time in this lecture, we did not apply any external bias, right? I hope this lecture made you feel better. Like if you have already studied this particular topic, then I am pretty sure you did not study in this manner, right? No matter from whichever god you have studied, there are a lot of god of EDC in the market. They will say that no one in the history of EDC, I think they derived EDC. Okay, there are a lot of educators, there are a lot of GATE educators who have done a PhD, or I don't think like 10 PhD they have done in EDC, and they feel like that EDC was made by them only. So even if you have studied from those kind of God educators, then also I feel that here you have learned a lot of new things. And in the next lecture, whatever the mistakes those God educators do, that I will point out when we study forward bias. Because in the forward bias, a lot of God educators teach a lot of concepts wrong. Okay, so that we will see in the next lecture. And here as well, a lot of things would have been clear to you, like this kind of thing, that how to make the doping profile. Like if doping profile is given, then how do you make the charge density plot? How will you make the volume charge density plot? From volume charge density plot, how would you reduce the mathematics? This is the minimum mathematics that we are using. Here if you see this derivation, then these kind of derivation would come after a lot of mathematics, but minimum mathematics we are using. For E naught max, I am not using any mathematics. For built-in potential as well, I don't need to use any mathematics. But if they are asking between two random points, like between minus 2x by 3 to xn by 3, if they are asking electric field at a random point, then I need to use mathematics, right? So till this date in the examination, they have asked maximum electric field or built-in electric field only. Like here your chapter has ended. On this slide, till this date in the GATE examination, this much thing has been asked. After that, we are discussing what can be asked in the examination. In future, what can be asked. So in future, this thing can be asked. That at two random points, they can ask you about electric field, or at two random points between them, they can ask you about built-in potential. Is that clear to you? Okay. And then why we studied this particular slide? This particular slide we studied just to let you know that it is not necessary that always the doping profile will be linear. It could be non-linear as well. So here doping profile is non-linear. So how would I treat it? ND minus NA. ND minus NA plot I will draw, and I will multiply with Q. X and XP I will mark out. X and XP relation I will get from the charge neutrality. Okay. So that's it. This we studied, and then we studied the dependency, and then we saw this particular numerical problem as well. Okay, not numerical problem, this was conceptual problem only. So with that, we have ended this particular lecture. Okay. So in the next lecture, we are going to study PN junction under forward bias. So there as well, we will see a lot of new things, a lot of misconceptions that students are having, and we will try to eradicate those misconceptions. Okay. So let's meet in the next lecture. Thank you very much.